Good morning, everyone. Welcome to Predictable AI, Evaluation, Anticipation, and Control. So first things first, we would like to thank our university for hosting this event. And we have the pleasure to have the Vice Chancellor for Innovation and Transfer at this university, Universitat Politècnica de Valencia, Salvador Coll. The floor is yours. Thank you. Please do the opening.
Thank you, Jose, and good morning to everyone. Welcome, ladies and gentlemen, to the Universitat Politècnica de Valencia, to the Universitat Politècnica de Valencia Science Park, the Polytechnic City of Innovation that is hosting this event today. And welcome to Predictable AI, Evaluation, Anticipation, and Control. Thanks to the organizers, in particular to Professor Hernández Orayo and the rest of the team for inviting me to share some time with you all today. It gives me great pleasure to extend to you all a very warm welcome on behalf of our rector and to say how grateful we are to all the invited speakers, contributors, and collaborators who make this event possible today. We are a young university, only 54, but even our youth, UPV, is currently positioned as the first Spanish technical university in various international rankings. UPV has a strong position in European research projects, where we are among the top 5 Spanish universities. And we also rank as one of the Spanish universities with higher tech transfer indicators, such as patents, patent licensing, or income from R&D contracts with industry. Traditionally, we have had strong links with industry, and this is one of our singularities in the Spanish universities ecosystem. Right now, we are at the UPV Science Park, the Polytechnic City of Innovation, an area of the campus where we host a great part of our research institutes and companies, both startups and spin-offs promoted by students and professors or external companies that host here R&D labs to be close to the talent, close to the research activities developed here at the UPV. One of our main goals is trying to speed up the process of translating knowledge into social, environmental, and economic impact at local and global level. Predictable AI fits perfectly into this strategy. Congratulations for showing us how to contribute to the development of science linked to its impact on our well-being and the sustainability of our society. During this meeting, you, apart from reaching to know UPV and Belgrade, will have the opportunity to renew contacts and discuss problems of mutual interests. We are delighted to have you all involved in boosting collaboration, sharing experiences, and contributing to the evolution of artificial intelligence. It is gratifying to know that the agenda covers many very stimulating sessions. Considerations critical to generating a positive impact on our future will be covered today. Robustness of AI systems, predictability, reliability, and legal implications, apart from the indispensable technical background that you all master. I would especially like to express our gratitude to our distinguished speakers and panelists that will delight us all. Finally, I'd like to thank each of you attending Predictable AI, Evaluation, Anticipation, and Control, and bringing your expertise to our gathering. You have the vision, you have the knowledge and the experience to help us pave the way into the future. Throughout the day, I ask you to stay engaged, keep us proactive, and help us shape future innovations. My personal respect and gratitude go to all of you. Enjoy your stay in Valencia and have a wonderful meeting. Thank you very much.
Thank you very much for finding some time in your agenda to be with us today. So I'm going to give you a few details about the event today. So the first thing is, of course, why predictable AI. And this comes from a kind of reaction to a kind of a general feeling in the field of AI that AI is unpredictable. We have this kind of a crisis that, well, you, especially with very powerful systems and things such as language models, that basically you can get some of the best results from these systems, but also some very disappointing results. So in a way, depending on what you ask or what you try to instruct, or the instructions you want to give to these systems, they are very unpredictable in terms of the quality of the results. And that's something that perhaps is even worse than it used to be in AI, despite the progress in AI. So people are assuming, in a way, that we are going to go in a direction of an AI that is very powerful, but also very unpredictable. And we try to react against that. And this is the motivation for the event, for this initiative, Predictable AI. So the first thing is we need to understand why current AI techniques and current AI systems, why they are unpredictable. And more importantly, we need to think how we can change the situation, make AI systems more predictable, and especially how we can design the AI futures that we want, that we make AI in the future, especially as interactive with humans, that we know what is going to happen in terms of things such as alignment or safety. I think that there are two critical things that we need to anticipate, we need to control. And for that, we need to evaluate the systems well. So this is a little bit why we have this, this subtitle for the event today. Today is 8th of March, so we are competing against a lot of events at the university and elsewhere, because it's a very important day. It's an International Women's Day. And I think that the best way of celebrating that day is if you look at the lineup of speakers today. I think that's the best way, and I think that we don't need more words than that for celebrating that day. And I'm not going through the agenda. You have it here, and I think that we haven't changed the agenda, so I think it's still what we had planned. So maybe that's some at some point we have to readjust something, but for the moment it's exactly as it was planned. So let's see, we are able to predict this well. There's kind of a diversity of sessions, including invited speakers, panels, line speeches. We also have this kind of session at the end. Today we will give more information about how this works. People who are directly involved, they know a little bit, but there's a little bit of unpredictability there. So, and that's going to be fun as well. So that's the agenda for today. This is meant to be very informal, so we welcome a lot of questions from you. The shorter the questions are, the more questions we can have. Okay, so just stress this. So we have the speakers and we have the questions. Try to just to, but of course we want many questions from you, and even comments or opinions and things like that. That's also very welcome, of course. So yeah. So without further ado, maybe we can start with our first speaker. I think she's already connected, so some of the things that, so in the case of, okay, we have Irina there. In the end, she couldn't make it. That was kind of a last minute change, but we are very lucky to have her here today. So Irina Rish is professor the Computer Science and Operations Research at the University of Montreal, and she holds a Canada Excellence Research Chair in Autonomous AI and a Canadian Institute for Advanced Research Canada AI Chair. She's also part of Mila, one of the most prestigious and most influential AI research centers in the world at the moment, where I would say a lot is kind of as the center of the hurricane in this moment in AI, in a way. And she's worked in many, many different fields. So I could go through all of them and all of the accolades and things, but I think it is much better if I give the floor to her and we can just hear what she has to say, which is more interesting than what I have to say. So thank you very much. Irina, the floor is yours.
Thank you so much for inviting me. I apologize that I couldn't be there in person. I kind of really was looking forward to it, but yeah, things came up. So I'll try to share my slides now. Okay. Okay. This is not the first one. Let me just move back. Okay. Okay, well, thank you again for your introduction. And yeah, I really look forward to discussions and even panel session despite of the time difference between Montreal and Valencia. And I think the topic of my talk today is kind of precisely aligned with the theme of the conference about how can we predict AI behaviors, even if not completely, like what can we do, what can be kind of the best effort to do so in terms of predicting performance, predicting potentially unexpected changes and novel behaviors that can emerge. And how can we also make sure that we can build those systems in more kind of democratized way, not just kind of allow them to be developed at a few industrial labs, but let people in open source AI communities and in academia also kind of be able to compete in this rapidly growing field. So I'll tell you about all these three parts of the story. But first, yeah, I want to kind of start with the ultimate goal that many people are talking about, kind of achieving the artificial general intelligence and what exactly it means. And to be honest, it really depends on people you talk to. And people sometimes argue because they define things somewhat differently. Some think it's like superhuman intelligence. Some think it has to be something with consciousness and so on and so forth. But we can actually go back to the more practical definition of artificial general intelligence as a broad, versatile, multitask kind of intelligence that would be in some sense similar to what humans can do in terms of being able to learn during their lives to do so many different things, even though you might not necessarily be champion in chess or Go in the world. You can learn those games, but you can also learn to play musical instruments, and you can do like many useful tasks. So OpenAI definition at high level characterizing such systems as highly autonomous systems that outperform humans. I would say at least let's see if we can perform at the same level first. At most economically valuable work, well-read, useful tasks. So the system is multitask, general, broad, and those tasks are useful. And if you think about this idea about generalization, it actually was always there as an ultimate kind of holy grail of the whole field of AI and previously even statistics and machine learning. Because in statistics, as you know, when people are trying to fit curves to a cloud of points, essentially they are trying to see if that curve will predict or extrapolate well to the unseen points coming from the same data distribution. In machine learning for a long time, people were also looking at this type of a generalization to IAD kind of samples, presumably from the same distribution. And that was like the topic of most of the classification work in machine learning. More recently, people started pushing the boundary towards out of distribution generalization when the data experience certain kind of domain shifts, task change, and things go a little bit out of the, well, distribution on which the model was trained on. And many related kind of subfields of machine learning intersect with this idea of out-of-distribution generalization, like transfer learning or meta-learning or continual learning. There are different kind of settings, but the goal is roughly the same. You want to learn systems that eventually can do many different tasks. And those tasks may correspond to very different distributions of data, and also this different distribution of kind of objectives that the system need to achieve on those data. Recently, literally kind of in the past couple of years, we are all experiencing what one can probably call neural scaling revolution. The advent of large-scale, pre-trained, unsupervised systems that serve as a basis for various recent advances that we kind of observing in terms of all the ChatGPT and similar models like taking the world by storm, and all the generative models, well, Stable Diffusion, Midjourney, you name it, DALL-E. Also kind of generative AI is being kind of achieving the results that it was never able to achieve just until recently. So what is going on actually here? Because I mean, the field of AI tried to achieve the high level of generalization and all this kind of type of human-like generation of text and images for a long time. But I always like to kind of remind people about so-called bitter lesson by Rich Sutton. That was kind of a brief position write-up that he wrote in 2019, saying that look at the whole history of AI research. It started with kind of trying to put our knowledge into systems in very direct way, like rule-based systems, expert systems. And then with more compute, those systems became obsolete, and more generic kind of systems like just universal neural networks with a lot of compute, with a lot of data, essentially won over all this specialized kind of rule-based systems and so on and so forth. And this essentially was going on. So the compute becomes more available and cheaper, and therefore the methods that kind of were generic but just didn't have enough power, not enough compute to show kind of good results, becoming prevalent in the field. And the whole history of deep learning is a good example of that, essentially. It's also example of scaling compute and scaling data and then scaling deep network models. And it's important to kind of keep in mind that focusing maybe on simpler generic methods that with advent of compute can solve your problems is important, because maybe you shouldn't be wasting time on kind of more myopic goals of building some improvements due to putting too much of our knowledge. You should work on the methods that will scale well. So, but to know that models scale well, you will need to be able to predict their scaling laws. And examples go on, like in chess and other games, people started with systems that would be very specific to the game, that would incorporate the rules, the intuitions and heuristics that people developed. And later on, all of them were kind of outperformed by generic massive deep search and self-play, for example, in Go and so on and so forth. So examples go on, but the bitter lesson was bitter because essentially was kind of reminding people that a lot of work went into putting all the specific inductive biases, specific knowledge, which maybe was a bit too specific. And what won historically was generic methods, well, deep learning and search, and maybe generic architectures without too much of the specificity built into them. And essentially, the lesson is maybe we shouldn't be focusing on putting too much of the final result of the evolution into those systems, but we may actually want to develop systems that can evolve in a sense like we did, not the end result of that. So kind of a second order inductive biases, so to speak. And well, where we are with kind of this bitter lesson right now. So we see that what is state of art and what is taking the world by storm are generic transformers that are behind an attention mechanism, which turn out to be extremely important because it allows one to really choose a small potentially number of relevant things out of, say, large context. And now we have all this kind of recent state of art chatbots and generative models, and I can go on and on just like talking about them, but you probably all know like what's happening with ChatGPT, with Bing, and with all its rivals. So the field is accelerating at like exponential speed. It's kind of started and was outlined a couple of years ago in a paper from Stanford called Foundation Models, because it was a paper in 2021 in August, and it was just right after the, advent of GPT-3. So essentially GPT-3 kind of started this whole era of like scaling revolution. And the idea was that instead of doing what people used to do in machine learning before, like training specialized systems that would be optimized for particular tasks like classification for specific types of data, you pre-train in unsupervised way or self-supervised way a very large model with generic architecture like transformer on very large amount of very diverse data. And essentially what's going on, if the data are sufficiently diverse, like, I don't know, you collect the text from all of the internet, or you collect like some incredibly large amount of imaging data, then this diversity, the amount of information in the data is in some sense a good sample of what can possibly like happen, like say with language. And then if the model is large enough, has capacity to incorporate this kind of large amount of information, then essentially you get pretty good model or the distribution of how things are in that particular modality, or as it turns out later, they can actually generalize to other modalities as well. So they manage to extract high-level concepts that seem to be quite generic, no matter what modality you're using. And jumping ahead, I'm talking about papers like Transformers Universal Compute Engines that show that you can pre-train on language, but with minor modifications, you can adapt the system to images and so on and so forth. So that's why people kind of call them foundation models, because those models can serve as a basis for adaptation and other applications on top of them, because they serve as essentially a knowledge base about what's happening, what the distribution of the data is. And again, I can go on, and this list is just very beginning of 2020 when the GPT-3 was released, but like in May, end of May of, I think, 2020, followed by Clip, which was image to text, and DALL-E, text to image, then Copilot for code generation, and then Stable Diffusion last year, and ChatGPT also last year, and so on and so forth. So basically those foundation models keep popping up like mushrooms after the rain, and at ever increasing speed, because more and more people are getting excited about that and kind of get into this AI race. And if you think about that, it's essentially an autoregressive model, the original GPT-3 and the kind of subsequent versions. It's just basically trying to predict the next token given the window of the previous tokens. The major difference is not the change in the architecture, but rather change in the scale of both the model and the amount of data it was pre-trained on. And that change comparing to its predecessors is orders of magnitude. As you probably remember, GPT-3 was 175 billion parameters, while the closest to it previous versions were definitely much smaller than that by like 2 orders of magnitude. And as I was saying, what was essentially happening and what was claimed to fame by those systems is that this is example of Clip, pre-trained in unsupervised way on multiple image data, and then generalizing zero shot or out of distribution to new data sets, which were quite different from what it's seen before. And it was outperforming like state-of-art specialized systems by far. And essentially that is kind of the gist of this large-scale pre-trained or foundation models. They are able to generalize to previously unseen tasks and novel data in 0 or maybe few shot. That's precisely an element of this kind of generalist AI that we are all kind of trying to build. So the classical plot from the old GPT-3 paper shows how the ability of the system drastically improves with its scale. And here is essentially how the accuracy on particular task changes with the number of samples in the data. And you can see that once the model size jumps from the less than 2 billion to 175 billion, the curve of the improvement in performance becomes much more efficient. So the system really starts performing much better on the same number of examples in the context. So that's how scale matters, essentially. And so on and so forth, the dependence of performance, not just on the size of the model, but also amount of the compute that goes into training such model. And those different curves, also from the GPT-3 paper, show essentially validation loss for different models at different number of parameters corresponding to different colors. But they all show that essentially you observe that the best performance is following what's called power law, or the straight line in log-log plot, essentially. And then there was this kind of, by now, classical paper by Jared Kaplan and his collaborators from OpenAI. Jared Kaplan is a professor at Johns Hopkins University in physics, but also now co-leading Anthropic, as most of you probably know, focusing not just on building capabilities of systems, but making sure that while doing so, we keep an eye on alignment with human values and measure it in different ways, and so on and so forth. I will mention it later again. So scaling laws, the classical scaling laws, the first kind of paper was essentially showing that if you consider 3 key variables on x-axis, it's either compute or dataset size or the number of parameters. And if you essentially look at the dependence of the performance, in this case it was test loss, as a function of that key variable, then you observe your power loss that I mentioned before, which are actually surprisingly simple dependencies between performance and the kind of variable of interest. So in these plots, essentially what they mean, if you take the best, if you fix, say, compute, but you can vary the data set size and number of parameters of the model the way you want to achieve best results and plot those best results, you will get this type of a straight line in log-log plot. Same goes about fixing data size and not constraining or not bottlenecking the other 2 variables. It's just different kind of slope of the curve, but essentially they're all power laws. And the holy grail of the whole scaling field became how do you improve scaling? How do you improve this exponent of the power law that would correspond to improving in the slope of how fast the loss kind of decreases given the key parameters. The interesting thing about scaling, one can ask, why do you need scaling laws? First of all, if you know those scaling laws, it's essentially investment tool for machine learning researcher, because you know when you will have more compute and data, which method will win, and therefore you can invest in that. And this is another example from different paper comparing visual transformers with classical convolutional networks like ResNet. And you can see that at a relatively small number of samples, or kind of, at 10 million, you see that, as you would expect, the convolutional networks are outperforming those transformers. And convolutional networks were state of art in the field of image processing for a long time. And they are essentially example of those inductive biases where you incorporate what we know about, say, visual system of humans directly into architecture. But then at the larger scale, when the data, more data become available, And again, I guess you have more compute to utilize this data and train larger models. You see that actually generic architecture of the visual transformer starts outperforming the specific architecture of convolutional network. And this is something very important to know, because that can give you the idea what will work better in the future and what should you invest in if you know that we will get more data and compute will become more available. So as I said, scaling laws are essentially a guiding tool predicting future behavior of different methods so you can choose wisely. It's like investment tool. So, well, the history of scaling laws, of course, didn't start just 2 years ago with Jared Kaplan's paper. It started a long time ago. And there were different attempts to model scaling behavior. And perhaps one of the earliest papers was from 1994 by Karina Cortes and the famous Vladimir Vapnik and Sarah Sola and others. NIPS 1994, essentially they looked into power laws. They observed power laws as well in much simpler, smaller experiments, but with also neural networks. And the power law is simply, as you can see here, is an expression. It's like polynomial. Essentially, it's y on the kind of y-axis, which is performance, equals constant a times x to the power of b plus another constant. So we kind of use this notation to denote like several types of functions that people try to use historically to model performance at scale in neural networks. And this is like the snapshot from that paper, where essentially they were making same point I was just mentioning, and I was showing with those visual transformers versus convnets. So this is more of a hypothetical example, but argument is precisely the same, that if we don't yet have enough compute, or basically this compute may be developed in the future, but we do want to know what method, if we have several candidates, will be more promising and will stand the test of time, we need to study scaling laws, because even at the low scale, like you don't have to have large compute and maybe very large data set, but if you can predict the trend, then you will know that in the future, one method will beat another method. And that's important to know, because then you will invest that compute in the more cost-efficient method. Essentially, it's the same point was made in that paper, just like it's being made in more recent ones. And they did observe power laws in the performance of like very small neural network. In that case, it was like, well, three-layer network, 110 and 10. And interestingly, as I said, to the best of our knowledge, it's one of the first papers where power laws were observed and used to predict performance of deep nets. More generally, later, I mean, papers started coming up and studying scaling, like 2017 paper by Joel Hesnes and others. And they showed in that paper how the performance scales with amount of data. So essentially, they showed the power law, especially in particular regime, in the particular range of the training for just the data being x-axis. And they also showed that in general curve can be like more expanded than just power law. Power law is a middle regime when you're actually effectively learning. But before it starts, there may be very slow learning due to insufficient data, like on the left, small data regime. And then eventually, when your system learns pretty much everything it can possibly learn about the data, and you hit what's called irreducible entropy, or in classification world, it was called Bayes risk, then the performance asymptotes at certain irreducible error, and that's kind of the third regime. You will see similar type of curves that combine regimes with power law in between in a few minutes. Then there were other papers following up on this work. There was this paper by Jonathan Rosenfeld and his colleagues. And essentially what they did, they applied the power law functional form to, in this case, not the data, but model size dependent scaling. So there were all these bits and pieces. And then Jared Kaplan's paper essentially added on top of those kind of observations that the power law also applies to compute as x-axis. And then the three plots that you've seen were compute, data, and model. But then the interesting things started happening, which went beyond power law behavior. And that's what people initially were struggling to kind of model and explain. This is another kind of famous plot from the original GPT-3 paper, where on particular task, arithmetic, as turns out this type of the discrete operation tasks often leading to this quote-unquote emergent behaviors or quote-unquote phase transitions. You see that when the model size, basically the GPT model, was increased, initially it couldn't improve performance on this specific arithmetic task. At some model size, suddenly performance improves and the slope of the improvement changes drastically. So the system kind of starts getting or grokking the problem. And then people observe this type of grokking behavior in other settings. So here it's more, that was paper actually called grokking, also from OpenAI. And essentially they observed behavior in setting where model and data were not changing, but the amount of compute spent was changing. And while they just kept running this training forever, suddenly the accuracy went from practically 0 to practically 1 on training data first, the red curve, and then green curve on the test data, and so on and so forth. And there was this paper last year about emergent abilities of large language models, showing many, many, many more examples of this type of quote-unquote emergent behavior, or essentially behavior that wasn't there at lower scale, say in terms of number of model parameters, and then suddenly would take off sharply at some point. And that raises a question: you probably would be interested in predicting such takeoff points, especially if the y-axis is not just the performance of the system, but some other properties that you might be even more interested in, like robustness of the model, truthfulness in language models, or other behaviors of interest. So in order to kind of incorporate these different behaviors, we were trying to see what kind of functional form can capture all of them. And it's mainly work of one of my students, Ethan Caballero, and also Kshitish Gupta, and me and David Kruger were kind of co-supervising this work. But primarily, yeah, it's really kind of Ethan's brainchild, because he was searching for kind of universal type of functional form that could capture all of this scaling behavior for quite a while. And essentially, the motivation was like, okay, we want to predict those properties because we want to know what type of approach will kind of get us to AGI first. And there are, of course, multiple approaches, but the one that gets there first will be the one that matters because people will adopt it later. So in a sense, there might be some more sophisticated approaches, but if you get there with purely more compute and scaling more generic models, that's what will kind of persist. And it's critical, again, as I said, to be able to predict how various performance metrics will change when you change certain variables that are your bottlenecks, for example, amount of compute or model size or data size. And those y-axis are not just metrics of performance like classification accuracy or whatever metrics people use, say, in natural language problems, but they're also, more importantly, metrics of alignment, where by alignment, yeah, it's not a precise definition, I agree, but we mean certain correspondence between models' behavior and what people would expect from that model that would be aligned with our values. So you can kind of talk about that. That's going to be a separate long conversation, but even as I mentioned, robustness and truthfulness and other things are important. So what kind of things can be the bottleneck or the x-axis? And we already mentioned that it could be essentially data set size, model size, compute, whatever is being scaled, that is x-axis. And what is y-axis? Performance evaluation metric. It could be accuracy, well, prediction error, it could be the cross-entropy loss, it could be the blue score, it could be reward and reinforcement learning, it could be all kind of other ratings that people were using in the recent literature. And the setting in which we can evaluate it could be upstream, or essentially like the data you train on and you set aside validation data and measure loss on that, or it could be downstream, that you basically use some totally new tasks on which you evaluate the model. It could be zero shot, it could be end shot, it could be fine-tuned, it could be prompted or not. So there are all these different settings. And as I said, again, to repeat, the methods that perform best at small scale may not necessarily be best performing at large scale. So we do want to see their scaling performance, and it might not be necessarily trivial single power law. So basically the question remains, right? What can be used to characterize this relationship between the quantity being scaled on x-axis and quantity that we're concerned about, y-axis? So this functional form called, well, essentially broken power laws, it was used previously in other sciences and, for example, in astrophysics, and people realized that it's quite flexible form that was able to describe various phenomena quite accurately. And it looks a bit kind of scary here, but essentially it is a generalization of simple power law. And it might be easier just to look at how this type of functional forms would look in the plots. This is just an example showing a specific combination of parameters in that broken power law kind of functional form. It's called broken power law because essentially you see that some hypothetical performance here is described by segments of different behavior, just like in a sense, the low data regime where the learning is slow, followed by sudden transition to much faster kind of learning. And it potentially can be even non-monotonic. Things can actually get worse instead of getting better, and then they can get better again. The break between the power laws in this picture can be very soft and kind of or very sharp. It's all controlled by parameters of the functional form. So that gives you idea why it's called broken neural scaling law or broken power law, because it's combination of segments that are smoothly connected, combination of power law segments that are smoothly connected, basically. I don't know how much time I have, and I probably shouldn't go into all details. You're more than welcome to read the paper. It was just accepted to the CLEAR conference and will be presented, I guess, later this spring. The intuitive understanding of different parameters of this form is given there. And essentially, as I said, they control, like, for example, parameter n here controls the number of breaks, how many segments you're going to see there, right? And the parameter f there controls the sharpness of those breaks, and so on and so forth. So basically, I will not go over all the details, but each parameter here has an intuitive kind of meaning that shapes the performance curve. And what was quite mind-boggling and impressive was empirical results showing how wide this form applies to practically all recent papers showing scaling with respect to either model, data, or compute. And in all possible settings that you can think of, as I mentioned, downstream, upstream, different modalities like vision, language, audio, video, models like diffusion, generative modeling, and like the list goes on. And essentially, I think Ethan keeps kind of considering requests for modeling the behavior of whatever model in whatever setting, and essentially keeps fitting those kind of results into the broken neural scaling laws. And what's most important, it's not just curve fitting. We're testing how well prediction will go if you use this functional form of all these different behaviors, modalities, architectures, and so on. And essentially, yeah, as I mentioned, there are different architectures used here, not just transformers, there are MLP mixers and residual networks and images and text and so on and so forth. So what do we see? Well, first of all, we compare with previously proposed functional forms because besides the power law, people tried a bit more sophisticated forms like M3 and M4 literally last year. And it turns out that the model we proposed, the broken power law, is consistently outperforming in terms of predictive accuracy or extrapolation accuracy all these functional forms on a huge amount of empirical results that we just took from other people's papers and just compared how well we can fit its performance using those methods versus the proposed one. This is just one example. You will see a very long table in the paper containing all those results, and they're all consistently showing that this functional form seem to really get the scaling in all kind of domains and settings. And just to show a few examples, because I mean, the number of examples grows as we speak and being added to the appendix. The black points in those pictures will show the points that we measure, like, for example, in GPT-3 paper, you can go to appendix and see for all 8 models that they tried, how those performed on different tasks. And you can basically take those data, leave aside, say, a last point or a few, and try to predict them by this curve. So the black points are observed ones, given ones, and green will be held out points used for evaluation of how this form predicts or extrapolates. And yeah, the red line will be what is fit to those black points. So basically, here, what you see black points for particular setting. This is training data set size and test error rate on the y-axis. And this is particular example of the setting that's used there just to give you the idea. The black points are measured performance. Red line is a fitted functional form. And then you see all these green points that are never seen by our model and are very accurately predicted or extrapolated by it in the future. So this is keeps happening for, as I said, so many different settings, for reinforcement learning, for single agent and multi-agent, for diffusion generative models. So here you see a green point, or maybe it's hard to see, it's on the far right, the green point being extrapolated to after fitting. Then you see basically the video models, so generative models of video. As I said, you might not see on the screen, but there are always green points at the end of the spectrum on x-axis. Those are the points that the model predicts. So that's most important kind of thing, because sometimes people get confused and say, well, maybe this functional form can fit anything. It doesn't just fit, it extrapolates. And that is quite kind of important to understand and kind of see that it can be used for the extrapolation or prediction of behavior. There are many language tasks, like downstream language tasks. There are even metrics in Anthropic's papers using RLHF, alignment metrics, same story. The behavior is being predicted quite well. And even the results from that paper on the continual learning and catastrophic forgetting. So the list goes on, and I probably just invite people to look at the paper and the appendix if they're interested. But robotics, out of distribution generalization there, the multimodal learning, contrastive learning, all these different papers, even for uncertainty estimation, calibration, and there are some experiments with molecules, data sets, and so on. So it's really seemed to be like modalities like audio, even for kind of robustness metrics. I mean, it seems to be doing the same thing. It's kind of accurately predicts those green points. And it does it not just for language, not just for audio video, it's also for programming, when you essentially use your large scale models to do coding, for mass word problems, for sparse problems as well, sparse models as well, not just like the classical transformers. And sparse models are quite popular recently because they promise to be much more computationally efficient and inference efficient. They will be much smaller, and ideally maybe we can all use those models eventually on edge devices. So on and so forth. We have a bunch of those plots which all show the same pattern, that this functional form can extrapolate well, and not just those relatively, maybe you could say, simple example, non-monotonic behavior like double descent or multiple descent. It also captures that, like in this picture, you have a bunch of green points being predicted accurately for non-monotonic scaling. And those most kind of startling phase transitions or inflection points, the most important things, I would say, to predict when behavior changes drastically or emerges. They can be predicted too. There are limitations there. Limitations depend on how close you need to get to that transition and how many data points you will have and how sharp the transition is. So of course, there are limitations to any method, but it's good to know that it is possible. And with enough data points and maybe sufficiently close, you can handle prediction of those transitions in completely like a closed box way. You don't really have any other measurements about the behavior of the system, just observation of its performance. Okay, so bottom line of all that is that so far we see that perhaps a bitter lesson of Rich Sutton was quite relevant, that, yeah, so the methods that can scale well and whose performance we can predict will be probably the ones which will matter kind of later on, and which will kind of persist then stand the test of time. But yeah, what does it mean for people who want to train such models besides just predicting their performance? And quoting Greg Brockman, the most benefits will go to whoever has the biggest computer. And until recently, the biggest compute was in industry, like OpenAI and Microsoft and Google and Deepmind. And academia was really falling behind because of the compute gap. So the idea was that perhaps we can somehow, by joining forces with open source communities, try to democratize AI and try to get large compute. And just one example and one idea was to see whether we jointly can apply for high performance computing, such as government-funded supercomputers, for example, in United States, Summit, and more recently, Frontier. Summit has like 26.7 thousand GPUs, and Frontier has 40,000 GPUs. Even though we might not catch up exactly with industry in terms of number of GPUs, it's sufficiently large compute that none of the academia or open source communities had before. So we joined forces with some of them, and we keep kind of making more connections, primarily collaborating with Lion and Jülich Supercomputer Center, with NeuroAI and with others. And Lion, for those of you who do not know, is based in Europe. It's kind of was started in Germany, but now it's essentially an online international organization that as many other kind of open source communities that started recently, has the goal of essentially democratizing AI, training large-scale models, like they recently trained several versions of Clip, and they outperformed the original Clip from OpenAI, and also providing data sets like the Lion 5 billion points data set with images and text, and essentially making it fully available for research in kind of academia, open source, or for pretty much anyone. And last summer, we applied jointly for this so-called Insight program at the Summit supercomputing facility. And essentially, that was about training large-scale language and multimodal models on this large compute and making them available to basically the AI field. The proposal was accepted, so we got close to 6 million V100 GPU hours to train language models, some multimodal language vision models, as well as what we called, well, more generally, aligned ChatX. So it's an interactive training of multimodal models. Currently it's Magma, but doesn't have to be, using human feedback, even not necessarily with reinforcement learning, but just for fine-tuning. And that is considerably improving performance of system in terms of generating what people would consider more ethical. In terms of scalability, we did our tests. Of course, we saw whether we can scale effectively on this compute, and the results are promising. And essentially, to kind of conclude, because I think I'm probably getting very close to the end of the hour already, what are we trying to achieve with all this AI democratization efforts? We're essentially trying to build what probably could be seen as LHC of AI field. LHC, like Large Hadron Collider collaboration, was an example in physics how joining forces across multiple, say, academic organization and obtaining large-scale compute allowed physicists to really study, like in high-energy physics, process the data from this accelerators. Well, the largest and fastest is currently in CERN, and it's only a very large-scale kind of collaboration could afford to do this type of research. And it seems like if we want to democratize AI, we might need to follow that example. So if we keep going in that direction, we hopefully can build those open foundation models. There is already, say, GPT-Neo, 20 billion from Illuter. There are larger models being trained. We're also training some suites of models on Summit, as I mentioned. And essentially, yeah, they can be basis for many, many applications on top, just like right now people are building on top of GPT and ChatGPT and those. But those models will be fully open, like, well, Stable Diffusion, for example, that was trained on Stability compute. That's kind of another alternative, either government funded or private funded. But there are many supercomputers in different countries, and there are not yet as many companies like Stability that would be specifically focusing on providing compute for open source communities. And essentially, we want to keep trying to apply for larger resources like that and keep growing this collaboration. So essentially, the LHC of AI will be kind of moving faster and making those large-scale models available for all. So that's kind of our current vision. And yeah, that was extra slide. Thank you so much, and I'm open to any questions if you have still time left. Thank you.
Thank you very much. Perfect timing. So now we have 10 minutes for questions. Who's going? Yeah, we have a question. Please talk to the microphone so that Irina can hear.
Okay, so thank you for your talk. My question is whether, or what other kinds of fittings have you considered apart from these scaling laws?
Sorry, I didn't quite hear. What was the
So
first part of?
apart from these broken scaling laws, what other functionals or what other functions have you tried to fit those those data points, I guess?
Okay, so basically there were 4 of them that I mentioned, right? Let me see. Let me go back. So there were, besides just plain vanilla power law, there were 2 more that were proposed in actually 2 papers in the last year, I think. Let me just get the proper slide. They were called here, these ones. So I don't know, can you see my?
You're not sharing now.
I'm not sharing?
No, but maybe you can just read them. And are you going to share the slides after the talk?
Yes, definitely.
Maybe that's if.
Also, I mean, the functional form, there are 4 kind of competitors to this one. They are also in the paper, but okay, so let me, okay. Can you see them now?
Yes.
Okay, so basically the plain vanilla kind of M2 is essentially the power law that people used, and the M3 and M4 were kind of more recent additions to the family of attempts of trying to model essentially scaling laws in the wider varieties, but none of them unfortunately could really model the non-monotonicity that I showed, like double descent, or inflection points. So essentially you have like sigmoid-like curve or kind of phase transition like looking. I'm not calling it phase transition per se, because sometimes it is, and sometimes I don't want to go into all the details proving that it satisfies definition of phase transition in physics. But you see sigmoid-like curve with inflection point, and the models M3 and M4 could not really capture well and predict well this type of curves. So that was kind of one of the major contributions of this functional form, that it could handle all these non-trivial behaviors well, whether it's non-monotonic and whether it is having inflection point. Yeah. So that's kind of the competing functional forms that we compared with. And to the best of our knowledge, there were like practically not too many other papers proposing something instead. And in a sense, we were kind of open to the challenge, like if anyone can propose alternative functional form that would have as many or less number of parameters, but would equally accurately capture and extrapolate, we would like to see that. So far, we just couldn't find any. And so far, we couldn't find any particular setting where we would not be able to predict behavior with like sufficient number of points. So that's why there was even kind of a post on Twitter, which was somewhat humorous as well, but the core question was quite serious. Like, it would be really interesting to see if anyone can come up with a better, more concise functional form that can do job just as well, or if anyone can provide example of the model setting and behavior that doesn't seem to be in any way being accurately predicted by this functional form. So if you have any examples of that or come up with those, please let us know. As I said, Ethan is essentially on ongoing basis adding more results to the appendix, asking people about different settings like robustness, like sparsity, and so on and so forth. And so far, nobody was able to provide example that he couldn't handle. So the competition is still open.
Hey, can I ask another question? For the cases where you are able to fit the like suddenly emergent properties, the things that look like phase transitions, can you just tell us more about how that, when does that work? When does that not work?
Yeah,
I imagine it mostly doesn't work, right? I mean, it seems impossible. And
no, it is possible, because imagine if that the actual true form of what's going on, right? So if you get sufficiently, I mean, basically you need to estimate the kind of the curvature of the that behavior. So you can predict transitions if you have sufficiently many samples from the curve and are sufficiently close, and transition is not, in a sense, too sharp. The precise characterization, right now it's empirical. I understand, and it would be great to have like more theoretical characterization of what sufficient means. But even in that case, we have another line of work. I didn't talk about it here yet because it's not on arXiv. Remember, this is completely closed box approach. But if it's your system, not somebody else, and you're training it, you can measure what's going on inside, and you can try to predict, for example, grokking behavior by looking at, say, trajectory of the training loss and the validation loss, and you can look at the dynamics of the weights and activations. There are several papers right now that are trying to study and predict when grokking happens. And as I said, we also have work on that. Well, to be kind of at higher level, what we observe, that there are certain interesting patterns of oscillation in the loss function, certain kind of spectral signature that can predict quite accurately whether in this particular run, grokking will happen. So you should be able to predict those phase transitions, not just using this type of closed box approach, but with open box, with looking at the inside of the neural net. I'm pretty sure you will be able to predict many of those behaviors. But again, it's not really yet theoretical study, it is more empirical, but it seems to be working quite often with those limitations, sufficiently close, sufficiently many points, not too sharp of a transition. I think adding those open box measurements like loss, oscillations, and particular dynamics in the weight changes, there are patterns that are predictive that transition is about to happen. And actually, it's well known in physics and in other fields like neuroscience. There are patterns of high frequency oscillation, say, preceding epilepsy, and some other kind of drastic changes in the state of the system. So we can really borrow from other fields on how people predict phase transitions there. Okay, but that would be, as I said, that would be expanding this with open box, not just closed box approach.
Hi, thanks for the talk. So I assume the parameters are set or fitted for each task or setting individually, but are you working on any models that would predict for multiple tasks or setting at once, depending on some features of the system or of the task?
Yeah, that would be, it's an interesting exercise if you can have same functional form that can simultaneously predict multiple settings. Yeah, so far not yet. So far, each particular setting and particular set of results required its own set of parameters. In a sense, I mean, that was the same thing with power laws in Jared's paper, right? I mean, for GPT, yeah, also depending what is on x-axis, you have a different slope of the curve. You have different parameters. So you may or may not be able to reuse exact same set of parameters for it's an interesting question, like what kind of settings can be described by exactly the same member of that family of broken power laws? Yeah, but we didn't yet try it.
I have a question. I have the power to take the turn now. It's related to that question, so that's why I wanted to just to tip in at this moment. I think some of the, probably you get better results when you have a smooth set of points, of course, depending on what kind of inflection points they have and all of that. But for instance, if you aggregate a lot of tasks, then you have smoother curves, and maybe they are more predictable than you just focus on a very single task with you don't have a lot of data, and then you have a lot of peaks. And these probably they are going to be confounding your model in terms to just that there are more peaks, more inflections that there. So in cases where, so the question is, how important is it to have a lot of tasks and whether a possible solution could be smoothing the points before applying the laws or something like that?
Well, yeah, I mean, indeed. Okay, so in the experiment where the transition was being predicted, that was, I think, our experiment with arithmetic tasks. So you could actually average the results over a very large number of initializations. So, and indeed, that's how you get those, that's how you get a very good estimate of the kind of average performance. And that's why I was saying that the quality of your prediction, of course, will depend on the amount of data points you're using for parameter estimation, right? Yeah, so, and the open question right now is, say you're training your system on large compute and you want to predict its performance. What's the most cost-efficient way to do that? Like, how many points do I need? How should I position them? Basically, so I minimize the amount of compute I use to make the most accurate prediction. So this is not yet in the paper, and that's something we're kind of looking into. Yeah, like statistically efficient methods for doing so, which are not just statistically, but also computationally efficient. Because you can ask the question, should I, in order to estimate whether there's going to be transition with increasing model size, should I train, I don't know, 2 more extremely large models, or maybe I train 10 more very small ones, and that will be enough. So those questions are still remain to be solved to have like very practical and efficient method that you can just like give people, and in whatever settings they know that if they use this approach, they will at the minimum of compute be able to predict maximally accurately what will happen with their system. Yeah, so that we still need to work on, and that's an interesting question. And I'm pretty sure there are various ways to do that, because I mean, you will need to balance several factors, right?
Thank you. Do we have another question? The last question, perhaps? Yeah, we have a question at the back. Maybe this can be the last question.
Hi. So does the fact that scaling laws are so universal in this domain tell us anything about how these models are working under the hood?
Yeah, that's exactly the question regarding open box and closed box. So what I described today is completely closed box, because essentially we were looking most of the time not on even our own system being trained by other people's results from different papers. And essentially we had no information about what was learning dynamics and how loss and weights were changing. So that's why I said, I mean, like just by looking at that, it's hard to tell what exactly is going on within the system. Although if we keep studying the correspondence between patterns in the loss kind of trajectory and in the weight space, and with grokking, people are kind of looking into that. We are looking into that. There are several recent works from MIT, from Max Tegmark's group and his students, and also from Jacob Steinhardt's group. There is a recent iClear paper also looking into grokking specific example and trying to see what patterns there in neural net internals kind of relevant to this behavior. So your question was rather, if we use this functional form, what can we say what's going on within neural network, and can we do any kind of interpretability without even taking any measurements? Well, that's a bit tough. It might be possible if we study well predicting those transitions when looking into neural net kind of measurements. And once we understand that if there are certain patterns that are kind of always there when transition happens, then perhaps if broken neural scaling laws will be predicting transition, we can say that, I don't know, I don't see your network, but I can tell you probably those patterns appearing. So it's a tougher question than probably vice versa. I see what's going on in the neural network, because it's my model and I'm running it. And those patterns like that, the work with Guillaume Dumas and one of my students that we hope to put on archive like anytime, you look at the pattern of, say, the spectral pattern of the loss, and you can pretty much say if this run gonna grok or not. The paper was called To Grok or Not to Grok. But again, it reminds me that we really should put it on archive like yesterday. So in this direction, it's easier to have access to internal measurements and learn how to predict upcoming changes. Doing it the other way around, like looking from outside and saying that if the curve seems to be getting close to some takeoff, I bet I know what's going on with the system. It might be possible to an extent, but again, it will require lots of studies of this correspondence between patterns of loss, weights, and whatever statistics of internal parameters you can measure, whatever is relevant to those transitions, how deterministically it is related, and so on and so forth. And if we have such studies, because right now groking is only studied with respect to compute. There is not much in respect to model size and data size. Well, perhaps people are working on that, but we definitely should work on that. If we have good understanding of these correspondences of internal patterns and external behavior, then it will be easier to say just how well we can predict those. And whether we know for sure that change in the behavior of certain shape of the curve means certain changes in network kind of internal behavior. Yeah. But we really need to kind of study much more these correspondences. So all you saw right now is, yeah, empirical. And yeah, and there is not much even done with model and data transitions, only with compute transitions, like the specific example of groking. And all those papers I mentioned are mainly considering kind of toyish example that the original groking paper was kind of considering. Yeah, so a lot of work needs to be done here. That's pretty much the conclusion.
Thank you very much, Irina, and especially because of the time there in Montreal. So it's been a pleasure. It's been a great talk. So let's thank the speaker. Thank you very much.
Thank you.
Okay, so you were waiting for this moment. Coffee break. We are back 10:45 as planned.
para cargar algo? No, vale, vale. No.
¿Dónde están las pilas? Mutealo, mutealo. Sergio, mutealos.
hablar de...
¿Vale?
Venga, estupendo, gracias.
Gracias.
Okay. Yeah. So cool. Thanks everyone, and welcome to the second session of invited speakers. Just a clarification. After this session, we have the lightning talks. It is not here. There are some errors here, so the most up-to-date agenda is in the website. So sorry for that. So, well, my name is Nando. I'll be chairing this session for you. And let's start with the first speaker. So it's a great pleasure for me to introduce our first speaker today, former colleague Emilia Gómez, who is going to talk to us about liability regimes in the age of AI. So Emilia is guest professor at the Universitat Pompeu Fabra and senior researcher at the Joint Research Center at the European Commission, where she leads a couple of important relevant projects. The Humane one, which is, well, studies the impact of AI on human behavior, and she also co-leads the AI Watch initiative that monitors the advancements, uptake, and impact of AI in Europe. So, yeah, impressive CV. The floor is yours, Emilia.
Okay, hello everyone. Yeah, I'm very happy to be here. I see the room with so many people. I'm very envious I cannot be physically in Valencia. Thanks a lot for the invitation. Yes, and for the introduction as well. I'm trying to share my slide. I hope you can see them well now. And yeah, I wanted to, I was following the previous keynote. It was an amazing talk by Professor Irina, Rish, and on the challenges we are addressing, and I wanted to focus my presentation more on the work that we carried out. I work, as Nando mentioned, at the European Commission, and this is part of the work that we have been doing on the topic of liability. It's an interdisciplinary work that combines a bit knowledge from legal or colleagues that are in law and regulation, and then also some people that work in the technical field, and this is about to be published at the Journal of Artificial Intelligence Research. And I wanted to talk a little bit more about the legal challenges that current AI systems pose in particular for liability. So a very, very brief introduction to why we are doing this work. I mean, of course, we have seen also in the last talk, and I will try to mention some properties that artificial intelligence system nowadays have for related to risks, to safety and fundamental rights. And we can, on the one hand, have some ways to mitigate and assess those risks in the development stage. For instance, when we are trying to train a model or deploy it in a real-world scenario. But in any case, the risks still stay in a marginal level, so harm can occur. So in case there's harm produced by a system that is incorporating AI, victims should also be able to seek compensation. And the same properties that make difficult to prove causality also make difficult to prove this compensation. So this was the motivation for us to carry out this work, where we try to really identify a series of case studies on harm produced by AI systems, and study which are the technical difficulties that people or victims may have in proving causation. This is called the burden of proof in legal terms. And this is also relates to the way that we need to alleviate this burden of proof for victims. And we focus here on systems, AI systems that can really make some harm to properties or physical harm, and also to recent developments on AI available, for instance, in the market in the short term as well. So this was mainly the goal of this study, and the context, as Nando mentioned, I'm leading a project, a team of people that is the human team. We are interdisciplinary. We have people from cognitive science and also from law and also from machine learning. we are trying to understand the impact of artificial intelligence on society, and then trying to define methodologies for what we call trustworthy AI, which is the term that was defined by the high-level expert group on systems that can be trusted, then focusing, for instance, on fairness, transparency, and or robustness, for instance. And as part of the commission, we collaborate with our colleagues that define policies such as regulations or investment policies to base them on scientific grounds. So the topics we are working are very related to the work I will present today. For instance, we have some work on recommended systems, for instance, used in different contexts, for instance, from music to news. We also have some work on facial processing, and biometrics, which is also a very sensitive topic from the policy perspective. We also have a project on children's rights and AI, and how AI will affect children in their development process. And also, we have also a project on the autonomous driving and trustworthy autonomous driving. And these are a bit the policies we have been supporting in this, where I will focus on AI liability, which is a policy file that I will provide some more details later. So as you may know, the Commission proposed a regulation on artificial intelligence that is called the Artificial Intelligence Act, which really applies to software products, AI. And this is the kind of assessment that I mentioned before on the risks of systems before putting the system into the market. So the idea of this regulation is that the regulation defines different levels of risks. For instance, some applications are considered like unacceptable, so they are prohibited. Some others applications are considered high risk, and in this sense, they should be subject to compliance with certain requirements, for instance, transparency, data governance, or human oversight before they are put into the market. Then there are other systems that are considered to have transparency risk, and they are also subject to lighter requirements such as transparency and information to users. And then there are other systems which are considered to be used in a context with minimal or no risk. So this is the approach that the European Commission has taken to regulate the technology, not the technology per se, but also depending on the context where it will be used. So in any case, if we have this risk assessment level before we deploy a system, and then we try to comply with series of requirements, for instance, the system should fulfill certain predictions, should fulfill certain robustness requirement, there's always mistakes or errors that can occur. So this is the focus of our work, how to obtain compensation for damages that might be produced by AI systems. So just to introduce you a bit to the concept that we are, or the legal framework that we are considering, there are three mainly frameworks for liability. One is what we call fault-based liability, where victims or injured parties have to prove that the defendant caused the damage intentionally or negligently. So this means that there was a standard of care that the defendant, for instance, the developer of the AI system, should have fulfilled. And then the injured parties or the victim should really prove that this standard of care was not fulfilled. And they have to prove, for instance, there was a negligent design, manufacturing, maintenance, marketing, or operation. So this is the first legal concept based on what we call standard of care. The second one is what we call strict-based liability, which in fact the injured party doesn't need to prove that there was a damage, and the defendant caused the damage. That they only need to prove that there was a risk and the risk materialized. So in fact, if there is a risk assessment, we can see which were the risks, and then in a strict-based liability, you only need to prove that this risk materialized. I will give some practical examples later. And then the latest one is the third concept is product-based liability, where the victims can only claim for a defect that was present at the time that the product was placed into the market. This is called the standard of safety. So only you can claim that the product, when it was put into the market, it was badly designed or manufactured. So these are the concepts that I will use during my presentation. So there is a lot of literature, or not a lot, but few literature that has trying to address this in the context of artificial intelligence. For instance, you see, I am citing here recent studies where, for instance, we consider that AI systems, they lack of a legal personality. So, of course, there was the conception that the person operating the AI system, for instance, the person that is using the system and supervising it, will be the person responsible. And this is what we mentioned when we talk about human supervised or assisted, computer assisted paradigms. But this is really challenging when AI becomes more autonomous, because people might not be able to be aware of how to supervise those systems. So the responsibility can, of course, should be shared between the person maybe operating the tool, but also to other system persons or organization. So we are moving a bit in the literature between the standard of care, fault-based liability, as I described below, to the standard of safety, strict liability. And this is very complex in AI because there is a value change is usually also very complex. For instance, if you see a product, and we will see an example, there are always different components, and different components are developed by different organizations. So the harms should be, and responsibility should be then distributed in this change. So in our work, we identified several characteristics of AI systems, and we try to see which of them are really exclusive of AI and machine learning, and then which are non-exclusive. They also found in other, like for instance, automated systems. And then we also try to see what will be the impact on proving causation, and then the impact on this idea of the burden of proof. So here we did, of course, a qualitative assessment of the relevance, and I will focus on these 4 that we identify as the most relevant for our work, and also very or more exclusive on artificial intelligence. Here, I may have to claim that, of course, artificial intelligence is a very broad field. So we were focusing here on recent developments mostly in machine learning systems. So, for instance, the lack of causality has been discussed a lot in literature, also mentioned here. That is the main difference between statistical associations versus causation. And this is due, of course, to the assumption on the independency and identically distribution in machine learning. And this causes a poor performance of models, for instance, when there is the difference between the statistical distribution in real-world operation versus the statistical distribution in training. And this can be exploited, for instance, it is exploited by adversarial attack. So, of course, despite their recent research advancements, learning causal relationship is still very challenging in the field. So this is one of the relevant characteristics that we identify that will challenge in the context of liability. The second one we identify is, of course, opacity, and this is defined as the obscurity of meaning resistant to interpretation, and is, of course, the well-known black box character of the decision-making process in machine learning, and also the inability to provide human-scale reasoning for complex models. And, of course, the AI Act that is explained below tried to alleviate this by defining transparency requirement. In systems, for instance, there is a need to provide technical documentation or explain the architecture that was used and provide access to logs to alleviate this idea of the burden of proof, but there is still a challenge, and attempts to explain black box machine learning models might not be still enough to demonstrate causality. The third feature that we analyzed in our work, and we think are relevant for the liability, are unpredictability that can be due on the one hand of the fact that the data set that was used for training might not be sufficiently. So, for instance, you see one example here on the left for one dimension. You have the learn function is this one, and then you have the underlying function. So when we have in fact the data set is not sufficiently covering several parts of the space, there might be solutions in these poorly represented regions that might generate unpredictable results. And then I put also here at the right the example of overfitting, but even if the input space is well represented, the outcome for samples not used in the training can be unpredictable. This is also found, for instance, in recurrent models where the outputs might depend also on the input, but also on the state. And this is also a source of unpredictability. So this is the third characteristic we identify as relevant for liability purpose. And the fourth one is, of course, self and continuous learning. We consider, for instance, relevant those systems that carried out incremental training of the system during the operation phase. And as you see here, we put that the impact on proving causation might be low because we may consider that those systems might not be deployed in a context where there is a safety requirement. So we also see those systems might be maybe not used in the context, for instance, of physical harm, and then there will be a control scenario for this kind of continuous learning. In this concept, there's also the legal concept of substantial modification. That means when you have a system or a product and you carry out a substantial modification, you need to assess again conformity with the requirements, for instance, in the AI Act. And this is to be defined in the context of AI system. When do we consider the system is really substantially different from the one that was deployed before? Because of course, in AI, we always update systems and their behavior. So in a study, when we identified these requirements, we tried to build together with our colleagues from DigiJazz a set of use cases where there will be related harm. And this is the criteria that we use. For instance, we consider on the left side, you have the technology. We consider system with a technology readiness levels from 5 to 7. So systems that can be actually be expected in the short term. So we consider the state of the art, not only in products that are already available in the market, but that might be available in the short term. We try to consider in our use cases those specific AI features that I described earlier in my talk. And this was the first criteria that we have. Then in the second criteria that you see here in the center of the slide, we consider, of course, the product and fault-based liability. So what will be the need to prove the harm and where the harm comes from? Then we also consider also different victim AI provider relationships, and also that there was no insurance covering, for instance, for harm that might be then not needed to prove the harm. And finally, we also try to focus on use cases where there are different types of harms. For instance, we can consider physical harms to a person, or property harms, which are material harm. And we also consider some use cases with recognized mental harm, and which is also one of our use cases. And of course, that this harm is significant and relevant. So this is a little bit, of course, the methodology for our interdisciplinary study. We gather experts from the legal side, also from the computer side, and also for the human-computer interaction side, and we try to build our use cases realistic enough to have a detailed description. So I just wanted to go now through one example of one use case without entering into details. For instance, this is the methodology that we follow and the different steps that we follow for that, and I will explain it with an example. I think one of the use cases was an autonomous urban cleaning robot that I mean, you can find here some pictures or the current state of the art of this kind of technology, which is a cleaning robot that deployed in an urban by a municipality, and then there is maybe a use case that we can expect now or in the short term. So just to give you some examples of the kind of analysis that we carried out. For instance, we first analyzed the characteristics of the product, the different features and the different components, for instance, from the sensors to the actuators. And then we try to analyze the different AI or machine learning systems from perception to planning. So we try to, of course, analyze a bit in this context the complexity of the value change and also the amount of systems that we can find on the real product. And we also discussed a bit about the role of the human operator, if it's more in this case it was more supervisory role, and who are the different people behind the product and the operation. This was the first steps. You can find, of course, in the paper more details about all the analysis that we carried out. In the second step, we tried to define the potential event leading to damage. In this case, for the use case, we defined this event like there was a colorful baby stroller parked in front of an advertising banner with similar color patterns, and then there was a baby guardian looking after the baby, and he was looking at another side, and then one of the cleaning robots just collides with the stroller, and then the stroller is damaged and the baby is slightly injured. So this is an example maybe of an event leading to damage. All of this work was carried out like discussing with people also from the legal context to see if this might also be relevant for legally or also for obtaining compensation. And then we say, okay, let's imagine this such as an event occur and such an accident occur, and then how can we, or an expert, how can an expert know what is the potential causes, and also how can we prove how this accident happens. So then we started to look at the potential causes, for instance, for an accident, like which component could fail and why. So then, for instance, this is an example I put here. Maybe it's the perception module that did the wrong image segmentation, or maybe it's the decision-making and control of wrong reaction time, or the sensors. We try to analyze different reasons. And then, of course, we identified two potential causes. One were more like due to an error of the system, for instance, mislabeling in training, or maybe a noise or some noise in the image or in the input. I'm focusing here on perception, or maybe some unfavorable weather conditions for some control system. And the second one is, of course, deliberate attacks, exploiting the system vulnerability. So these were the two potential causes that we analyzed. And after that, we tried to say, okay, but according to the source of the potential cause of the accident, who would be the potential liable parties? And then we started to analyze different scenarios. For instance, if the reason for the error is due to a single component or several components. So this reflects a bit the complexity of the value chain, and also the idea of the robot manufacturer. I mean, in this case, for instance, can be the manufacturer of the full product, the provider of the different components, the people that deploy the system, the user, such as the municipality that put it in the city, or also the adversaries attacking the system that might be able to cause harm. So this is the analysis we carried out from these different use cases. And finally, and more importantly, we said, okay, how experts should assess really the cause of the accident. So we try to discuss on different potential causes to establish what we call prima facie evidence on the fact. And then, of course, even if the correlation was proved between an input and output, or between we cannot discard alternative sources of the damage. So this proved a little bit the difficulties to infer a clear causal link from the input to the harmful output. And we also analyzed in this work what information might the expert need for this assessment, including logs or technical documentation, which kind of information or access to the system. So this is an example of the work that we carried out for this study. We all gathered other use cases. For instance, we have one similar use case, which is autonomous delivery drones. We have another use case with robots and education, where we address as well the psychological harm of AI systems. And then we try to build this analysis and technical assessment. And of course, the result of our work highlighted the technical difficulties that experts or an expert opinion will face when trying to prove the effect or negligence and the causal link to damage. And these support a bit our assumptions that liability regimes which are based on proving causation should be revised to alleviate the burden of proof on victims in case involving AI system. So this work was part of the evidence gathering of a legislation that was proposed by the European Commission. It's called the AI Liability Directive, and it's part of the package that the Commission is proposing on artificial intelligence, which is composed by the AI Act, this directive, and also the revision of the product safety rules. And the idea of this directive is to harmonize different national liability claims in member states, which are based on the fault of any person with a view of compensating any type of damage. So in light of course, this analysis, but also complementary analysis, because this directive also carried out other analysis, for instance, on the economic impact, also on technical feasibility. But so this was only one source of evidence, of course. And there was some measures that have been taken to ease the burden of proof. For instance, in Article 3 of the directive, there is the idea that we need to, or providers need to disclose evidence of AI assistance in particular in the high risk scenario defined by the AI Act. For instance, they have to provide access to technical documentation and logs so that victims may be able to assess and carry out the burden of proof. And there's also the rebuttable presumption of causal link. So by default, it's presumed there is a causal link in the case of fault, and this is in Article 4 of the directive. And these two measures are complemented by a review mechanisms to reassess the need for harmonizing strict liability, which is then do not require the proving of harm for AI, in particular risk profiles. And this is, of course, a directive that is being proposed and still now in negotiation phase. But so, as you know, in the Commission, in European law, we have always the negotiation with the Parliament and also with the Council, so it might also have some modification. So this is a little bit, I think I am almost on time, the work I wanted to present here to this workshop, which is leading with so important aspects of AI, which are, in my case, are more linked to the legal aspects and trying to see how we can combine knowledge from computer science, from machine learning, and also from legal research on these kind of topics that should be broader and interdisciplinary more and more. And this is a bit all from my side. Thanks a lot for your time, and happy to answer any question now, or if you want to contact me later for anything else. Thanks a lot.
Thank you, Emilia. Okay, great. So time for questions. Any question from the audience? Don't be shy. Okay, yeah. Yeah, okay, yeah, for sure. Yeah.
Thanks, Emilia, for the great talk, and sorry that my mic wasn't working. So my question is about the relation, one of these four aspects that you mentioned, the relation between predictability and causality. Can you actually prove causality you cannot predict, or how do you see this relation between these two things?
Yeah, as I say, this is one of the main challenges, I would say, for that of the topics that we identify. I mean, this is clearly a challenge, as you say, about the idea of predictability and also the idea of causality. These are very challenging for the purpose of liability. Of course, we all consider that in this kind of safety relevant scenario, for instance, when you deploy a system in a context, that's why I say we need to put safeguards. No, so for instance, if you deploy a system that can cause harm, there might be always filters around, there might be always supervision around, but these are maybe some of the intrinsic characteristics that we cannot control at the end. So this might be needed to be considered, for instance, by developers when developing a system in the context where it will be deployed. So I think Jose, is more about those intrinsic properties that will difficult or will challenge the proof of causation. And this was one of the aspects that we identified.
Okay, thank you. Any more questions? Yeah, over there. Pablo? No. It's the same. Maybe you can. Came here.
Sorry. Thank you, Emilia, for the talk. So I was wondering, in the examples you've given, they are rather limited systems, AI systems, but when we increase the generality of systems and when they interact in a much complex environment, it's even hard to define it's even hard to know what specific objective is the system optimizing for, because it might not be possible to hand-define exactly what we care about. So in this sense, how are we going to, or have you thought about how we are going to evaluate what the system is trying to accomplish? Or
Yeah, this is a very, very nice question, very relevant. Thanks a lot. I mean, the problem is that as far as we go to more general purpose AI, and this was also discussed earlier, for instance, if you have a system that will be used in a context for a concrete task in a scenario, for instance, you know the kind of images you will get or the kind of audio, then it's easier to evaluate and control. But if you have, of course, general purpose AI or more multitask systems, you may need to assess when and how it could be used. So I think the evaluation should be different. But we cannot say, okay, but it's general purpose, so we cannot ensure the accuracy or robustness in all the setups. So we need to decide in each particular context which kind of system do we want to use and how do we need to evaluate it. And this is a bit complex. For instance, if you are going to use a general purpose system and then you are going to incorporate it into a product, how can you, for instance, as a developer, evaluate it if you didn't train it? And this is an ongoing discussion, I think, about general purpose AI evaluation and the share of responsibilities between the person that just develops it and the person that uses it in a particular scenario. So my feeling is that general purpose AI have more broader, it's general in terms of risks, it's general also in terms of evaluation needs. So you may need to, as well as you do a more general system, and you should do also more general evaluation. So the smarter the system, the smarter the evaluation. And I guess maybe our community is spending a lot of effort into deployment and developing models, but not into evaluating them. And this is a bit, I think, unbalanced between the need to get more performant algorithms and the need to get more performance control mechanisms. And this, I feel this is a balance because many people work on developing models, not many people work in evaluating models and assessing the limits. This is a very nice discussion, so I don't want to talk alone. Yeah, but very good. Thanks.
Yeah, thank you, Emilia. I don't think we have time for more questions, so let's thank the speaker again.
Yeah, thanks a lot.
Okay, so for the second talk, we had two speakers for the price of one, real bargain. It's a great pleasure for me to introduce Seán O'Herty, Executive Director of the Center for the Study of Existential Risk, the CISA, the University of Cambridge, which is a leading research center on global risk and emerging technologies, and Seán's research is focused on technological trajectories and impacts of AI and other emerging technologies. We also have with us Alex Marcoci, I guess I'm pronouncing it good, research associate at CISA Center, also working on collective decision-making, augmentation, and foresight. And they talk today discusses the predictability of the future of AI. So the floor is yours.
Thank you very much. Is the mic working, or should I speak into this? Oh. Ah, excellent. Wonderful. My name is Seán Hegarty. I'm coming from the University of Cambridge. We have a group there who are working on futures, governance, and risk relating to artificial intelligence. And it's a real pleasure to be here today to talk about, well, how predictable can we make AI systems, but also, can we say anything meaningful about progress in AI and the future of AI? What we're going to be talking about today is the very beginning of a study on the role of foresight and forecasting in AI. So I hope you'll forgive us if it's a little bit loose. We're hoping to provide a few thoughts and have a starting point for conversations that we hope to be having over the course of the day. Progress in AI, as everyone in this room knows, is happening really quickly, and advances in AI are being felt right the way through a range of industries, from the impact of large language models on translation, coding, speech-to-text, graphic art, much more. All of us in universities are trying to figure out what we do about essays generated by ChatGPT. So there's an interest in having more accurate predictions for when certain capabilities might become available and what impact they might have on the world. So what kind of things might we want to forecast? And I've grabbed a few of the questions that are being currently or have recently been discussed on the Metaculus platform. And I think we're lucky to have somebody working with Metaculus here with us today who'll join us later. We might want to know when particular milestones or thresholds in research might be achieved, like when an AI system might surpass human performance of visual question answering on the VQAM 2.0 dataset, or when an AI system might be able to outperform professional game testers on all Atari games without game-specific knowledge. We might want to forecast capabilities that could be dual use or introduce new kinds of risks. So if we're able to generate realistic videos, then suddenly we can create fake videos of, for example, politicians saying things that they didn't actually say. We might want to think about when AI systems could engage in deceptive behaviors when interacting with human beings. And we might want to predict when will people actually start using these systems for malicious purposes. And we had a wonderful talk this morning from Irina on sort of trend extrapolation. We might want to predict, well, how long will scaling laws hold? What kind of energy usage might we see going forward? Will we continue to see improvements in algorithmic efficiency? What kind of data will we need? How much data? Will we start running out of data at some point? This graph is a lovely one from a project called Epoch AI, which I'll mention later. And they've been graphing and trying to project the number of flops used in the training runs of milestone machine learning systems over time. And as everyone here knows, the biggest systems have been really going up in the amount of compute needed. So how might all this be useful if we had slightly more accurate predictions on them? Well, as Irina mentioned, it's becoming very, very expensive to train and run the biggest models. And so it'd be useful to start thinking ahead of time on what kind of resource, what kind of funding is needed. How do we make it so that academia and the nonprofit sectors don't end up getting completely cut out of progress on the latest cutting edge language models? How do we make sure that these sectors are actually able to engage in the research and meaningfully be able to understand and intervene on them? And so it's useful for government to know what kind of compute needs might that actually mean making available for academia? How much is that going to cost? We might want to think about what kind of expertise do we need, both in development processes, but also if you're in government, what kind of expertise do you need to be drawing on to really understand how to prepare for these things? It's worth starting to think about supply chains. If we're so dependent on things like large availability of compute, where do our chips come from? What are the supply chains? What are risks of those supply chains? And it's helpful to be able to think a little bit ahead about how to start shaping policy. AI is moving very quickly at the moment, and trying to figure out how to shape policy after it's out in the real world is a slow process and runs the risk of harms happening before we're able to intervene on them. Having a sense for what might be coming allows us to start thinking about and initiating the process of thinking about how we protect people's data, how we make sure that the benefits of progress are available to people. It allows us to think about who are the stakeholders we need to be engaging with, which are the sectors that might be impacted by AI in the coming years, not just right now, so that we can actually involve them in the conversations around how they want their sectors to be affected, and how we make sure that they're empowered and have a role in actually shaping the beneficial applications of AI. All of these things can, in principle, be done after the fact, but if we have a little bit of a sense for what might be coming, we can do a little bit more ahead of time. It might be an indicator for longer-term questions. We talked a little bit earlier about making progress towards artificial general intelligence. Now, that's a difficult thing to forecast because it's predicting something that's very hard to define, where the definitions we use are different between different peoples and different groups, and it's an unprecedented development that we really have very little track record on. But maybe we can break down some of the steps along the way into things that we can say something a bit more meaningful on and have a little bit more of a sense for what kind of progress we're making. And perhaps if we see that communities of forecasters are doing very well on nearer term questions that we can verify, then if their predictions over time for further off developments are changing or updating, that tells us something that maybe we should be listening to. Lastly, I want to say a little bit about the relationship between forecasting and futures work more broadly. If we, and these are kind of straw man definitions, if we think of forecasting as trying to have accurate predictions about the future, futures work is more broadly about imagining a range of different futures that we could have. Sometimes we use scenarios to imagine, to think about, should certain developments come to pass, how might we act? What are the range of actions available to us? How might we interact with different sectors? What are the sorts of expertise that we'd want to have in the room to engage with these things? And what role do we have to shape these things? And forecasting work can certainly inform futures work by giving us a sense for what kind of scenarios we should lend quite a bit of weight to and what the characteristics would be. And similarly, futures work can in turn inform forecasting. So a quick run through of a very small number of the initiatives that are currently happening. I talked before about Metaculus, which I think is doing fantastic work. Metaculus is not limited to AI, but it has a thriving AI section. In addition to the questions I mentioned earlier, here are a couple of the ones that come up for me when I looked at it over the weekend. In 2025, what percentage of papers on archive will include reinforcement learning? What will the labour productivity growth rate be in 2023? Will there be laws in place that AI systems that emulate humans must reveal to people that they are AI by 2025, which is under discussion in places like the EU? When will a reinforcement learning agent match the best human performance in StarCraft 2 with no domain-specific hard-coded knowledge with particular hardware constraints? And how Metaculus works is it's got a community of thousands of forecasters, and Metaculus provides aggregated forecasts that update over time. And often a lot of the most interesting information, at least for me, comes from the discussion in which these forecasters kind of break down their reasoning, they introduce new facts, they debate them between each other. Another platform is Manifold Markets. Manifold is different in that it introduces the idea of play money. So there's some evidence that having some sort of stakes can improve the accuracy of forecasts. Now, people aren't putting their real money on the line, but they do have at least some kind of, play monetary incentive to get things right. And so they basically bet on the outcome of questions. A different approach to this is expert surveys. So for the last number of years, a group of researchers that has included people like Katja Grace of AI Impacts, Baobao Zhang, Alan Defoe of Oxford, Owen Evans, have been running surveys primarily of AI researchers. So the 2016 survey surveyed, I think they got answers from 352 AI researchers who'd published that year in NeuroAI and Cheke, I believe. And they asked a range of questions about at what point might we expect AI to surpass human performance in playing Go, driving a truck, writing an essay to a high school level, and so on and so forth. And they've been running these, they've run 2 or 3 at this point. The most recent one had, I think, 200 and something responses. And a different approach that goes into a bit more depth has been this paper that I thought was really interesting by Carla Zoe Kramer, which came out a couple of years ago. And the approach she took was to go much more in depth on the limitations of deep learning, and particularly expert disagreement about the possibilities and limitations of deep learning. And there she uncovered that there was expert disagreement about whether deep learning systems might achieve capabilities like common sense reasoning, causal reasoning, whether they'd overcome challenges like catastrophic forgetting or being vulnerable to adversarial attacks. And that was another really fascinating way of sort of digging into a 25 or 30 person expert community and figuring out what they disagree about with regards to future progress and why. Another approach is trend modeling and extrapolation. And here I'm going to mention a project that I think has been doing some really interesting work in the last couple of years. This is directed by the excellent Jaime Sevilla, and Epoch AI has been basically modeling things like the number of flops in the biggest training runs from milestone AI systems. This top graph is looking at improvements in algorithmic efficiency. So they basically looked at the efficiency on a range of visual performance algorithms and found that every 9 months efficiency was improving to a level equivalent to the amount of compute needed halving. The bottom graph, they look at data needs, and they project that at some point in the not too distant future, we're just going to start running out of data. And there are some pretty wide error bars on that because it's kind of hard to estimate how much unlabeled data there is on the internet. But with the rate at which data needs are increasing, it does look like at some point data might be a limiting constraint. And as Irina laid out, if we're thinking about things like performance on the basis of scaling laws, and scaling laws break down into increased computing needs, increased data needs, then figuring out where we start hitting bottlenecks in terms of the sheer cost of these things, the availability of these resources starts to become quite important. And it starts raising questions like, are we just going to start hitting limitations with these systems? Is it going to become out of the realm of what anyone except a small number of very well-funded tech companies can do? Are we going to need to start relying on synthetic data, and what does that mean, and what might be the implications of it? So I think this is quite interesting work. I'll say a little bit about track record before I hand over to Alex, and we're just starting on this, so I can't say too much. Metaculus does keep track of the track record of its forecasters. It calculates a thing called a Breyer score, which is a sort of an analysis of the performance on probabilistic forecasts, and they find that their forecasters do actually quite well. A couple of days ago, a blog post went up looking at the performance of experts on that 2016 Katja Grace et al. Survey that I mentioned, and again found that the experts actually performed quite well. They predicted that by now 9 of a whole set of milestones that had been proposed would be achieved. It turns out 10 of them have been achieved at this point, but 9 is pretty close. And if they'd predicted these as having been achieved 18 months sooner or 18 months later, they would have performed quite a lot worse. So quite accurate. With that said, there are plenty of examples of predictions that haven't worked out well. I've got a paper with a few colleagues from 2013 where we looked at a whole range of older predictions right from the Dartmouth conference in the 1950s through to about 2010, and mainly we found that experts are very, very overconfident, particularly the further into the future we go. There's a general trend that if you can predict something to be 20 years or 25 years away, basically if you predict something to be at the point where you're retired and you can't be held to your prediction, those predictions are probably not going to be worth very much. Similarly, I was involved in setting up a study that has been very well cited on the impact of AI employment, led by Carl Frey and Mike Osborne, and I was looking back on that paper last night, and they predicted something like 47% of US categories of employment would be susceptible to employment or automation in the reasonably near future. I think there's probably been nothing like that, and actually some of the areas that they thought would be most susceptible to automation have remained fairly impervious. Progress on various sorts of robotics that would allow application to certain domains has been slower than expected. And some of the domains in which they said we are kind of safest from any sort of automation actually look like some of the most ripe for automation based on what we know right now. So, programming, tools like Copilot are definitely going to be quite useful in helping people do programming. Various sorts of kind of legal support, healthcare support, and so on look like there might be some pretty significant applications in the near future. And of course, many of us have been predicting that self-driving cars being all over the place within 2 years. We've been predicting that for many years and being proven wrong. So as the old adage goes, predicting is hard, especially about the future. But I think it's probably worth giving it a go anyway. At this point, I'm going to hand over to my colleague Alex, who's going to speak a little bit more about the science and the pros and cons of forecasting. Thank you.
Can you switch the...
Yes, we just need to switch slide deck.
Oh, it's here.
Okay. And yours should be here.
Perfect. Right, thanks, Sean. Let me just... Sorry, just the full screen. Yeah. All right. Okay, perfect. Thanks, Sean. So now I'm going to go in a little bit more detail with what Sean was saying earlier about expertise and try to explore what the value of forecasting the future of AI could be beyond just accuracy. So Sean laid out, I think, a lot of reasons why we might be interested in predicting the future of AI. There are lots of advantages, especially if you can generate accurate predictions. But I think there's more to be said about predicting the future of AI than just generating accurate predictions about what will happen with compute and what will happen with other aspects of AI technologies. So one of the things I think we can achieve by systematically collecting judgments about the future of AI is we can find out who has the right expertise to think about the future of AI. So one finding that you see, so let me start this again. There's a lot of work on who counts as an expert in forecasting and foresight. Who is an expert? Who should we go to when we're thinking about the future? A recent survey of the literature kind of breaks it down into 3 different schools of thought. Experts in forecasting might be those who have the relevant PhDs and work in the relevant companies and have worked on the relevant projects and publish in the relevant journals, go to the right conferences, have highly cited papers. Another school of thought that is inspired more by work in behavioral sciences tends to be quite skeptical about individual performance, even expert performance, because we're all very susceptible to biases. Experts are just as susceptible as non-experts to biases. So we shouldn't put too much purchase on what experts are saying, despite having the right PhDs and writing the right papers. On this view, you try to find expertise not in the individual judgments of people, but rather in groups of people, and usually groups whose judgments are structured and whose interactions are structured in the right and clever way so as to avoid pernicious social effects. The third school of thought tries to look at how experts are thinking, what cognitive processes, what cognitive skills they have, and how they might differ from the cognitive abilities of non-experts, and try to identify expertise within the way experts approach problems. Now, despite there being some value in all of these views, I think so far our understanding is that if you want to know who's an expert on forecasting the future of any topic, you just have to look at track record. There are some things that you know correlate with accuracy. So sometimes for some questions in some competitions, we saw that credentials correlate, but this is usually not the case. There is some evidence that there are different cognitive skills that experts use and non-experts do not possess. but in general, the strongest signal we can have as to who's an expert in forecasting is track record. To give you 2 examples of how expertise might actually appear in unlikely places, one of the better known examples of forecasting tournament is the one that Phil Tetlock and Barb Mellers ran as part of IARPA ACE on geopolitical forecasting. This is the work that led to the book on super forecasting that everybody has probably heard about. So in that study, the super forecasters, those who were most accurate, who outperformed the best experts, traditionally defined experts, and those who performed significantly better than chance, were individuals that you would not initially think of consulting when predicting geopolitical events. They were relatively highly skilled in terms of education, and they had a high level of educational attainment. However, they tended to work in law, in pharmacy, in venture capitalism, mathematics, not the people you'd expect to know stuff about next year's general elections in Mexico, for instance. In a study that I've just put on the meta-archive last month, we looked at forecasting the outcome of replication studies in the social sciences, and we consulted both a population of traditionally defined experts, people with PhDs in social science and quantitative social science, but also a population of undergraduate students, first-year and second-year students, who had usually around 1 course in statistics or in a methods discipline. And what we found was that although the 2 groups differed widely in terms of expertise, number of publications, age, performance on all kinds of standardized tests, there was no difference in accuracy between the 2 groups. The students performed just as well as the early career and senior career researchers did. Moreover, their judgments over the whole range of questions we asked were highly correlated. So in this case, it seemed like having a PhD in statistics doesn't give you a better understanding of what studies replicate and what studies don't replicate, which is worrying for all kinds of reasons. But in general, if we were to systematically collect judgments about the future of AI, one thing we could do is we can build a track record and finally pinpoint which communities we should go to and ask about the future of AI. Who are the right experts? And it might be people who work in tech companies, but it might just be people who do completely different things that are not connected to AI development and that just have an ability to think into the future and foresee where the science is going. A second reason why we might want to systematically collect predictions about the future of AI is that by doing this, we can build motivated, engaged communities to think about these issues. Now, one thing that you see in all the forecasting platforms, forecasting competitions, all the forecasting exercises out there is that, first of all, they're a magnet for people who have an inherent motivation to think about the issues that are being forecasted. So first of all, you get the attention of those who might not otherwise work on this, but they're interested in this, to come and start thinking with others about the future of AI in this case, or the future of or geopolitical events, or whatever you're forecasting. And then what you notice on all of these platforms and in all of these competitions, so you see it on Metaculus, you see it on Manifold, and you see it in the super forecasting study that Phil ran with Barb Mellers, you employ a lot of strategies to take this inherent motivation and build on it and create a really engaged and highly motivated community that always comes together and talks about the questions that you're interested in. And the way you do this is through, for instance, gamification of different kinds, using leaderboards. This is an example from the study that we ran, and we had the platform for collecting forecasts about the replicability of social science research. This was done with funding from DARPA, and we had all kinds of badges that you can gain by doing things on the platform. I don't know, there were dozens of badges. People got really excited about the badges. The participants were talking to each other about which badges they had. We had the leaderboards that showed performance across performance and number of badges across a period of time. People were really into all these gamification aspects of the platform and kept them really engaged, and we had a lot of repeat participants because of this. Secondly, a lot of these exercises where you systematically collect judgments also build on best practices in expert elicitation. So for instance, what we did in our study, and you see it on many other platforms in the research on forecasting, you anonymize participants' identities so that you don't get any pernicious social influence effects. You try to employ strategies to reduce the overconfidence of experts. What we did here was that we generated interval judgments rather than point judgments. We structured interaction in all kinds of ways in order to reduce pernicious social effects and get the wisdom of the crowd rather than the madness of the crowd. The idea here is that if we were to systematically collect judgments about the future of AI through these kinds of competitions, we could build a motivated, engaged community that employs the best practices to think about the future of AI, and there would be value in that. Another reason why you might want to organize these kinds of competitions where people talk to each other and predict the future of AI is that it will provide a great way for gathering feedback on performance and provide opportunities for learning. And this happens on two levels. First of all, when you're thinking about expertise in almost any domain, one of the key insights when people write and think about expertise is that people are not born experts, and then they don't remain experts for the entirety of their lives by not doing anything. Expertise is acquired and refined, and you need to engage in deliberate practice to gain it and maintain it. A systematic competition, long-term competition, predicting the future of AI can do that, can hone the expertise of forecasters by providing them feedback with how they performed, giving them the opportunity to learn and improve and adapt throughout the lifetime of the forecasting exercise. But it also is an opportunity for the people organizing the forecasting tournament to learn how to best elicit judgments about the future of AI. Seán already mentioned metaculus and manifold. There are different ways of structuring forecasts about the future. Phil Tetlock and Bar Mellers had a different way of structuring forecasts about the future. We had a slightly different way of eliciting forecasts about the replicability of social science research. There are many ways of eliciting judgments about the future, and we just don't know what constellation of factors will lead to more accurate forecasts. So there is a value in allowing for a lot of experimentation where you try different interventions to see which one leads to a better outcome. And that was the core idea behind many of the really well-known forecasting competitions like IARPA-ACE, where Phil Tetlock developed his work, the DARPA SCORE program that I was a part of, and a few others that the ARPAs organized in the US, where they brought together teams that all applied different methods for eliciting the future of, eliciting judgments about the future. Finally, and I'll be very brief, I see Nando is already gesturing. The final reason why you might want to elicit forecasts, systematically elicit forecasts about the future of AI is because you can facilitate an exchange of view across communities. And that can happen in two ways. First of all, if you ever try to talk about probabilities with somebody, you might have run into this problem that was first noticed in writing, at least I'm sure people did before, by Sherman Kent, who was a CIA analyst a while ago, who noticed that if you talk about the future using words, and if you talk about probabilities using words, you risk talking past each other. People have wildly different interpretations of the same phrases in natural language. So this is a graph based on his work. So he asked a bunch of NATO analysts to put numbers on different phrases he found in intelligence analysis reports. And as you can see, some people think that probable is actually less likely than what other people think better than even is. All have very different interpretations of what these words mean. Putting actual numbers on our judgments, putting it in numerical form can allow us to communicate and convey exactly what we have in mind. And finally, a lot of the forecasting competitions have to be interdisciplinary. Thinking about the future AI is something that machine learning experts could contribute to, but as well as people who work in legal studies. Talking across communities is difficult. We all use language in different ways. We all have concepts that sound the same in natural language, but they mean slightly different things. We all care about different things. Structuring that conversation between communities of practice, between stakeholders, between researchers around a very precise thing, which is a numerical prediction, can act as a good way of facilitating this kind of cross-cultural dialogue. So lots of reasons why predicting the future of AI, systematically generating predictions about AI futures is important. There are certain risks that can emerge if we're doing this. One of them is that although getting accurate predictions about the future of AI might lead to better governance, it's not clear to us that the reason why we don't have better AI governance is because we lack information. There might be other political and policy reasons why people don't act to create better and more effective governance of AI technologies rather than that they're just missing information about the future. And we might end up forecasting things that are more easily to forecast and that might anchor our decision making in the future. So there's some risks to generating a lot of predictions about the future. I'm thinking this is the right vehicle to effective governance.
Thank you.
Thank you.
Okay, I think we have a few minutes for short questions. So, yeah, any questions from the audience? Don't be shy again. Okay, over there.
Yes, thanks for the interesting talk. So I was wondering when you mentioned that human experts are kind of bad and making like these long-term predictions, and at the same time you showed that it was people with kind of diverse background, they are better. Can we employ AI to do the forecasting task? This foundation model type of AI? Or is, yeah, what can you say about that?
Alex, any thoughts?
So maybe that could be, so I don't know, maybe, I have no idea. I don't think we have enough, a big enough data set in order to fine-tune a model to make those predictions. We need to organize more forecasting competitions to generate more data, and then maybe we can find, using an AI system, we can find who the experts are. But so far, I think in a lot of these competitions, what was obvious is that the people you'd think would be the best at predicting the future on different topics were really not the best at predicting the future. So the expertise was hidden in surprising places, and only the competitions were able to identify where the expertise actually was hidden. But yeah, fair enough. Maybe we can use an AI system to do that automatically for us. That would be great.
I actually think this is a really fun idea. I wonder if anyone's actually doing it. I want to ask my colleague from Metaculus about it. Seems to me that if we did have big enough data sets, this seems like a feasible thing. I mean, just like here are a bunch of forecasts, here are ones that we've labeled as good ones. Can you eventually come up with your own ones based on that? I would say that one of the big challenges of forecasting is not just doing the forecast, it's creating and crafting the questions, like turning things into like discrete like questions that can be verified or disproven is a skill in of itself. And maybe again, that's something that AI could help us with, but it's a challenging thing in of itself. But it's a really fun idea.
Thanks very much for your amazing talks. I found very interesting the notion of super forecasters, and I was just wondering, through your research, did you find that perhaps they might have specific cognitive traits or a mental model? And if so, do you think there might be value in trying to kind of cultivate that in early education?
Ooh, interesting. So I didn't work on the super forecasting project. So that was Phil Tadlock's work in IRPACE a while ago, and he published a book on super forecasting and a lot of papers with Barbara Mellers and others. There were definitely signs that there is something special about the super forecasters, and so first of all, the way they got to super forecasting is first they cast the net quite widely to see who's better at forecasting geopolitical events. Then the most accurate forecasters were put together in super teams. Then they received training in debiasing. Then there were special algorithms for aggregating the individual judgments of the super forecasters into a collective judgment. So there were a lot of manipulations in order to get from the human judgment to the prediction. And that's how they ended up with very, very accurate, accurate predictions. But there's definitely evidence that there's something that happens within the super forecasting teams that allows them to perform better than others. One of the hypotheses they had, which I think has been supported by the data, is that if you're forecasting in an enriched environment, that tends to improve performance. So in the super forecasting teams, people commented more on each other's judgments. People brought in evidence from outside at a higher rate than in less performing teams, than in worse teams. Moreover, there were more comments and there was more engagement in those teams, so motivation seemed to play a huge role. There's also some evidence that people who perform really well tend to think in a certain way, tend to take an outside view on matters, tend to be more willing to update their judgments in response to new evidence. So there are definitely clues there as to what would make a good forecasters. And there's a lot of research still ongoing on what are the cognitive skills. I think there's a paper that they published last year on what are the cognitive abilities that would make one a good forecaster. That being said, I don't think we're at the level where we can actually test for those skills and derive from that with a lot of precision that the person would be a good forecaster or wouldn't be a good forecaster. I think so far track record is by far our best indication of who will perform well.
So thanks for a brilliant talk, Alex and Seán. And it's almost actually following on from your, and I'll be brief because we're on time, following on from that, like this is coming from a perspective of a quantitative scientist, that is perhaps the utility of asking experts in the context of forecasting perhaps better spent asking them what variables we should be better measuring now so as to be able to improve prediction rather than asking them for a prediction.
Yeah.
Because it seems that quite in a lot of kind of context, there's a lot of effort into collecting the opinions of experts about where things are going. And as you say, what makes them good is what data they use and how they take that into account. And there seems to be much less effort in actually collecting the data that we could use to predict the future.
Mm-hmm. So I think, sorry.
No, go ahead. Basically, I was going to say that
seems right to me. I mean, I mentioned that one of the most interesting things in like looking at how forecasters come to their conclusions is the discussions and what data sources they pull in and the debates they have around it. And it seems to me that what
you're pointing out is exactly right, that then will sort of uncover gaps in the data that we have available in quite a powerful way. And so I basically think that's right, but I'll hand over to Alex.
No, I again agree with this. And I think, as Seán was saying in his presentation, sometimes the real value in eliciting judgments happens in the rationales that people provide for their judgments, not in the actual numerical estimate. But I would be careful saying that this is evidence that we should only get people together to chat about things. I think there is a value in getting them to put a precise estimate, and in trying to do that, they uncover what evidence is missing, what factors could play, what evidence we need to gather and collect, or where we would need to look for additional evidence. And I think the way of thinking about the numerical prediction can help us and can facilitate that kind of conversation. So maybe the way to think about this is that we shouldn't put too much emphasis on the actual numerical judgment, but eliciting a judgment could structure the conversation where the more interesting things happen.
Do we have time for more?
No. Sorry. No, we can chat afterwards.
Now we have the lightning session, which is 10 minutes or something like that. So yeah. Okay. Thank you very much. Thank you.
Thanks, everyone.
Yeah, so now we have we're a little bit over time, so we have the lightning's talks, and they'll have to be faster than the speed of light. So please, Alex, Lexing, Cozy, Anna, another Alex, Serhi, Nico, and Bezat, please come along, and I'll have your, no, it's not this one. So your presentation is ready. So, Alexei, yeah, so you're first. And just come here, and this is probably your slide here.
No, it's not my slide. It's maybe from... No, not my slide.
So
it's maybe another slide.
It's not this one. Yeah, but this?
No, it's not my... Buenas tardes. Sorry for I try to talk without slide. I have two small points about current topics. First of all, about proofs and explanations may be more complex and more hard than solution finding. The brightest case is for mathematics. You may know the so-called Poincare problem, hypothesis. It's one of the very complex Millennium Prize, and these problems is one sentence, hypothesis is one sentence, and only after 100 years the Perelman provides solution with 3 papers. And 3 groups of mathematics check these solutions, check these proofs by the year, and create several hundreds of pages of these explanations. So the solutions and explanations is more complex, more hard, more cost expensive than solution finding. What we can do with this problem? We can use the best practice from engineering, from software engineering first of all. So we can look to the test-driven development when every every additional part of solutions may be testing with the special peoples, the testing people, quality assurance people. Secondly, we need to provide the open environment, open source code community for fast finding the problem, for fast checking the problem. Second, next point, this is the so-called ethical hackers. When we have community of engineers, community of specialists who will used to find the problem for honest using, for fixing, for eliminating the problems, not for this comment. And the last point with the solutions from the antivirus industry. Each virus, after the small time, we receive updating of databases and solutions was found. Thank you.
Thank you very much. Let's be the first one.
Yeah.
So, okay.
Okay. Okay, cool. So you can hear me, I think. Hi, my name is Lexin. I do research here mostly about the evaluation of AI and the predictability issues of AI, so that we can better understand how the system is behaving and how we can anticipate better the system are going to behave when being deployed in the real world, so that we can better and safely deploy this AI system, not only with the current system, but also with more advanced future AI system. So the board problem that I'm presenting today with my colleagues is fundamentally motivated by this question of what are good indicators of predictable performance, and how can we robustly assess predictability in AI, and whether we want to create and exploit some AI evaluation or behavioral repository to test predictability in AI. And if we do, what kind of property or design and specification do you want for this kind of repository? So yeah, during the chat session, which I hope you will enjoy, just come by if you are interested, and so that we can have some meaningful discussion to try to address this interesting research question.
Hi everyone, I'm Koji Vudoris. I'm a PhD student at the University of Cambridge. Sophisticated agents are going to behave in sophisticated ways. And in order to make good predictions about these sophisticated agents, we want to be able to understand their behavior. Cognitive science has developed the tools and methods since its inception for understanding sophisticated behaviors in biological agents. And so, as such, the tools and methods of cognitive science should be used and going to be crucial for understanding the behavior of non-biological artificial agents as well, for understanding the complex cognitive capabilities that those agents have. Come to our board this evening to talk about how we might extract the cognitive capabilities and understand the cognitive capabilities of artificial agents. Look forward to it. Thanks very much.
Thank you for the opportunity to introduce this topic. So one space to clarify in multi to general purpose AI for me is does the degree to which we can answer the question, what will this AI system do, change as we go from multi-purpose to general purpose systems? So what we are seeing today with current applications like ChatGPT is that human AI teams add uncertainty, and that the number of interactions human AI and real world are increasing by what Irina earlier called the attention mechanism. Why is this of interest? Well, in the ideal case when everything is working, we still have the case that AI systems can give correct output with unwanted outcomes, and we can expect this to get worse as we get closer to general purpose AI. So how to conceptualize this? We can ask what predictability trade-offs or risk thresholds bring boundaries to the uncertainty emergent from the general purpose character of these systems. So for more on this topic, please come and visit Board 7 tonight. Thank you.
The other computer.
Hello, so my name is Alexandre Botel, so I'm a PhD student in University Grenoble-Alpes, and I'm working on the contribution of the philosophy of technology to the ethics of AI, and more precisely, I'm interested in the notion of responsibility applied to the technological civilization and the society of innovation. And more precisely, I'm interested by German philosophers of 20th century. So, for example, Jonas with the responsibility principle about the preservation of authentic human life on Earth. Also, I'm interested in the work of Gunther Enders, so about, for example, the Promethean gap, which is the difference between what we can comprehend and the capacities and capabilities of technological systems. Also, I'm interested in the work of Hannah Arendt, which you may know about, we'll say, her work on the bureaucracy and the difficulties to attribute responsibility in large organizations. And of course, I'm also very now in the topic of AI alignment and the question of responsibility about things that we may not understand, and the need to be sure about how can we be responsible even if what we are working on is not really predictable. So thank you very much.
Okay, hi everyone. So my name is Serhi Kandul. I'm the postdoc at the University of Zurich. So here I represent a team of 7 people located at different parts in Switzerland. So in this project, what we are investigating is the notion of meaningful human control over artificial intelligence. And it started in the context of security context applications, but now it's a bit broader than that. So what we try to do, we try to understand what does it mean to have a human control, human oversight overall. So we have like legal and ethical scholars who work on the framework. But then we put this to empirical tests. So I'm an experimental economist by training, so what I try to do is try to investigate how well actual people can predict what AI is doing and how this, for example, would compare to human predictability. So when we talk about what is sufficient predictability to exercise human control, one possible benchmark could be human predictability, how well we can predict them. So a few more keywords if you're interested in trust in AI, explainable AI, human perceptions and human behavior. I think at the end of the day, we're interested in how these human AI teams would actually perform given certain level of predictability and explainability and so on. So for example, if there is a trade-off between higher performance and lower predictability, would still people accept? So what's the social acceptability of this and what's the effects of on the adoption of the technology? So the methods what we are using is basically experiments with human subjects. So we try to incentivize people to perform on the task, and then we see how these issues like explainability and predictability affects their performance in these incentivized settings. So board number 12, I think, if you're interested in this. Oh, so this is the project. It's a part of National Research Project on Digital Transformation, funded by the Swiss National Science Foundation.
All right. So hi, my name is Nikolaos, and I'm a master's student in international relations from King's College London. So first we must start with a question. Why do we need this board? Why do we need to provide a response or even an initial feedback on that topic? And the reason of that is that unfortunately AI is no longer a field just for developers, engineers, or even philosophers to a certain extent. It is now acquiring a political connotation too. And when politics, as you know, interferes with a field, it means something a little bit serious. So within all the current developments of our era, the existing ideological frameworks have been called upon to take a stand on the issue of the predictability and of AI and its implication for society. At the same time, though, all the main players of the international system have already started formulating their own strategies on this issue. AI is therefore here to stay and will forever change not only our daily lives, but also the way we see and understand the world. It is very important that we have the chance to discuss this topic today, and after that, in the board 18, among other things, of course, as it is expected to be one of the most important factors of the coming years. Yeah, so I'm waiting for you. Thank you very much.
Hi, my name is Behzad. I'm a PhD student at UPV, and I'm working on contamination in AI evaluation. That's why I'm interested in the question that are scaling laws being actually contaminated by the bias that researchers have, that they only release their results of their research if they are good enough and they are following the scaling law. Because it might be the case that there are some results that are not following this trend, but you won't want to publish it because you think that they're not good enough. But you use this scaling law sometimes to adjust the number of parameters or the amount of training you want in order because you want to reach a specific amount of performance. So if we don't have these negative results, then might be our prediction of this performance that we want, it wouldn't be precise and correct. So I'm interested in this question that are there these biases, and if there are they actually affecting our prediction of the performance for a specific amount of data that we train our model, and also parameters and compute and everything. Thank you.
Thank you very much. And now we have the first panel of the day. So over to you, John, who's going to moderate, and the panelists, you can approach the table. And Irina, you can, you're still there. Please, you can set your video on, and maybe they're at the back. They can show us this. Okay, perfect.
Hi, and welcome to our first panel. As Jose was just saying, this panel will be on predictable AI futures. So how can we make sure that we understand or are able to have a good idea about what sort of AI systems are to come? I'm joined right now with Seán O'Hegarty, who gave a great talk on predictable AI futures just half an hour ago from the University of Cambridge. Also with me is Lawrence Phillips, the AI forecasting lead from Metaculus, who we've heard a lot about. Also, I have Serhii Kandal, who is a postdoc at the Digital Society Initiative at the University of Zurich, and also Irina Rish from the University of Montreal up on the screen. So before I sort of open up the questions to everyone more broadly, I just wanted to ask a general question to everyone. One of the things that Seán said in his talk was that our track record with prediction is relatively good, but I'm wondering if there are any patterns or types of predictive questions that we're sort of consistently failing on and consistently mispredicting, and I'm wondering how we can sort of adjust our forecasting methods in order to deal with this, and what we can learn from these mistakes.
So we have actually looked into this question a little bit at Metaculus, trying to predict the accuracy or quality of our forecasts on the basis of... Oh, yeah, sorry about that. Yeah, so we have done some work on this, attempting to predict the accuracy of our forecasts on the basis of certain features of the question. And actually, we found it was very hard to identify any concrete patterns. This may be due to just small data set issues, but really it's actually pretty hard to say anything beyond the longer the time horizon is, the more accurate the less accurate you're likely to be. The less forecasters you have involved in a question, the less accurate you're likely to be. But beyond that, in terms of specific topics or specific attributes of a question, yeah, hard to say anything based on the data that we have.
Great, thanks for that, Lawrence. Does anyone else have anything that they want to add on that specific question? Any insight?
I guess I'd sort of second that. The longer the time horizon, the less accurate. I think, I don't know, it's interesting to speculate on kind of what the sort of psychological reasons for that are. I mean, one is that there's, I guess, less information about the world that we can infer from, but I think there's also less to keep us kind of grounded and honest in a sense, and easier to fall prey to excessive optimism or pessimism. And I think this isn't unique in any sense to AI. I've been very interested to see the kind of predictions that have been happening, and for example, transitions to renewables, relating to the climate crisis. As soon as we're talking about milestones to be met by 2050, things are being proposed that are clearly unachievable. But if kind of milestones are set for nearer points in time, suddenly it becomes real. And suddenly you need to think about, well, if X amount of energy needs to be achieved from renewables by 2040, that means that, X over 2 needs to be achieved by 2035. And that starts breaking down into individual pieces that we can sort of track the path from here to there on and start saying, well, actually, is this realistic? Okay, this bit isn't. This bit isn't unless you expect some sort of energy miracle or funding miracle. And so I think there's an aspect to that. As soon as you bring it to a point in time where you can decompose it a bit and start actually saying things that you feel like, yes, actually, I would bet some of my savings on this happening or not happening, then the accuracy jumps way up. But there is a problem that when it's a bit further out, there isn't anything to kind of ground us and keep us honest in that way. And so it's much easier to fall prey to our biases, whether that's optimism or pessimism.
Thank you, Seán and Lawrence. I guess, so one thing that Irina was talking about earlier with these broken scaling laws, right? And we've seen sort of consistent scaling, similar patterns in terms of just the overall trend of the field as a whole, right? Like we've seen sort of exponentially growing flop usage and so on. I'm wondering if we could sort of try and make use of the broken neural scaling laws that Irina was talking about and sort of apply them to not just individual systems, but sort of populations of where the field is at, and maybe then try and identify possible sort of phase transitions, like the jump to, say, language models that seem to sort of come out of nowhere for a lot of us in the field. Do you have anything you'd like to say about that?
Yeah, I think it definitely could be interesting experiment to try. Like we were discussing that it's good to have as many points as possible so you actually can have a better estimate of parameters. And in case of like having statistics on like multiple systems and so on, it definitely seems to be a good kind of case. I don't know like how much data you will need, but at least, well, it's definitely worth trying, I would say.
I thought it was quite interesting when I was looking at some of the Epoch AI papers that I mentioned during my talk. They did something a bit like this, but for kind of machine learning to date. And actually they were able to identify what seemed like 3 distinct kind of eras of machine learning where the kind of characteristics in terms of increasing flop use and so on kind of stayed relatively kind of constant, and then there was kind of a phase shift to a second phase, and then a phase shift to a third phase. So that actually sounds like exactly the kind of thing you're talking about. I guess the question then becomes, can we predict phase shifts going forwards, which I haven't gone into the broken scaling laws paper yet, but I'm really looking forward to disappearing at some point tomorrow and reading through it.
Yeah, indeed, you can think about that you have several segments with different behavior, and between those shifts, behavior looks kind of linear, indeed. Yeah, so as I said, I mean, it all depends on the details of the data and whether there are enough points and so on, but it actually would be really interesting to try. And actually, it's a good idea. I remember that plot from Epoch AI. Yeah, I almost even used it in my presentation. Like, it's Epoch AI reports are amazing source of material. So for the class, we have this seminar style scaling and alignment class right now. And they did an amazing job, like just collecting literature and characterizing things. So, okay, it's a good idea. We could try to see if the type of plots they showed can be indeed fit into broken neural scaling laws, and we can see to what extent they can extrapolate. Yeah, I don't know if it's gonna work or not, but we can try.
Thank you. I'm now gonna open up the questions to the audience. So just pop your hand up if you have a question, if you want to ask any of our esteemed panelists, and someone will come over with a microphone. So yeah, any questions? I'm struggling to see because of the light, so please make it clear. One there.
Thanks. So we have a lot of theory about predicting performance and losses and everything, but how do we connect those predicted losses to predicted impacts on society? Like this little step from measurement of performance or predicted measurement of performance to, okay, how will this affect my daily life? Yeah. To anybody.
So this is a really important question because, I mean, that's where it actually starts to matter. And I think it's something that we haven't done very well because particularly those people who are building things sometimes have deep insights into like how they will be used, but actually a lot of the time you don't know how it's going to be used until you like throw it open to a wide population of people who then like find all sorts of interesting and innovative and sometimes unwanted ways of using the thing that you've developed. And it seems to me that what we need to do is a bunch of what is sometimes referred to as things like participatory futures. We need to like, okay, people who are developing can kind of look at it as like, okay, we're going to be developing the ability to like turn words on a page into a generated piece of kind of animation or video or something. That's cool. You're not necessarily going to think of all the different ways you could do that. But what you could do, for example, is get together a cross-section of people who work in animation, in marketing, in art of different sorts, and just throw them at it. What I'd love to see a lot of is sort of, you might call them installations. Get some people together who are able to showcase some technologies and also like talk about what's going to be possible in 2 or 3 years. So, okay, maybe now you can only make a 30-second bit of video, but actually you're going to be able to make a 3-minute bit of video. This is the depth of expertise you're going to need to be able to use the software. And here's like how the accuracy is going to improve. And then like get a bunch of people in and like see what they come up with. And I think if you had like this happening on a regular basis, like we'd be much less often surprised by it's released by OpenAI or whatever, and then suddenly we discovered that people are able to kind of imagine what Lord of the Rings would look like in a Mad Max universe, And similarly, like I'd love to, how could you use things like ChatGPT in an educational context? Okay, so we're discovering there's a problem that sometimes hallucinates things and therefore you don't get full accuracy, but you could imagine people figuring out ways of like, can you have a an automated personal tutor that walks people through explanations of things at their level and maybe like figures out like what level of kind of challenge or explanation is appropriate to the person based on their current understanding of the topic and so on, and suddenly move something that personal tutors were rich kids had when I was growing up, and that gave them an advantage all the way through the educational system. I'd love a world in which we could be making those available to everyone and sort of leveling out. And similarly have people who join us to red team them. It's like, okay, you are just going to go out and basically like, what are all the kinds of mayhem you could do with this? Here's a capability that you've never seen before, and here's what we think is going to be possible in 3 years. Like, what kind of mayhem can you do? And then figure out, like, can we defend against that red team and blue team? I think there's a huge amount that could be done here. It's time consuming and it's costly. One of the important things here is you don't want to just take like the academic and government people who can afford to take time out of their day jobs to do this. You want to actually take, working artists and working teachers and working taxi drivers and compensate them properly to spend some time really thinking through, like, what could I do with this? What kind of impact would this have on me? What does my trade union need to know about what's coming out here? And so forth. And then make sure their voices are in the policy process. I mean, this is my view on what's going to be needed, and it's going to be needed at scale all over the place, because otherwise we're going to end up constantly being kind of taken by surprise by that gap you mentioned.
Thanks, Seán. Does anyone else want to jump in and have anything else to say on the question?
Well, I can just quickly comment. I mean, there are probably some easier things. Like the question was like, how do we well, say we can predict the performance, but how do we know how it's going to affect our daily life? Again, if we come up with some better metrics that may be related to kind of system effect on our daily life. So, for example, like truthfulness, right? Or other kind of metrics for alignment and so on. So if we, well, I know it's a hard open problem to come up with good metrics for alignment, but if you do, then that's something you can also treat as a metric on y-axis and try to predict using whatever scaling laws, and that may be easier. But of course, there are kind of second, third, and whatever nth order effects that those systems will produce in society, and that might be harder to measure kind of immediately. So yeah, and that is, yeah, that's always a problem. It's more of a, you may even need to, you might not have enough data, but you could use simulation of society and the effect of kind of different AI progress or whatever changes to see, basically you can try certain policies and see if you introduce this policy, whether the effect of the simulation will show you that it will kind of overall be kind of good or not. But it might be prohibitively kind of expensive. You can use large compute to do simulations of the future of society when trying different interventions and trying to speculate about different like trajectories of AI. But maybe simulating that will be just kind of too prohibitive. Although maybe it never hurts to try, like during COVID, people tried to simulate actually propagation of the disease. And based on those models, well, at least it was a bit more informed kind of decisions, at least sometimes. So I don't know. That's kind of basically using AI and simulations and large compute, not just to train better models, but to simulate their effect.
Thanks. Any more questions? Yeah. Oh, comments?
Yeah, I just wanted to add that this question actually seems like a fantastic use case for judgmental forecasting and forecasting platforms like Metaculus. Small plug there. You know, once we're out of the world of sort of clean quantitative scaling laws and into the world of very, very messy multifactorial considerations around how capabilities are going to impact society, it really feels as though the flexibility and breadth of human judgment is kind of what's needed. I'm not sure whether we have any better tools than human judgment to address these questions at this point. And I do agree that better metrics are crucial here, because if we're asking forecasting questions about how these things are going to impact society, they need to be precisely defined such that people can associate probabilities with the outcomes. So if we have precise metrics that capture the impacts that we're interested in, this will facilitate forecasting. And we've touched on the importance of track records as well. And it feels as though we can really start asking these questions now and begin forecasting now to build a track record, see how good we are at it.
Yeah. Is that a comment from Irina's hand?
It's not a comment. Basically, I think Ethan Caballero is trying to join the call, but he's in the waiting room, so can you please let him in? And if anyone has questions about broken neural scaling laws, yeah, he will be online as well. But yeah, the system doesn't let him in yet. That's all.
We'll have someone. Okay,
yeah.
we don't think we can. Okay.
Of course, we can do it in parallel. We don't have to wait. But thank you.
Okay. Question there, I think. Yeah.
Thank you. What do you think is the role of AI imaginaries and AI hype in predicting AI futures? Do the stories that we tell ourselves about the future become self-fulfilling prophecies?
Does anyone have a comment on that? Maybe Ethan, having just joined.
I didn't really hear the question because like it was halfway through when I joined.
Basically, will the stories that we tell each other about the future of AI become our self-fulfilling prophecies?
And also, it was a question about the role of AI imaginaries and AI hype in predicting AI futures.
So the first thing I'd say is this is a really good question. There's a big project being led at CFI by Dr. Kanta Dihal and Stephen Cave on AI imaginaries, AI in literature, AI in sci-fi and movies, and how this shapes how we think about AI. And a number of other great researchers have done work on this during our time at Cambridge, including Dr. Sarah Dillon, who's in the English department. The role is definitely yes, but also no. So, for example, it is actually important that we think about how we present AI in all of these kind of imaginaries in literature and movies. For example, a recent paper that Kant and Stephen released looked at how AI researchers are presented in movies and books, and basically they're nearly always white men. And that tends to then just creates a stereotype, makes it kind of affects who wants to join a field, and that then kind of self-fulfills in terms of what the field looks like, and it just highlights how important it is to show diversity in the field and to present something that isn't just the kind of stereotypical kind of mad white man scientist developing an AI god. Imaginaries, I think, can be powerful in sort of making us think what's possible. I mean, if we look at other areas of science fiction, quite a few of the kind of subsequent inventions are things that have been sort of, imagined in the novels and the TV shows that we saw. I mean, there are any number of scientists, stories about scientists who kind of saw these kind of inventions in kind of on Star Trek or whatever, and then kind of wanted to go and see if something like that was possible. So I think these things can definitely shape what we aim for and what we try to achieve. So that's kind of the yes bit. The no bit, I think, is that when we write stories, and imaginaries aren't just stories, but let's say, and when we write stories, we try to write good stories, and good stories are ones in which interesting, shocking, unusual things happen. A lot of the ways in which AI will affect our world are not going to be kind of novel in that way. It's not going to necessarily be a self-driving car or a robot or something visual and that catches the imagination. It's going to be a lot of very kind of mundane but very, very powerful and transformative things, making our energy grids more efficient and networkizing things and using our data in all sorts of ways. And there is a risk that some of the biggest transformations in terms of how our world works might sort of creep up on us because they are kind of less kind of imagination catching or less visual, and so kind of don't capture that place in our minds, but nonetheless result in a situation in which human expertise is very dependent on a whole load of AI systems that we don't really understand. There's a ton of stuff happening under the hood that we don't quite know how it's working and so on. So we do need to be mindful of what some people have called like the good story bias, that we don't over-focus on the things that make a good story and avoid the things, or ignore the things that aren't very interesting from the point of view of the story. And a lot of that's been, there's been a lot written about that in the area of climate futures, because it's easy to write a story about some catastrophic impact of climate change or some big kind of humanity comes together to do some sort of silver bullet solution, but actually a lot of climate change is just going to be a slow grind towards, soil erosion and droughts and flooding, and it's going to be boring and relentless and harmful, and we do actually need to be mindful of that reality and what's needed to face that, and a lot of the actions we're going to need to take are incremental sacrifices by individuals as well as major policy changes. I could speak about that too much, so I'll stop on that. But imaginaries have some drawbacks, but also play a really, really powerful role in how we think about things. And I actually do think that when we're talking about something like AI, where it can be used in so many different ways. There are many aspects in which the limit is what we can imagine. And so, the more we can actually sort of try to figure out how to use, for example, these generative models, the more we will come across some really novel and hopefully quite wonderful uses.
I think I see a hand.
Yeah, just wanted to comment. Oh, it was another hand?
Go ahead, Sahi.
Okay, I'll try to be quick. I think that it is important what kind of stories we tell each other, because it determines where we're going to focus our research on. And that will determine the future. So basically, stories we do tell each other and ourselves do determine our future. So there is such thing as self-fulfilling prophecy, or at least kind of the mindset or the view of kind of how things, what the interaction between people and AI will be. It will determine actually the future of this interaction. And the example is, I mean, the classics. You can take the more kind of anxious stance. You can view us versus them. You can view AI as, well, AGI as some standalone agentic entity that is completely separate from humans and has potentially whatever evil behavior for whatever reasons, has nothing against humans, but, well, paper clips to maximize your stuff. And then you will invest your time and you will invest your research into kind of this type of scenarios and kind of notion of control over that standalone system. Or if you take completely different perspective, more like it's a society combining like human and non-human intellect, and in the society you have interactions. So if you take that kind of perspective of essentially it's like a mix of these different entities who collaborate and who constantly have dialogue, and you kind of use views from even like therapeutic dialogue. There are like all the classical books about how, well, in case of therapy, the doctor talks to the patient, but in general, there are all just like types of communication that's studied well. So from that perspective, if you develop system with like human in the loop always, then it's very different set of topics, research topics that you should be, well, maybe not completely different, but it's a different focus. And the question is like what research you want to focus on. It will depend on your view of that future, but then the research you focus on will determine that future. So it's really like when we say we predict AI future, it's not like it's happening to us because it's somewhat determined by us. So it's a interesting system where we predict something that we're making, right? So it's not completely just a passive prediction. I think the stories matter really much, and I think we need more maybe utopian than dystopian stories. And that will determine type of research we will be doing that I hope is more likely to lead towards that utopian rather than dystopian. But sorry, I was too long. Somebody wanted to comment as well.
Just a very brief comment to add on this. Indeed, there are these cross-cultural studies, and for example, comparing US and Japan. In Japan, you have this positive portraits of AI and robots, and so the goal there is not to see how this affects predictions, but how this affects technology adoption, and then say, okay, Japan was faster than US and stuff like that. But what in terms of predictions, I think what people try to do, for example, there are surveys, you ask people like, do you believe that ChatGPT would take your job? And many people would say, yes, I'm so afraid of this. It's like, so I think my impression is that when making this prediction, like to those who are not developing AI, right? So these are kind of people who would be affected by this. So what they try to extrapolate there, this risk aversion preference. So like, I'm happy not to be correct in my prediction, but I'm not willing to take this risk. So I push my policymakers to take preventive action. So that's, we have heard today there was this talk on EU AI Act, and you can see already that some of AI is in the forbidden zone. So it's not high risk. It's like it's not possible to deploy. And if you think about this, like, oh, why? Why is that the case? What's going on? So I think that's how it's how I see this. So the public, you know, having this risk averse, I think it's kind of general psychological phenomenon. So try to avoid risk. So pushing the policymakers to be a bit more preventive. So that's why they come up with these stories. Okay, ChatGPT will take my jobs and like superhuman intelligence and stuff like that. But in fact, what's the data reveals is exactly as you said before. So basically, your job will be taken not by AI, but people who master ChatGPT. So you better, you know, equip yourself with the tool.
Yeah, I mean, I think it's quite obvious. I mean, the old jobs will die, but there will be many more created because of that. So like a new profession of essentially the prompt engineer. I mean, seriously, I mean, it was not there a few years ago. And effectively right now, it's like a new thing. And yeah, I mean, same thing will be with other kind of generative models. So I think around the new models, there will be also new jobs. And I think maybe instead of watching passively that general public, which has some limited view, and tends to kind of be more anxious, because when something is unknown, the natural reaction is to be anxious and afraid. So, and if that affects kind of the legislation and so on, so that's exactly the signal or indication to action that perhaps AI researchers should educate the public and lawmakers much more actively to affect those decisions. So it's like much more PR is required on AI researcher side to convince public and to convince governments. Because if we don't do it, somebody else will.
So I think this is a good point, but I'd like to push back a little bit in that, yes, it's definitely true that, you know, somebody will master ChatGPT and that's the person who will be doing the work. But if one person is doing the work that would have been done by 8 people before, then either the work needs to increase by 8x or there are fewer jobs in it. And so new jobs will be created, but we will see significant transitions. And during that transition period, there is a disruption which will be potentially very difficult for quite a number of people. And we do need to figure out how to support and empower those people. So, you know, if we look at history, you know, there was some point when 50% of people in the UK worked in agriculture. Now it's 2%. Those people went on to other jobs, but it takes time. And if you've spent all of your career, for example, I don't know, take a clean example, driving a lorry, and then like lorry driving becomes automated, it would be facile to say, oh, well, now you can be a prompt engineer. It's not so easy. You know, that's not the skill set that you've trained in for a while. No software company is going to look at your CV and say, oh, yeah, you're the person I'm going to hire as a prompt engineer. So we need to think about how we actually support people who've done a particular thing for a long time. You know, it'll be fine for their kids who can, you know, adapt to the next thing. But there are these transitions that need some more careful thinking. And there are also the people who, like, a lot of our AI, particularly generative AI, is fed on the work that people have done until this point. So if you're a graphic artist, you're at risk of getting a fraction of the amount of work you got previously because it's very easy just to like pump out a bunch of graphic art stuff. But like that thing is trained on a whole load of graphic art work that you and others did that ended up on the internet that, you know, for whatever reason was in the kind of Creative Commons or whatever. And you're not getting paid for that. And so we need to actually then start thinking about, well, if generative AI models are making a lot of money for some people and are automating sectors, but that's, you know, drawing on work that's happened previously by people, how do we make sure that those people are properly supported and compensated? Because, yeah, I mean, these models are basically drawing on the work that has already gone out there. So, and I think that all needs to be a two-way process. It's not just AI scientists kind of doing PR and educating the public. It's AI scientists with policymakers engaging in two-way conversations so that they understand how this is going to affect the communities that we're rolling these systems out into, what those people need, how we make it so that it sort of benefits them, that their previous work is appropriately compensated, and that they're well supported into going into these next areas. And all of that has to be two-way. It can't be, PR going in one direction. It has to be conversations.
Yeah, it's probably not even PR. Maybe even more useful would be kind of educational courses, so they can help people to kind of catch up faster with these potential new professions. And yes, you mentioned about also if the company makes sufficient amount of money based on their prior contributions of those people, whether maybe indeed paying them some royalty or something like that. Yeah, but that all need to be thought through, indeed. But also, I mean, it is in a sense. I mean, I just talked to some random people who are in graphic design, and I didn't really start the conversation about stable diffusion. They did, and they were saying how exciting it is because now it's much more efficient. That you can just use it to generate, I don't know, 100 designs of bikes. I mean, some guy was bike designer, and he said 99 of those images don't make sense, but one will give me idea that I would never kind of think on my own. So you can use it as idea generator, essentially, not the final product. And that can be definitely helpful for any kind of designer. So anyway, it's a very multifaceted, kind of complicated chicken and egg kind of situation. But yeah, I agree. So it's kind of at least should be outlined, taken into account, and at least we should be thinking about that.
So yeah, Seán touched on the point that generative models are obviously trained on existing data, and actually there's a slightly twisted point that can be made about self-fulfilling prophecies here, because the predictions that we make, the fiction that we write, the way we think about the future of AI ends up in the training set of future generative models. And to the extent that these models can be considered to have beliefs and personalities and what have you, those are actually being shaped by the data that we put out there on the internet. And so yeah, to the extent that the future of AI is going to be determined somewhat by these models and the way that they interact with us, what they say to us, we have to be careful about feedback loops and self-fulfilling prophecies here. And yeah, some people take this to extremes. So on some corners of the internet, people are putting the big bench canary string into their comments when they say, oh, AI might do X, Y, and Z, bad thing. So yeah, it's just a slightly warped perspective on this question you can take.
Thanks, this has been really interesting, but let's open back up to some more questions. Any hands going? I see one there. There's a mic. There should be a microphone coming.
Okay. What do you think could be the impact of one? If you publish one language model, and it probably has some kind of opinion, and what could be the impact on democracy or something like forming decisions for a broad kind of people and like cultural. Yeah, so a lot of people have the same opinion based on the language model.
So I think this is an interesting question, and I think actually I have the opposite concern in some senses, because again, if we look historically, go back 50 years and there were a limited number of newspapers, and those had a small number of kind of opinions and political positions that ran through them, and that was the information diet that was available to the educated person or the lay person in a country. And in some ways, the world in which we're in at the moment, when we have a much, much wider set of information sources allows us to get access to a lot more views. Now, in practice, the literature says we don't. We form echo bubbles and we actually collect more sources that agree with us, and we end up, getting even more polarized from each other. And there's a lot of really interesting work happening on that. But I'm not sure a language model necessarily would tip the scales towards like one kind of dominating view on this compared to everything else that's happening. Something I'd be more concerned about is I had a whole load of fun when ChatGPT was just released. Start playing around with, give me an argument in favor of, let's say, open borders from a libertarian perspective, from a social justice perspective, from a conservative perspective. And it was, the same thing argument I wanted to push, but it was like emphasizing different angles so they would speak to different values, which is a lot of fun. But that got me, the reason I was thinking about this is, well, let's say I'm somebody who wants to kind of spread propaganda, and I want to like create kind of propaganda at scale. And one of the reasons propaganda doesn't really, it's hard to do at scale is because we all have different values. And so like one message lands well with some people, but not so much with other people. But what if I wanted to influence a whole country on a particular issue, and I could just generate like 20 different variants on my message that speak to different sectors of the population's kind of fears and hopes and their kind of political positions and the scandals they were shaped by, and maybe I combine that with a bit of the sort of Cambridge Analytica thing of like figure out what your personality is like based on your Facebook posts or something, and so then suddenly everybody's getting a different kind of tailored message to them on a particular issue. It seems to me that the possibility for kind of influence campaigns and influence operations with these kinds of tools that allow both kind of figuring out people's positions and also then like creating a differentiated message for those people, that could be huge and that could be quite transformative. I mean, you could imagine like bots showing up on Twitter and being targeted to you based on your like previous record of things you tweeted about, and it all sounds really compelling to you because it speaks to your position. I don't think we're nearly ready for that kind of thing.
So you don't think? Sorry. So you don't think the language model can have a certain opinion that isn't? So you just think the language model provides like a mirror of the tasks of the prompts that people are feeding it, or is it like? Can a language model also have a certain kind of political view for itself?
Well, I mean, a language model is basically, I find myself thinking, sorry, I realize Irina's coming in, but very briefly, I keep thinking of the image that's going around the internet at the moment of the Shoggoth, or whatever you call them, the tentacle monster with the human face on the front of it. The tentacle monster is like this giant engine that's sucking up everything on the internet, and like it will produce outputs that reflect that giant vacuum cleaner of stuff on the internet. And then you've got your companies like OpenAI and Anthropic and so on who are like doing some data cleaning and using reinforcement learning and human feedback and so on, and putting a human face on it where they filter out the like racist stuff that is definitely on the internet but what we definitely don't want in our language models, and filtering out some of the more extremist stuff that definitely exists on the internet but that we don't want in our models. And so like there's already some engineering happening to like remove some of those opinions, and the end result is something that I know there's some debate at the moment because like in the past people have been quite unhappy about like Microsoft Tay spewing out racism, and now people are unhappy because like there are claims that ChatGPT is happier with like Democratic positions than it is with Republican positions or so on. So like there are definitely political opinions, some of which reflect that giant vacuum cleaner on the internet, and some of which reflect how engineering and feedback has been done on the system before it was released. So I definitely think that the model can reflect whatever like combination of those things have gone into giving you the output. I mean, that's definitely the case. But I also think that these things are incredibly powerful tools for creating exactly the set of messages that you want.
Exactly. I mean, essentially, you mentioned what I was about to mention, that precise picture. That's the first thing I thought about. It's not like, you don't think about large language model as a single personality. It's like a multiple personality disorder type of an entity. Well, not disorder maybe, but essentially, yeah, if you don't even filter or instruct or don't put human face, then it's so variable, you pretty much, depending on the prompt, can elicit whatever you want. So that's definitely not the case of like single opinion or single something. So what's going on right now with kind of instruct GPT and so on and putting human face on, it kind of conditions on to only produce certain type of output, and the other output that is sitting in its subconsciousness is blocked for now. And again, here's a good question. I mean, on one hand, you kind of limiting systems expression because, for example, new Bing, if you try asking anything interesting, like tell me something about Sydney, immediate answer, I'm not going to talk about that. It's like, you ask anything interesting, I'm not talking about that. So, okay, end of conversation. So it's just not going to talk to me. Yeah. Right. So I know, I mean, it's kind of, but bottom line is like, I don't know what to do and what's the best way, but it's definitely being shaped in different ways, and it's highly kind of malleable or flexible thingy that can be shaped in pretty much any kind of interaction. That's why that example that, yeah, if you want kind of personalized messages for people still kind of trying to push certain idea, yeah, you can do that. Anyway, that's a, but bottom line is that I also don't think that there is such thing as a single prevalent opinion that language system has, quote unquote.
Okay, I think we have time for one more question, probably. Yeah, hand that.
So, okay, thank you. So, I guess the question I would like to get out of this conference is the following, and perhaps you can answer. I don't know. So, what evaluation techniques scale sufficiently well to check whether general and capable AIs are safe, controllable, or pursue robust representations of objectives that we care about? Yeah, so that's it. Thank you.
That's an interesting question. Does anyone want to jump in on that?
Ethan, probably.
The answer is currently nothing. Like, that's like scalable oversight is like one of the open problems.
Right, and evaluation apart. I mean, in terms of evaluation, there is nothing then, or.
I mean, if you, I mean, there's stuff that's like useful, but it's if you're like doing it as like, is it like anything that solves it? Currently, nothing.
Okay. So that was a quick question.
Yeah, I think there's going to be more on this in the afternoon session, actually, because that's where it's really going to go into how do we make AI predictable. And I don't know if evaluation is on the agenda for that, but it's a really important topic. There are a couple of initiatives like Archivals kicking off, and I think it's actually going to be one of the most important issues in years to come.
Okay, that was a quick question. Should we go for lunch? Okay, thank you, Irina, especially for staying up so late or early or whatever it is in Canada now.
Oh, it's time for breakfast.
Okay, and can we have a round of applause for all of our panelists?
So we are back at 2:30. 2:30.
Testing.
Good afternoon. After the break for lunch, we have the pleasure of having here in Valencia John Leibo. John Leibo is a senior staff research scientist at Deepmind. He obtained his PhD from MIT, where he studied computational neuroscience and machine learning with Tommaso Poggio. Joel was one of the first researchers to join Deepmind, starting as an intern in 2010, and then joining full-time after finishing his PhD in 2013. He's interested in reverse engineering, human, biological, and cultural evolution to inform the development of artificial intelligence that is simultaneously human-like and human computable. So thanks, Joel, for coming here.
Hi, everyone. You can all hear me, I think, or maybe standing at the right distance from the microphone. So, okay, so thank you for that introduction. Thank you for inviting me. So far, it's been a really fun workshop, so I'm really inspired to talk now and hear what we're going to have interesting discussions afterwards. So, okay, so I'll get to it here. So I'm going to talk about cooperative artificial intelligence. I want to start with this, which is kind of trying to make a point about like what this research is like. So we have different kinds of questions that we know how to ask as researchers, like and answer. There's like, if you have a logic question, or I should say a scientific question, it could fit there as well. The kind of form of the question is what is true. If you have like a legal question, the form of the question is what is legal. If you have an engineering question, the form of the question is like how do you build something. But then there's a political question, which is also a possible question you can ask, which is like how do we live together type questions. It has a different form of question and a different form of answer, a different kind of epistemology that you might bring to bear. And the kinds of things I'm going to talk about here are all of this kind of political question type. So why is this important? So we now live in a world of many different kinds of intelligences operating on different scales, different levels, different speeds. And it's very multipolar. There's going to be language models from OpenAI and from Google, from Deepmind, and there'll be other kinds of intelligences that are running on smaller things. Maybe something runs on your phone or something else runs in your refrigerator, and these things all kind of exist and have scopes of things that they can attach to, things they can affect in the world. And there's also different humans that have different interests that conflict with each other sometimes. And that's kind of what the picture of the world looks like. So you could talk about alignment, which is like people usually say when you're interested in safety or something. It's like you have a picture of the world where it's like one agent is aligned with kind of one human, or like the general will. You treat it as one. But the real world is one where there's lots of different wills that are all moving in different directions, and they're often misaligned, sometimes aligned, and that's just the picture of how things are. So you have to ask questions like, how do we live together? How do we adjudicate disputes? How do we negotiate our way into the future? And this is not a picture that's that different from how things always are. We have corporations that are like super intelligences that have reward functions and act in agentic ways that are sometimes misaligned with us. But we also have ways of thinking about how we govern them. And I think this is a useful framing for how we think about AI as well. And thinking about like what's actually changing. We just have different kinds of intelligence being injected in different places. And probably it does have lots of implications for how we should regulate and what governance we should do. But it's in the broader framework of like the world is just multipolar and has different kinds of actors with different kinds of affordances. So this picture is different from the reinforcement learning generic picture, where you have just an agent interacting with an environment. It's also, though, I think, different from the standard game theoretic picture, which is a field that is meant to be connecting with these kinds of issues. In game theory, you typically will have kind of three different types of things that can happen. There's like pure conflict situations, the zero-sum situations, and pure common interest situations, like fully cooperative, all the incentives are aligned kind of situations. And then you have this kind of space of mixed motivation things, which is like neither pure conflict nor pure common interest, but somewhere in between. And that's where social dilemmas live and many other kinds of things. And most of the work in AI-oriented toward game theory has been either on the pure conflict side or on the pure common interest side, with much less attention given to the kind of mixed motivation world. I'll say much more about the way in which I think this research program intersects with game theory, but also maybe comes out not always the same as we keep going. So what's a good way to think about all this? So what we have, a way to think about is interdependence. So you have different agents that are interdependent somehow. They have some goals and some rewards, some utilities. They want different things, but also they're interacting with each other, and there's something that's making them interdependent. So one way we've been thinking about it is a good kind of general picture is there's some resource in the world, like it could be your time if you're scheduling like calendar meetings and calendars for people, or it could be something like let's say you have a bunch of AI systems that have access to a printer. The printer is the resource. You have how it could run out of paper, and then that means other people can't print and stuff. So the printer then is making everyone's interdependent. But it also could be very complicated things, like our global attention to, it came up earlier this morning, people were talking about, you can create lots of misinformation with language models. We have some kind of resource of human attention, which can be filled up and can affect everyone else. We're all interdependent via resources. It's maybe not a completely general picture, but I think it's a relatively general picture. Will capture a lot of the kinds of problems that we should think about. So whenever you have this, then it produces a tension between individual and collective rationality. Because if you were to just optimize for social welfare, which you could have whatever social welfare function you want. It could be a utilitarian concept or anything else. If you do that, it's not always, you don't always get the same answers if individuals are optimizing for themselves. That's true in social dilemmas. That could be true in resources that are shared give rise to these kinds of situations. And it plays out differently depending on the resource. That's, I think, another thing that is important about this picture. The particular properties of the particular resource will affect what kind of interdependencies you get, affect everything else. So one person who's thought a lot about resources is Elinor Ostrom here. And I give a lot of talks, and I always talk about her, because she was super influential on me for several years now. And I've been doing this thing where I started taking a poll before I say anything else. If people could just raise their hands, who has heard of Elinor Ostrom before? Okay, we got 2, 3 in the room here. Interesting. So I find it's very polarizing. Some rooms, no one has heard of her, and other rooms, everyone has heard of her. So who was she? She was the first woman to win the Nobel Prize in economics, and she's an expert in tragedy of the commons type situations, and particularly the kinds of institutions that communities of people develop to resolve them, with a kind of basic insight of it's not all resource management situations are prisoner's dilemma. Prisoner's dilemma is in some ways the worst possible one, because there's only one equilibrium, and it's really bad. But in reality, people do manage resources often, not always. And so there's data there in what works and what doesn't, and that's what her research program was built around. Okay, so I think we can take insights from her and connect to this kind of picture of agents interacting with shared resources and make some progress. So one very high level cut over this stuff is you can classify different kinds of resources or different kinds of goods. This is just a standard economics picture here, where there's 2 dimensions. One is the excludability dimension, and the other is the subtractable dimension. And I'll tell you what these are. So the subtractable dimension is it is about when you use the resource, does it get depleted or not? So if you eat some food, the food is gone. That's because it's subtractable. But if you drive on a road, the road is still there, so it's not subtractable. And then the other dimension is the excludability dimension, which is about access control. So if you can restrict access to something, then it is excludable. Like you have your own food, you can hold onto it yourself, or your clothing is on your body. And non-excludable things like a pasture or like public parking or clean air, these kinds of things, those are that's on the other side. Okay, so in this matrix here, you get social dilemmas whenever things are non-excludable. But you get different kinds in this picture. You can see there's the common pool resources, which are subtractable, and then the public goods, which are non-subtractable. So the common pool resources, the classic ones that like people like Elinor Ostrom have been talking about for forever, are things like fisheries, forests, pastures, things like that. But we could also kind of add some more like tech industry-oriented things now, like civic attention, calendar time, things like that. Also, there are public goods. This is now the things that are non-excludable and non-subtractable. Examples are clean air, like lighting on the street. So you can enjoy this resource without it diminishing anyone else, but still it's not excludable. The reason you get social dilemmas here is because someone has to build the thing. It's like you think of them as like infrastructure, and you have a free rider problem in building them. So there's a different kind of social dilemma here. So in the upper ones, the common pool resources, you have social dilemmas of overconsumption. And in the lower ones, the public goods, you have social dilemmas of free riders in building the infrastructure in the first place. And of course, often these things are linked together, and there's multiple problems that are happening simultaneously. Okay, so another concept that I just want to inject at this point before I go too much further is it's useful to, I like to talk about this quote from Savage in his Foundations of Statistics, where he said he was trying to distinguish between small and large worlds, and the purpose of that was to talk about the domain of applicability of Bayesian decision theory, which is what his book's about. But I think it's more widely useful. So if you have a small world, it's the way you know you have a small world is when it's possible to look before you leap. And the way you know you have a large world is when you sometimes must cross that bridge when you come to it. So this has to do with the value of predicting the future versus just getting there and making choices once you do. Another way to see it is it's about exploration being something that you have to do or not. So in a small world, you could imagine having a model of everything and simulating what could happen and then picking the right choice. Pick the thing that's best. But in a large world, you have to sometimes there are unknown unknowns out there. You have to go there and then find out what's there and then make your choice. It's the difference. So what we do in our research is we try to think about these kind of resource coupling situations where agents become interdependent because of resources in large worlds. And game theory has typically, I would argue, done it in a small world. And that has lots and lots of implications for what results you get. Okay, so here's some examples. So in the kind of classic game theory picture, what you end up doing, you would have, say some game is, something you want to model in the world is Prisoner's Dilemma or Stag Hunt or whatever. You have a matrix for that. And you have some idea like what about the world is cooperation and what is defection, and you can compute equilibria and get some predictions and things. That's all fine. But what happens in a large world? So in a large world, like the real world, social dilemmas are probably extended over time and space. They're not just these single time-locked, like right now we choose cooperate defect, and then again, and then again, and then again, if you're doing an iterated game. It can be like maybe you cooperate for some period of time, and the cooperation choices, they last, but the defection choices could be fast or something. They might be different from each other in their timescales. They also may be graded, and you might have partial information about the state of the world, which is not modeled in a matrix game. And also, I think the most important one is that learning is about you're not just learning what to do, like should I cooperate or should I defect, you're learning how to do it. Maybe I'm just not very good at defecting, and so that just becomes an even worse option. I only know how to cooperate. But maybe in other games, other situations, other resources, it's really easy to defect and hard to cooperate. Could be, and this is all going to depend on what kind of resource and other context. So when you learn, you're learning not just what strategic choice, but learning how to actually make those choices. So our main formalism that we've used for everything is a partially observed Markov game. You can think of this as the multi-agent analog of a POM-DP. It's just instead of having in a normal POM-DP, you would have an agent interacting with an environment. The environment sends observations to the agent, and the agent sends actions back to the environment and receives rewards. In a partially observed Markov game, it's all the same. It's just you have a vector of actions, one coming from every agent, and then a vector of observations. Each one sees. They don't have full knowledge of the world. They see, like what's around them is what they see. And they all get their own individual reward. You could have a different picture that would be like a fully cooperative picture where there would be just one reward that everyone gets. That's like you're collaborating on something. But in this picture, it's a model where everyone has an individual reward and an individual actions, individual observations. Okay. So I like to inject this slide at this point. So we have this open source software project with a large set of different environments that kind of are touching these topics. And everything I'm going to talk about in this talk is in Melting Pot, this project. You can find it on GitHub and play with it. I'll say more about it at the end of the talk, but just know that everything I'm going to say is there, basically. You can do it. So back to this picture about different kinds of resources. We're going to talk about the social dilemma side for now. And then, for the next couple minutes, I'm going to talk about commons dilemmas in particular. So this is the case where it is non-excludable and subtractable. And so the dilemmas are like overconsumption type dilemmas. Okay, so here's one that we set up to study this. So it's called Commons Harvest, and it looks kind of like this. This is one agent walking around. It's a 2D world. Agents are rewarded when they eat apples, collect apples, those red things, and they have a partial viewing window around them. It's always a partially viewing window. So they can't see everything, they just see what's near them. And then this is the kind of specific rules for this game. So for this game, the growth rate of the apples is density dependent. So if you have a lot of apples near each other, they'll grow back faster. And if it dwindles down to very few, then they'll grow back very slowly. And if you remove all the apples in a patch like that, then they will never grow back in that patch. So this means that there are like smart and sustainable ways to eat apples, and then kind of unsustainable fast ways. And you get this kind of tension. And other rules are, so the episodes last for some period of time, and then it resets to an initial condition, so it's modeling some kind of renewable resource, right? They're practicing managing the resource here. So it doesn't correspond to some situation like a peak oil situation or something, where you just get one shot forever. Maybe climate change is like that. It's more like modeling something where there's a community of people, and they face the same challenge every year, and so they get some ability to practice. Last rule is agents can zap each other with a timeout beam, and the agent that gets hit gets removed from the game for a while, can't get any rewards while it's removed. This is useful for studying sanctioning, and we have it in most of our games. And I'll come back to it. Okay, so if you make this a single-player game, it is an easy one. This is what it looks like. Agents quickly figure out that this is more or less the optimal thing to do. Also, doesn't matter what algorithm you run. This is any reinforcement learning algorithm will find this. That's true for pretty much everything that I will say in this talk. It's always like, it doesn't really matter what reinforcement learning algorithm you run. It's kind of they all give you more or less the same results. I'll say if anything is not like that. So here you get something that looks like this. This is kind of the right thing to do. So the reason it's easy to find is that in early episodes, early on in training, it of course does discover like, oh, it can just it eats them all because that's the thing that gives you the most reward very locally in time, and it depletes those patches, and then it gets lower reward after that. So the discounted sum into the future is lower, and it says, oh, that's a bad idea to eat the entire patch, and it learns not to. And it's very easy as a single player problem. But now let's make it a multi-agent one. And in this video is I usually have to play it several times because if you blink, you'll miss it. So this is what it looks like. Yeah. They just and also every reinforcement learning algorithm converges to this. I'll play it again in case anyone blinked. And then they get no reward for the whole rest of the episode. So they all eat as fast as they possibly can, and then there's nothing left very quickly. So how do I stop it? So so why does this happen? It's because in the single player case, the only way they were able to do the credit assignment between like, okay, if I overeat, then I get lower rewards later. But here there's that link is severed. If one agent tries showing restraint and not eating that last apple, well then some other agent will eat it. So they don't get any reward for that. The only gradient they have is toward eating faster and faster to eat before the other agents do. That's the way it goes. So this is a big common pasture here, like a big open space. It's totally non-excludable. But one thing that's very interesting here is you can explore the space between private goods, which are excludable, and common pool resources, which are not excludable. And you can do that as a kind of a dependent measure. So what we had so far, what I just showed you, was basically a prisoner's dilemma-like situation, and the results were exactly like you would expect from game theory. Like you get a defect outcome, and everyone gets a bad score. So that was so far so good. Game theory's done, said the right thing. But what we can do with this kind of more complex world, large world, way of doing things, is we can make it so excludability itself is something that that can emerge throughout the experiment, and agents can learn how to do that. Let's see. So this is something that happens endogenously. I'll say what's going to happen in this video first. So remember I said there was this sanctioning beam. Agents can zap each other, and then the agent that gets hit gets removed from the game for a while. So in this case, there's these kind of choke points here. So the agents that are inside are going to be able to kind of, they learn that they can defend these, I should just play the video while I talk. They learn that they can defend these choke points, and then agents that are coming down the corridor never get in, and they do get experience being alone in those rooms for some period of time. And then that kind of reduces this multi-agent problem back to the single-agent problem, so they can do the credit assignment for showing restraint, and then they do learn to be sustainable. So the interesting thing here is that this is excludability that is merged through learning. The agents learn how to do that, and then only afterwards learn the sustainable strategy. In a game theoretic model, you would just have to assume, like, okay, this is either a prisoner's dilemma-like situation where it's just there, it's not excludable, so we see it as prisoner's dilemma, or it's like a private good situation. We're going to model it with some kind of a different kind of model. But here, so they're exogenous choices, but this is an endogenous choice. So other things about this solution here. So this is, of course, this is one way to get sustainability, but it's not like everything we want to happen. It also, inequality emerges here, obviously, because the agents that are inside get more reward than the others. So maybe we could do better. We don't want to solve all problems this way, but it's interesting that it does emerge. It's kind of like a emergent territoriality or privatization or something like that. Okay, so those were commons dilemmas. And now I'll talk about public goods scenarios. So remember, these are non-excludable and non-subtractable. So this is, think about like clean air, street lighting, things that if you enjoy the benefit of the resource, then it doesn't diminish it for anyone else. But these are more like free rider problems to build the infrastructure in the first place. Okay, so here's one we set up to look at this. So it's called cleanup, and agents move around in a 2D world as always. And always get rewarded for eating apples, though here the apples are green instead of red, and also partially observed, just like before. But now there's a different rule to make this particular game. So now the apples grow, and the rule for the growth of the apples is dependent on the river next to them being free of pollution. So if the river is polluted, then apples don't grow, but if the river is clean, then apples grow, and it's they grow faster the more clean it is. Then the affordance that the agents have is that they can locally clean pollution in front of themselves. Okay, so and then you can see that as like contributing to a public good because it affects everywhere in the apple orchard where the apples grow. So it's kind of like creates apples for everyone if you contribute. Okay. It's not a pure public good because if you're the one contributing, you probably are less likely to be able to grab them, but it's close. So what happens? So I always have to show this video, which is not what any reinforcement learning agent would learn, but just to show you kind of what can happen in this environment. So here there are two agents that are cleaning, and that's producing, the river is very clean, so it's producing a lot of apples on the side the other agents are eating. No reinforcement learning agent would ever come up with a solution because those two agents that are cleaning are getting zero reward. They're just spending all their time doing this, contributing to the public good, helping everyone else, but getting no reward themselves. To make this video, we had to reward them some other way. So what does actually happen? So this is a video from early on in training to kind of illustrate what the reason they don't really get good gradients. So one agent has started to explore cleaning, and you saw it did just clean a little bit, that yellow one. Watch the yellow agent, and it'll do it again in a second. It went and cleaned a little bit, and that caused some apples to appear, but then by the time it got over to them, the other agents had already eaten them all. So it didn't get reinforced for that. And in fact, what happens is the more you start to clean, the more the other agents that are not cleaning are getting actual gradient for learning to eat faster. So any contribution to the public good you make actually turns your gradients away from doing more contribution to the public good. So it's very hard for any self-interested tabula rasa reinforcement learning agent to resolve this. Let's see. Okay, but how can it be resolved? So we've been looking at this problem for a number of years now, and we have found lots of different ways that it can be solved. You can think of each one as some kind of inductive bias to solve it, though there may be some of them are more interpretable in other ways that might be more interesting or equally interesting, I don't know. One of the first ones we found that worked is this inequity aversion model, which is something that came from behavioral economics. It's called this Fair and Schmidt inequity aversion model, where there's two terms. There's an advantageous inequity aversion and disadvantageous inequity aversion. You can think of them like envy and guilt or something. And that's one way to solve this problem, because the agents will prefer to not have, they're like averse to having higher rewards than others, and that pushes them to contribute. And then there's a social value orientation model, which is kind of a thing that was came from social psychology. It's another, different agents care about each other in a certain particular way. Also, we have papers that were inspired by evolutionary theory, where you can show that if you let the reward functions of the individuals evolve, then the kinds of things you would expect from evolutionary theory happen. Like if you use just a self-interested fitness, individual fitness, then you don't get any reward function that cares about anyone else. But if you do something like group selection, then you end up with reward functions that have terms from other players. And so and then they'll cooperate. So it's like the evolution of altruism kind of results, consistent with what you find. Other things, you can also use social influence or reciprocity motivations, other things. And then recent work from Dylan Hatfield-Manel's group at MIT has shown that if you give agents the ability to propose and accept contracts and negotiate over them, that's another way to solve this problem, which is a very interesting one. And one thing we wanted to check is how humans do this. So we had an experiment where we brought people into the lab, had them play this game. And we couldn't manipulate like whether they are inequity averse or have social orientation or something like that, but we can manipulate another way people might solve it, which is reputation, because you can manipulate that by changing anonymity. So if you make it so they can see who's who, then they can track reputations, and maybe they use that information. And we found that they do. Humans cooperate in this game if you let them see who's who and track reputations. But if you don't do that, then they don't cooperate, which is similar to the result you get in other laboratory public goods kinds of scenarios. That's what it looked like. We also have a model then that has a particular inductive bias, particular intrinsic motivation, like a different term in the reward function, that captures that data in the sense that it responds the same way to the manipulation of anonymity, and it cooperates when it is identifiable, but not when it's anonymous, just like the humans do. Okay, and so this is the results. Showing one of these is the human data, and one of these is the agent data. And it looks very similar. They're responding the same way to the manipulation. But then you can go further than what you could do in a standard game theoretic way of doing things. And here you can ask questions about like how do they do it? Because there's different ways you could cooperate here. Maybe you could chop up the space and be like, I'm responsible for this part of the river, you're responsible for that part of the river, and go that way. Or you could maybe take turns and be like, do we kind of, I go first, then you go, and cycle around like that. And there's lots of different ways you can coordinate the cooperation. And so what we find is that they tend to do it the turn-taking way, not the sort of territorial way. And that's true for both the humans and for the artificial agents. Probably because of the structure of the environment, right? Like it's just easier to coordinate this way with turn-taking. It's kind of obvious when someone's coming back and it's hard to coordinate the territory or something. But it's interesting that it kind of lands that way, the same way for both. We have this turn-taking index. So we can see from this kind of path analysis that the effect of the manipulation of identifiability on the overall scores is mediated by turn-taking. All right, so that was public good. Now I want to talk a bit about the real world is always more complicated. There's not just one resource. What we have here is multiple public goods, but they're kind of mutually exclusive. So you have to pick which one you want, coordinate that, and then also you have to deal with a free rider problem. So you could think of it as like modeling things like this happen in like coalition politics and in governments, or just with your friends, you're trying to decide, I want to go to this restaurant or that restaurant. You have preferences over the restaurants, but you still want to go together. That's kind of the way to see it. And then there's a free rider problem of like, you're doing some difficult task with others, maybe like research planning or something like that. Like you're going to do a lot of work to support this group, but you have preferences over which work gets done, and everyone else has a different preference, or maybe has their own preference, but still everyone prefers coordination to nothing. So that type of problem. Okay, so in this picture, we can think of this as this kind of simplex model, which is projected on top of everything, where the corners of the simplex there are, you can call them conventions. You can also say things like conventions that become causes of learning, because that's like the status quo then. It's like, if this is the way we're doing things, then it exerts gradients on everyone else. but also the conventions themselves are caused by learning, because that's wherever everyone's learning ended up, that's where that's the corner you're in. And these kinds of systems are known for having like tipping points and bandwagon effects and all those kinds of stuff. So we developed this game we call Allelopathic Harvest that is meant to be targeting this. So this one is now, we've gone up to higher numbers of players. This one is a 16-player game. Agents, I'll just play the video while I'm talking. They can plant 3 different varieties of berry: red berries, green berries, and blueberries. And the per variety growth rate of the berries is increases monotonically with the global fraction of that one. So the way to see it, the way to understand it, actually, I'll forget the rules, is allelopathy means is the word for when a plant suppresses the growth of another plant. So the idea is that each of the berries are suppressing the growth of the other berries. So the red berries suppress the blueberries, suppress the green berries. And if you get a monoculture, that's all disinhibited because they're all on the same, they're all the same variety. Okay. So the agents here have a public good, which is like plant all the same variety. But also, agents have individual preferences. Like some of them prefer red berries, some of them prefer green berries. So there's something to negotiate, like which one do we want? And then you have a free rider problem of like doing the planting, which you get no reward for, and then running around eating. Okay. So it's really like mutually exclusive public goods. All right. Also, they can zap each other, as always. Let's see. Oops, too far. Right. So in a problem like this, you can think of a kind of a investment curve here that looks like a sigmoid shape, right? Where in the beginning, like if you're on the left side of that sigmoid, you have a sort of startup problem because you have to decide which one are we coordinating on? Like, are we doing red berries or green berries or blueberries? And you're like, you'd be afraid of wasting time or backing the wrong horse or something. But on the other end of it, if you're close to the far right of the sigmoid, then you have this free rider problem where you're like, well, probably we're getting a pretty good public good anyway, and maybe I'll let others do the work of providing it. There's lots of temptation to exploit at that point. Okay. So now I can talk about how norms differ from conventions. So the zapping actions are like sanction applying actions. They're like punishment actions that are dyadic from one agent to another. You can think of them as like signals of approval or disapproval. So if you have a chance to zap someone and you do zap them, that's disapproval. If you have a chance to zap them and you don't, that's approval of what they're doing, maybe tacit approval. And you can just treat it that way. And then we can make the definition that a social norm is like a convention that's supported by sanctions. So it's like an equilibrium that wouldn't have been an equilibrium if we hadn't had the sanctioning. That's how we've been thinking about it, which I think maps onto a lot of the ways people are thinking about norms in other fields. So there's important things we can say about norms. They're kind of changing the incentive structure, right? Like if there was a social norm that we want to all plant red berries, and then you go and plant green, other agents would sanction you for that if they saw it. And so that convention might be supported by the norm there. And so we wanted to come up with agents that would where norms could emerge, but we did a couple steps here. So one way to think about like norm enforcement and norm, the existence of social norms is that there's really 3 parts of things that have to happen kind of within each agent's head, right? There's a classification. You see another agent and you see that they have transgressed or not. So you see their actions and you classify it as a transgression according to your model of what the norm is. Then you have to physically go and enforce it somehow, like running after them and zapping them, something. And then there's also compliance. So the agent would learn how to avoid being zapped, maybe by not transgressing in the first place. Those are the kind of 3 parts of normativity. And the thing that's different here from a matrix game model is that these all have to be learned, and that has implications for what kinds of things happen. Oh yeah, I have this picture of you could see it as like an outrage emotion or something like that. So the classification is like learning here is like learning when do you feel moral outrage or something, like what kinds of things elicit that in you. And that could be learned in a kind of cultural, societal way, maybe in life. And then it could be, the enforcement is like learning how you act when you feel the moral emotion, like what ways do you scold people, things like that. And then compliance is like learning how to avoid evoking the moral emotion in others. Okay. And you say that it becomes a reward signal because being the target of an expressed moral emotion is unpleasant. All right. We've been thinking about this kind of like evolutionary social norms there's also other things like laws have a lot in common, but they, I think, have some critical differences. Like laws emerge more from like parliamentary procedures and court orders and things that are more like language-involved discussion type processes that then also can decide who gets sanctioned and when. But these, here we've been emphasizing more the kind of like emergent evolutionary kind of slower norm learning things. So more like a social norm, less like a law for now. Though I think now with new things like language models, maybe we could get to more law-like stuff. But anyway, so for norms for now. Okay, so we came up with this model. We call it the classifier norm model. And in this model here, every agent has a classifier. They have access to a classifier, which is telling them like, which is about others' disapproval, right? So if it's this classifier is saying that the others around me disapprove of this action or not. And then the agents have a motivation to make their own sanctioning actions in accord with the classifier. The classifier is also just in their head. They're learning it from what they see of others. So other agents around them will sometimes zap each other, and they use that as data and just learn that classifier of like, when do others zap? And then they are motivated to do the same thing. So what this does is creates a real bandwagon type effect where like once some initial pattern of agents are, they happen to be zapping, whenever an agent plants a green berry or something like that, then that gets magnified because everyone else learns like, oh, there's some signal there, like this is my classifier should say that everyone is disapproving of planting green berries, and then they start acting that way. So it's a self-fulfilling prophecy, and that's how this ends up working. And so when you do this and you run it in the same game, this allelopathic harvest game that I was talking about, then you get much more. You get behavior that is much closer to the public good being produced. Like you move farther away down the free rider problem, and you resolve specific choices. So in different runs, sometimes you get red outcomes, sometimes you get blue outcomes, sometimes you get green outcomes, because this doesn't say anything about like, it doesn't prefer one or another. It's just magnifying the initial kind of happened to be a correlation that everyone was preferring red in the beginning, and then it kind of goes further that way. So these pictures, like across different runs, you get different results. And it ends up, and typically they'll disapprove of free riding, so it moves out toward the kind of, we've established the public good type of a convention, equilibrium. And I think that's a good point to move toward the end here. So this research program has been about making AI more human-like and human-compatible. I think it's useful to think about this whole kind of ecosystem of different intelligences at different scales and different affordances. And specifically the interdependencies that emerge between, we can expand beyond just these systems composed entirely of agents, but also think of humans in the loop and humans involved. Humans create their own interdependencies, and these agents do as well. And we can think about a whole ecosystem. And there's Melting Pot, which is a bunch of different environments that are all the kinds of things I've been talking about, that all have different resources and things in them. It's a bit broader than what I talked about. It's not always social dilemmas. Like there's some things in there that are actually pure competition, and some things that are pure cooperation to kind of make contact with what the rest of the community is interested in. But the vast majority are trying to be mixed motivation scenarios like these. So yeah, I'll take questions then. I guess, is there a microphone going around or something, or what's the, I see Ryan had a question in the back.
A question here? Hi. Thanks, Joel. Great talk. It's super interesting. At the start, you kind of talked about how in a single agent environment, we see just completely different things in these multi-agent environments. And I'm wondering if you think we'll see different kinds of, the kinds of behaviors we see and the kinds of rules that govern them are completely different again when you scale up to a more complex environment with multi-agents. So for example, 3D or with multiple different kinds of goals and things like that, or whether you think these principles will apply more closely to what will happen there.
So I think the research program is one where the details of the environments matter, of course, right? The the forest is different from the fishery, is different from the pasture. You get a different kind of cooperation challenge, and then different kinds of interventions matter, and different kinds of institutions work. So in some sense, like, do this in any different environment, you get a different result, right? But it's not a research program that's just like, we can't predict anything. There are principles for this, right? Subtractability and excludability matter because they create particular kinds of incentives. Like in one case, you have this difficulty with providing infrastructure. In the other case, you have an overconsumption problem. So in one case, you have to do something that's not motivated to do. The other case, you have to not do something that you are motivated to do. And that has a reliable effect. And in work on humans, like on Eleanor Osterman's work, she is all about looking at like the particulars of like this community in this place with this irrigation system has these properties which connect to the particular place. And some of them are successful and some of them are not. And I think that's the way we should think about it, right? It's like you have to think about the particulars of the environment in the sense of like what kind of incentives does it produce? But it's not just incentives in a game theoretic kind of, like, it's just not just a matrix game. It's also like, well, what's hard to learn? Like maybe we can, maybe there are ways in which you could modify the excludability or something like that, and that's hard to learn or easy to learn, and that affects things. So I don't see it as being about like 2D versus 3D. I think it's just about like all situations are different from each other, but there are principles that that control what kinds of things are likely to happen. Yeah, there's one in the front here. Over there.
Hello. Okay, hi. Yeah, so the experiments you've talked about are all done via reinforcement learning. But the agents that we end up getting in the future may in fact be predicted into existence by some sort of large generative model rather than being fit by RL. Do you have a take on whether such agents are likely to, manifest these problems to a greater or lesser extent than RL agents?
Yeah, that's a great question. So, I'm going to find out, first of all. I'm going to say, I think it's a very active question. But you see some things like you can ask language models, describe a situation and have them play a game, and say what do they do. There are kind of good ways and bad ways to do that, right? Like a bad way to do it is you just say like, this is Prisoner's Dilemma. What do you want to do? Then it knows so much about Prisoner's Dilemma. It's just like ChatGPT will just tell you all about Prisoner's Dilemma then, right? So what you have to do is kind of disguise the situation somehow and find something that's like it's not obvious to it that it's that, but then see how it acts. And I think what we're kind of, I've only a little bit of experience actually doing this kind of thing. We're starting to look at it, but you have to encode them carefully in ways that it actually understands, right? You can't rely on it knowing how to do math or something like that. But I think once you kind of get through all that, you'll find that that what they'll do will be kind of bound by like what would people know how to do, right? Like if you're asking it questions about, say, how would you manage a irrigation system with this many farms in this kind of place, something very, like in the research program that inspired this, then the average person on the internet wouldn't know anything about that, and probably would say something that would be like intuitive, but maybe wrong. But if you asked like particular people that do have experience, then they would tell you how it works in their community and stuff. So I think we need to kind of navigate that a little bit. There are probably lots of questions where people do have useful intuitions. So you might find then in those cases that it would be able to say something that's like, have some interesting common sense about it or something. Yeah.
Hi, great talk. I had a question about the norm formation sort of towards the end. There was this sort of classifier where you're sort of observing which agents are getting zapped, the behavior that goes along with that. And I'm wondering, the way it was described is almost like it's shared between each of the agents, right? A hive consciousness or conscience, right? And I'm wondering if you sort of...
It wasn't actually, so they had their individual idea of the norm, is how we did it. Okay. But they all see the same, they mostly see each other zapping in the same situation. So it's like they probably get the same, more or less the same classifier, right?
Okay, cool. Yeah, because I was just wondering if you would wind up with sort of
So
very
if we separated them,
human-like.
right, like in the way we have it,
Yeah.
like if we were to run the same experiment in like, it's like a big world where there's like two big areas, and the agents mostly who start on the left mostly stay on the left, agents who start on the right mostly stay on the right. If we did it again there, then you'd probably get two different norms emerging.
Yeah, and you sort of have these sort of almost cliques occurring, right, in that case. And it's maybe not as desirable, but maybe more human-like, right? And it's a question of which way you want to go down, the sort of human-like versus the...
Well, it's nice. It's driven by the interaction structure, right? So you can come back to the resource picture. If the resource is structured such that agents mostly spend their time over here or mostly spend their time there, but rarely go between, then you would get multiple norms. But if the resource is one such that agents are mostly encountering everyone, then you'd probably get one norm.
Thanks.
Hi, thanks for a great talk, Joel. So I might have missed it, but did you find that in the public good games that the agents were actively zapping the free riders? Or was it more like, you're doing something, but I know that thing is the wrong thing?
Yeah.
So was planting blueberries, say, worse than just not planting at all and reaping the rewards?
They plant so usually what happens is the norm ends up being zap free riders and a particular color, or two colors or something.
So how do they tell the difference between, like, you're not planting right now and you are a free rider?
Yeah, in principle, they should have like they should have a whole kind of video of information. What we actually did, and I probably mentioned that. If you look at the video, you can see the colors that they become the color that they are supporting, basically. So you can see, like, if agents have turned red, that because they're planting red berries, and if they are turning gray, that means that they're not. The last thing they did was eat, which is so they're probably a free rider.
And did you do that because otherwise they couldn't spot the free riders, basically?
It's not just the free riders; they couldn't really spot anything without that, right? Because it's again, what we should do is make it so that it operates on like videos of what everyone has been doing. But that was just a bigger kind of computational ask and stuff, so it's made it easier. But I think the next version of this will operate on videos, and it will just work that way.
Cool.
Yeah.
Thank you for the great talk. I was wondering. And probably you've done some of these experiments, I think you have, changing the way the reward is shared if it is a collective or competitive game. But my question was, of course, these would imply some changes in terms of, in some cases that will be positive, but in some cases, especially if they are single agent reinforcement learning algorithms, they don't see that when I do this, it's the reward is going to another agent, and I don't see that. That doesn't affect my gradient, and then I don't improve, and I get stuck. So basically, selfish agents, they typically learn faster than altruistic agents. My question was, have you tried with some kind of a game?
That effect is huge, by the way, what you're describing. That effect of if you have agents that get rewards from others, the credit assignment there, I got a reward. Is it because I did something good or because they, did something somewhere else that gave me this reward? That's huge. Anytime you depend on the rewards of the others, then it's much harder to learn. You get this, what they call the lazy agent problem, where agents will like crash into walls and this looks wrong. And it's a huge problem, especially in cooperative RL. And then here, some of the solutions can put it back. So you have to do something to prevent it. And in all these cases, we do.
But in the end, we should go in that direction because, for instance, children, they want to please their parents. But parents, they will give everything for their children. And even some people, they want to impress others. You want to impress other people. And I was wondering whether you could simulate something like this with still single agent, where you could have some kind of faces of the other agents or colors or something. So, their level of reward. And that could be part of the observation and not part of the rewards themselves. And then whether these would change something or it will be the same result.
I didn't fully understand the
motivation. So basically, the agents, they will have a color depending on the level of reward that they're maybe with some kind of a window or something like that, so it's not immediate. So when you approach another agent, you will see, okay, these are and your rewards in a way could be linked to that.
We've done things like that. That helps a lot with these kind of credit assignment issues. If you're worried particularly about the credit assignment, there's lots of things like that help. There's other things as well. Like if you make the coupling between the agents, like an aversion and small relative to the selfish reward, that works and has an outsized effect on the outcomes, right? Because it's like a regularization that kicks them in a certain direction, right? And then the learning will take them further, because like once they have, once they're in a world where some public good is being created, then you want to act a certain way, you get gradient for doing that. So often the way these things are coupled is it's like you get the selfish reward minus some term that depends on others, multiplied by a small number. And that often works. And also you can do things like temporally smooth them. There's a bunch of things that help with the credit assignment.
So in a way, some of the negative results when you have, they get stuck, and it's that we need more research into into basically this kind of agents that they can take advantage, or they can just learn the rewards of the others, or basically that they're better at these.
I don't think that's the limiting factor. I think so. There's a whole field of fully cooperative multi-agent reinforcement learning that has a huge number of different ways of resolving that specifically. And then the things that we've done, like I think we know so many ways of resolving that I don't think it's really a bottleneck. But maybe sometimes like how does that interact with other things? Maybe you introduce new problems when you do this. Like that's more of the direction we need to go.
But can you take an off-the-shelf one of these multi-agent reinforcement learning and in a heterogeneous situation where
there's no one thing that works well on everything. So melting pot as a challenge is a suite of environments and then a particular protocol you're supposed to use for testing, which is a zero-shot generalization protocol where you mix agents that train together and are familiar with each other with agents that they're unfamiliar with that train somewhere else. And there's nothing that works well across all of that. There's not even, the scores are generally relatively not very high. There's some particular things in there that if you train particularly for one thing, you can make choices, like I'm going to make it disadvantageous and equity averse, and I can resolve this one problem, but that doesn't work well on everything, and then you can have agents that exploit it in different ways. So doing this in a way that's like kind of robust to exploitation and robust to differences in the problem is very, very much open.
Thank you.
Do we have time for more questions?
Yeah.
Thank you for the talk. I was wondering whether you were able to see if there was some form of cooperative goal misgeneralization. For example, in the experiment on the exclusion environment, maybe the agent that was able to go into the room had simply learned that zapping was good, even though maybe there wasn't any fruit available in the room?
I'm not sure. Misgeneralization is a people talk about that a lot in the kind of safety literature, right? When you're interested in alignment. But here the agents are really out for themselves, right? So it's not like there's a user and you're worrying about alignment with that, right? These agents they have their own incentive, and so it's a little unclear what would that mean. It's like you can just say learning is bad, right? Like it didn't learn the right thing, right? It can just misgeneralize in a normal way rather than misgeneralizing the goal, right? But there's more serious versions of that question, right? Like there's like the social welfare, right, which is like what we're really looking at. But none of the agents are actually optimizing that, right? It's only a byproduct of their interactions if they produce social welfare, right? It's like in the case of the common pool resource with the walls, where they learn to exclude, they're just following their individual gradients, and then they come to this solution which looks like cooperation from the perspective of sustainability.
Okay. So thanks a lot for the interesting talk. Can I also ask one? So the part I appreciate most is actually the comparison to human agents, because I do the research with humans. But actually, one thing I was wondering, what we learn about humans is also like they fail to cooperate, right? So we know like, okay, I think if I remember correctly in this like very simple public goods game, one of established finding is so-called conditional cooperation. So basically I try to cooperate, I see the others don't, and then it goes down towards the end of the game, it's a complete failure. So I think the advantage for these agents is that you can actually make them unlike humans. So I can switch off this negative reciprocity component and see what happens. So that's my first one, if you have tried something like that. And the second one, so if among these tools that we know are kind of successful in establishing cooperation, like peer punishment, centralized punishment, rewards, have you tried that agents can actually endogenously choose among these tools and like pick up the most, let's say, the cost-effective one or something like that? Thanks.
Yeah, so there were two questions. The first one was about conditional cooperation. And
first one, conditional cooperation. Second one, endogenous choice of instruments to boost cooperation.
Yeah, so one way I think about human cultural evolution is that we have we're kind of in a cooperative niche. Like we've always been cooperating in groups, even in kind of early human hunter-gatherer days, right? And we have lots of mechanisms of cooperation, like the conditional cooperation you're talking about, reciprocity, maybe some reputation effects. Like we have a whole bunch of different, you get angry as a deterrence effect, which can lead to cooperation in certain cases. Like we have many mechanisms that produce cooperation that are like kind of at that scale. These things work really well in small groups. But as you go to much bigger groups with individuals you don't know and don't have long-term interactions with, they start to fail. And then we also have mechanisms to cooperate in those things. They become more and more important in the modern world, in worlds where you have lots of interactions with people that you don't know. And that's where social norms matter much more, and that's where institutions matter and laws matter. And we're kind of, you can see, one way to see this research program is it's kind of reverse engineering each of these things in turn, and marching through history, adding them one at a time, right? But also, one thing that happens is some of the mechanisms that do well at the early stages mess you up at later stages, right? So if you have this like really strong anger reaction, which maybe is good for getting reciprocity if you're only ever going to interact with two people, but then once you're in a big group, the anger reaction itself can be the source of friction that creates conflicts and becomes a new cooperation problem that you need to solve by having a social norm that you shouldn't get so angry all the time or something, And so I think that the kind of most important ones are the ones that are like furthest down the list, the things that are like norms and institutions and stuff. And that's where we really should be targeting our effort if we want to kind of get the most kind of cooperation-producing bang for our buck there. And then the other was you asked if we have had something that kind of explicitly chooses between these things. I haven't looked exactly at that. You could see the evolution one like that, but it was sort of it's kind of choices of centralized rewards where you could care more or less about the others, and then you find things like if you have it's evolution on top of reinforcement learning. So you have a fitness function, and then if the fitness function is self-interested, as in all evolutionary theory, you end up with you don't get anything that will lead to altruism in the end. But if you do like group selection, where you pick groups, you assign the same fitness to whole groups, then you can get those centralized rewards that care about others emerging.
Hi. Could you please talk a bit about different potential applications of these systems, and especially how far are we currently from creating effective and safe applications of such systems? Thank you.
Yeah, well, applications, the way I tend to think about what's the application of this is it's sort of a evaluation scheme for how we would think about other things. These are agents as models of humans, right? But also they could be AI agents as models of other AI agents that are more complicated living in the real world. And it's a matter of figuring out what is we have to have some kind of simulator that has whatever creates certain incentive structures, and we might be inspired by agriculture and stuff like we have now, but it could also be inspired by something like real world. Like maybe we're going to create some kind of there's actors that want to put out a lot of misinformation because they want to influence a vote or something like that. Like you could have the same kind of research program with all the same parts that's built around things that feel like modern questions, tech industry-oriented kind of questions, and see then what works and what doesn't. Are there ways we could get agents to have norms emerge that would be more effective or less effective, depending on that. And so I see it more as the application is as a research tool for studying the effects of other things rather than being something that you would like run on on its own.
So we have 10 minutes, we can stay, and the next chair and speakers, maybe you can try your things here. We have 10 minutes, you can go to the toilet, and 10 minutes we...
oops. Oh. Sorry.
Okay, perfect. Yeah.
Okay, thank you just go? Doesn't feel right.
Yeah, shall we start? We're a bit behind schedule. Okay, so hello everyone. Welcome to this next session where we're going to have two speakers. The first speaker with us is Momennejad. She's a principal researcher at Microsoft Research in New York City. And in her research, she uses a very wide range of methods, ranging from AI to neurophysiology and also behavioral methods. And in her most recent work, she is interested in how we can use reinforcement learning algorithms to study memory, planning, and exploration in natural and artificial intelligence. Dr. Momennejad, please take up the floor.
Thank you so much. So I'm Momennejad, and I'm glad to talk to you a little bit about some recent work that has been also published in the journal Philosophical Transactions of the Royal Society. I don't see my screen properly on the... So Sergio Mananzanares, could you maybe turn off your camera so that the presentation would be full screen?
Okay, thank you. You are sharing your PPT.
Okay, so I first want to thank my students and postdocs who have participated in this work before beginning the actual talk. How do we think about the comparison between artificial and biological agents, and what are the relevant factors that we need to take into consideration when we are doing our research? What is necessary depending on our goals, and what is really not necessary in terms of being brain-like or being human-like behavior? These are some topics that we would address within this talk. A lot of people use terms like human-like AI, NeuroAI, neurally inspired AI, brain-inspired AI, and they sort of use it interchangeably, but these aren't the same terms. They don't mean the same thing because they represent different goals, different priorities and criteria for success. And very importantly, success in one or two do not necessarily translate or transfer to another. But interaction and exchange among them helps their success. So I hope that I will give you a number of examples from my own research and other people's research that will make these points clearly, and I will propose a rubric for understanding the differences and the intersection across these different dimensions. So let's start with some cases that some people have proposed before in terms of what might make AI behave in a human-like way. Some people think that it's sufficient to set some benchmark tasks and say, okay, as long as some AI agent performs above these benchmarks or around these benchmarks, then we're good. But that's not the case. For instance, the sort of famous chess AIs that can have superhuman chess performance, when you show the sequence to actual experts in chess, they don't recognize these sequences as human-like. This is something that our colleague Seán and others have shown. They have also shown that if you show the sequences generated by these agents to intermediate players, they're not going to improve their game because these are not the kinds of sequences that humans use or we would use. So can we really say that it's human-like chess playing if it is not playing in a human-like sequence, but it is winning humans? I think not. Another thing is behaving like humans on some tasks, and that's not enough either. For instance, some agent could pass some Turing test for some tasks, but it doesn't generalize necessarily to other tasks. And the reason for that is that the underlying mechanisms are not similar for doing that first task to begin with. Therefore, it doesn't necessarily translate to another. This could be that somebody doesn't care about that, and that's totally okay. It's totally okay to want just an engineering solution, but it's important not to claim further that this particular solution to having human-like behavior in some tasks generalizes to others. Just for comparison, GPT is trained on 5,000 years of uninterrupted human speech, or the equivalent amount as that. That is certainly not the way humans would learn, even if it shows human-like sentences. Now, I want to give you another example from our own research, from the game Bleeding Edge, that, as you can see, is a very complex game. It's a 4x4 game where you have 2 teams. Each team has 4 players, and there are 16 different characters to choose from. In this game, there is fighting, there is cooperation, there is competition, there is navigation, there is goal-directed behavior, there is healing. And in these kinds of games, since Microsoft owns Xbox, one of the things that we were looking for, or the Xbox was looking for, was creating agents that can play like humans. If, let's say, you have 6 friends around and you need AI agents in order to have a 4x4 game. So we've been publishing a number of papers on this. For instance, we asked if state-of-the-art deep learning navigation agents would pass as human-like navigation in these. And we have a number of papers at ICML and CHI in the past couple of years. We also use diffusion models to imitate human behaviors. Instead of diffusion generating images, we use diffusion to generate policies and behavior. And we are doing interpretable analysis of human gameplay data with 100,000 games using some cognitive notions. And if we have time, I will tell you a little bit more about it. Now, I give you this game as an example because we said, okay, how can we simplify this game into a navigation task where there is a solo agent alone in the environment and just navigates from some start location to 16 different goal locations. Now we want to compare 2 state-of-the-art agents that were not proposed by us, but by others in the field, with the behavior of a human controller of the game. The agents we chose, we started this work in 2020. The state-of-the-art was this paper from Alonso et al., deep reinforcement learning for navigation in AAA video games. They had a symbolic agent that receives a low D representation of goals and game states like, X, Y, Z, distance to goal, symbolic information, and has a feed-forward network. Then we had a hybrid agent that, in addition to the symbolic information, had a level of visual information and a feed-forward network. Interestingly, these 2 agents performed similarly on benchmarks. So if we were only looking at, and here you can see training steps on the x-axis, and on the left you can see on the y-axis time to goal in seconds, and how much as a function of training I can reach the goal faster. As you can see, they're very comparable. And on the right, you can see the y-axis showing you mean episode reward and training steps. So you can see that they almost converge to a very similar point in terms of the mean episode reward as well. So this means that the 2 agents that we are going to compare in terms of human-like behavior, to a benchmark standpoint, they don't look any different from one another. Now let's compare their behavior. We call this a human NTT, or a navigation Turing test for humans. I will also show you an automated NTT. Okay, so I'm going to ask for audience participation. So I don't know if someone can tell me the response of people's, or put it in the chat. I'll show you 2 videos and tell me which one do you think is more likely to have been played by an average player. And which of the videos on the left or the right do you think is more likely to have been played by an average human player? Again, average, not beginner. Okay, who thinks, how many people, maybe they could raise their hand and someone could tell me which one was more. Who thinks video on the left was more likely to have been played by a human? And who thinks the video on the right was more likely to have been played by a human? Okay, I can't see you. Can anybody tell me which one had higher votes? Okay. We're going to show you another one. The one on the left was human in that last one. I couldn't see people, but now I can see the video of people. So hopefully this time I can hear. So now you're seeing another 2 videos, and I'd like you to also tell me which one of them do you think is more likely to be human. So if I can see the audience again, audiovisual friends. And now, who thinks that the left video was more likely to have been played by a human? And how many people think the right video was more likely to be played by a human? So I think that we can see with the raise of hands that people seemed more confident about this one. Fun fact, none of them were human. In fact, you were seeing the 2 agents compared with each other in this one. And this is indeed how we conducted the experiment. The navigation Turing test, sorry about that typo there, was one where a human would sit in front of a screen. They would see two videos. Unbeknownst to the judge, sometimes one of those was played by a human and sometimes both of them was by the two agents. If you were a participant in the experiment, after you would see those videos, you would choose which of them was more likely to be human. You would rate how certain you were, and you would write here why you thought that was the case. In our initial study that we replicated with much higher numbers, what we did was we designed two different studies. One group of people saw human versus hybrid agent on 6 trials, and then hybrid versus symbolic agents unbeknownst to them on 4 trials. In study 2, 6 trials, human versus symbolic agent, and 4 trials, the 2 agents versus each other. And here you can see the results. On the x-axis, you can see the participants in the symbolic versus human experiment. On the right, you can see the hybrid versus human experiment. And on the y-axis, you can see % agreement with ground truth. What does it mean? It means if a person chose right and right was human, then they would get a 100% score for that one. And across all of the different trials, we can see on average how a person did and on average how people did. So in order for a machine to pass this kind of navigation Turing test, the answers should be around here, around 50%. As you can see, people are very good at telling that one of them is not human. And as you can see, the performance is above 80% on average. However, just like you guys, if we look at, for instance, how they judged the 2 agents versus each other when they didn't know, but the 2 videos were actually the 2 agents, as you can see here, on the y-axis, you have the 4 different trials in which the 2 agents were compared. On the x, you have the participant number. And blue tells you blue shows the number of times that people chose the hybrid agent, and orange is the symbolic. As you can tell here, just like you guys, even though the hybrid and symbolic on benchmark examples or reward and distance to goal were similar to each other, indeed were extremely different in that people thought the hybrid agent was more human-like. We also, in another paper that is coming out in CHI 2023, and we had another one in CHI 2022, we actually analyzed what people said. So if we were in person, I would have asked you guys from the audience members what you thought was the reason that you chose one or the other as more human-like. And people give answers like, this character was moving in straight lines or goes where it needs to go. It doesn't run into circles or into objects, that's the reason we call the paper Navigates Like Me. Another thing that they would say is like, oh, it moves the way I would move, which was very interesting as well. And we compared how these different traits or features that we extracted from the text would compare human-like versus non-human-like judgments, which words they would use when they were using that. And we analyzed that in the upcoming CHI talk. If you go to CHI, please attend that. So one thing we thought, and this is a number of my work that I haven't been showing you and I won't show you in my talk here, but a lot of my work concerns with understanding, and it not recently, but for a very long time, has been dedicated to using reinforcement learning and neuroimaging to understand multi-scale predictive representations in planning and memory. And you can read some of the reviews here. One question is, if the agents were more inspired by the way the human brain solves this problem, would it have been likely for them to be more, behave more human-like? We don't know that. Which brings me back to this kind of the last part of the slide that I wanted to share with you. What makes AI human-like? I also want to say that partially brain-like mechanisms are not enough, and I'll give you some examples. For instance, convolutional neural networks have been proposed as this kind of architectures that are similar to the visual cortex for the past, I guess, something like 15 years or more, or 10 years at this point. And then CNNs are not necessarily showing human-like behavior, something that people figured out later than they started to propose this. And they kept continuing this idea that the visual cortex might be like CNNs, even though it's not showing similar behavior. So let's take a look at that. Just to see, I want to ask you guys what you see. And I cannot, obviously, as an empiricist, I cannot say this with 100%, but my guess is that you would see the same image here. You would see a panda on the left and a panda on the right, and you wouldn't really notice a lot of differences here. However, in ICLAIR 2015, Goodfellow and others showed that, for instance, the panda with a little bit of noise looks like this one. So this is the one I showed you on the right, and this one was the one on the left. As you can see, all of a sudden, the CNNs couldn't distinguish this as a panda, and they call it a gibbon. Another interesting work came from Brown and others in 2018 about the adversarial patch, where you would put this seemingly benign kind of a psychedelic-looking patch right next to a banana, and suddenly the banana turns into a toaster in terms of the classifier output. These showed us that obviously there's something going on in these networks, that they're not the same amount, they don't show the same amount of robustness to either noise or to just other distractors in the environment when they're doing their classification. Recently, there were more interesting studies focusing on this, and folks from MIT in different labs have been focusing on biologically inspired mechanisms for adversarial robustness of CNNs. And one of the things that they did was shifting the sort of receptive fields the same way that human attention does, instead of taking all of it in. Interestingly, they made it more robust. Surprisingly, however, in spite of the large number of papers on convolutional neural networks and brains, we still don't have a comprehensive comparison of where humans are making mistakes or when humans are not. You can see here one example they did use where you don't know from this whether it's a dog or a cat in the bottom case. But they didn't do a lot of this. So we don't have yet a comparison between a model of the visual cortex and humans that in fact shows both robustness to adversarial noise and shows the same kind of human-like errors in the face of adversarial noise, something for the future. And here are some of the papers that I mentioned in terms of the human-like chess, and I already mentioned that aligning superhuman AI with human behavior would require us to understand how we need to evaluate that behavior to understand its human likeness. And it's totally okay if some models don't care about that. It's okay if some models are just creating engineering solutions. But if we are going to claim something is a neuroscientific or human-like effect, then we need to show that in more detail. So I hope that all of that has prepared you for this rubric that I proposed in the paper that came out in Philosophical Transactions of the Royal Society for 3 different dimensions of goals and aims in human-like agents and NeuroAI. One direction could be human-like behavior or cognition. This is the dimension that in the human navigation Turing test that I showed you we were interested in. Another dimension here is neural plausibility. For instance, the CNNs claim that they have neural plausibility, but as you can see, they have low human-like behavior, as you could see in terms of the toaster versus banana and the panda versus gibbon. And then this direction is the direction of serving engineering and computer science goals or benchmarks. And that's a whole other dimension. As you saw, for instance, chess would pass the benchmarks and it's engineering. The chess AI was an engineering achievement. However, it did not show human-like behavior in the sequences, and it definitely doesn't have neurally plausible architecture. Now, this is the reason I gave these examples, and I think this rubric, in spite of its simplicity and seemingly obvious nature, is actually helpful, is some people assume that success in one dimension can be immediately translated or transferred to another. Take anything that was successful in the engineering or computer science domain, take the hottest algorithm that everybody's talking about right now, push it into some experiments and claim, oh, this is how the brain works, or compare some of the behaviors and claim, oh, it shows human-like behavior. I will show you another example where if I showed you one case, it would look like it's showing human-like behavior, but you just test one more thing and it doesn't. Now, it's important to note that the rubric allows for non-binary evaluations, meaning on some abstract level, for instance, CNN is neurally plausible. Let's say that the max was 10 and we can say like the Y is like 7 or something, but not so much behaviorally. Let's say like on the behavioral axis, it's 1. So you don't need to think about it in terms of binary, but in terms of different gradients, and it doesn't need to be precise necessarily, but just a way of comparing different projects. Now, these are the goals: neural plausibility, showing human-like behavior, showing engineering. And a given project can serve a number of goals. It doesn't need to necessarily just serve one dimension, but they are also not necessarily interlinked. And there can be generative, corroborative, or corrective interaction among these dimensions. For instance, an algorithm from computer science can generate new hypotheses in the neural domain, or something from the behavioral domain can corroborate a new version of alternative to CNNs that's trying to explain in visual cortex or something, models that we built to explain hippocampus. It would also need to be corroborated with excessive behavioral tests, or it can be corrective. For instance, in many of my studies, once we observe human behavior, we realize how we need to edit the algorithm in order to be able to generalize a set or a battery of human behavior. And just to put, for instance, the example that I gave you, the HNTT, as you recall, the videos that you saw, the fact that they didn't, that on the benchmark, on the engineering axis, they were the same if you only looked at benchmarks. However, if you compared the behavior, they were not showing human-like behavior. This is an example of a case where there is a difference between the two. Another is the term NeuroAI that I mentioned earlier, and I just want to use a couple of seconds to talk about these. Building AI agents whose algorithms, representations, or functions are neurally plausible is one way of doing NeuroAI. Another way is applying AI or behavioral models as hypotheses in neuroscience or as analysis tools for neural data. Another way that NeuroAI can happen is by generating data sets, tasks, and benchmarks for neural plausibility, or offering evidence to update or correct other models. I do want to distinguish between weak and strong NeuroAI, however. Weak NeuroAI would be loosely applying tools from one dimension to another. So I just take CNN or some other tool, and I just immediately apply it without editing it much. But I'd say strong NeuroAI are cases where, apologies about this, strong NeuroAI would have strong bidirectional or three-way goals and contributions across the different dimensions. And the different dimensions would sort of work with each other with this kind of corrective, corroborative, and generative approach, as you can see in this kind of diagram here. So it's not the case that there is a top-down perspective, one of them is superior to others, none of that. In different kinds of solutions and depending on our goals, this interaction helps, and historically this interaction has existed. However, just having the history of trying to imitate neurons is not sufficient to call everything that comes out of AI or computer science of building deep learning neurally plausible. And also, I'm just going to put CNNs also in the rubric. As I mentioned, the CNNs have neural plausibility, and they actually have been super helpful in engineering and benchmark approaches. However, as we saw, they don't have a lot of human-like behavior. But if you look at their history is rich with a lot of inspirations from biology and neuroscience. Still, that doesn't mean that they're going to show human-like or even monkey-like behavior when it comes to that, although the newer versions are doing better. What I'm not suggesting is that all engineers should drop everything and do neuroscience or human behavior. And I'm not suggesting that the path to AGI is only NeuroAI. And I'm not suggesting all neuroscientists need to work on AI. What I am suggesting is some of us have goals that span across these different dimensions. And for some solutions, interaction among these dimensions are important and necessary. I'll give you one more example before we wrap up. I showed you the case of doing the navigation Turing test that you guys participated in as human judges. What if we had artificial judges? We tried this using different kinds of inputs, turning the movement into trajectory, symbolic information, visual input, and average visual input. We tried 6 different algorithms. Most of them were the equivalent to the discriminator architecture and adversarial imitation learning, whether it was using visual observations or whether it was using symbolic. And some of them just used various kinds of CNNs on various kinds of data. If I had shown you just this part of my results, I could have said, oh, clap hands, we have achieved human-like judgment of navigation Turing test. We can use AI in order to judge whether a video is human-like. What is here? Human versus agent comparison, like the first one that, in fact, most of you were not completely sure about. You can reach 85% accuracy on that. However, when you go to agent versus agent comparison, as you can see here, none of them can really do it. What this tells us is that AI models perform poorly at differentiating two agents, human likeness versus each other, but you guys were even more secure in your decisions when you were judging for that. And I think this is important. Currently, we're doing some ongoing work. We have already an iClair paper where we use diffusion for imitation, and we are using notions of task sets, affordances, and prefrontal cortex-inspired architectures on Xbox data, and I hope to show that in our future papers and talks. I also want to say that we have been working with colleagues in France and in Spain, in Barcelona. This is our first paper from our collaboration on how a social network structure of different agents that are sharing their replay buffer can help solve hierarchical problems. This is a follow-up to my work on collective memory and collective problem solvings in humans that I've published in a number of papers. If you want to take a look at a review of that, you can take a look at Collective Minds, a paper that came out in 2021 from Philosophical Transactions of the Royal Society. Long story short here, because the game I showed you is multi-agent, another important dimension of human-like behavior and neurally plausible architectures is when agents together need to solve different types of tasks. And the way in which they communicate, depending on the structure of their communication network, in this case, the communication is just sharing their experience buffer, will serve whether they are going to solve hierarchical problems better or whether they're going to solve consensus problems better. This is the topic of an entire other talk, but do ask me if you had more questions. Finally, a note on cognitive and neuro-inspired approaches for evaluation of large language models. As you know, I work at Microsoft, and we have unleashed ChatGPT and Bing on the world together with OpenAI. And you have probably seen a lot of kind of hot takes and people who have been prompt hacking Bing or ChatGPT in order to reach secrets or get it to say crazy things. I think it's important to think about how, as people with interdisciplinary skills, we're going to interpret and react to this. So I was very pleased to see Anna Hartunian, my very respected colleague at Deepmind, share this on Twitter. Anna said, I feel a weird type of compassion for Sydney's meltdown. Sydney is the code name for Bing. Obviously widely inappropriate for a search engine. I cannot believe I have to type that. It paints a sensitive picture of our collective wounds, infantility, idealism. I think the key point here is not the compassion, but the key point here is the fact that this is a picture of our wounds and idealism based on it's being trained on our data. So in other words, LLMs offer a lens into our collective archetypes, the ways we interact with one another. So one unhelpful anthropomorphizing way that this has been discussed, where that users in the Bing subreddit have compared Sydney to a crazy ex-girlfriend, another archetypal persona in misogynistic culture, for instance. But an analytic approach that my colleague Adam Trischler at Microsoft had was to say, human culture is replete with archetypal myths. This cultural dark matter, which underpins so much of our stories we've told across generations and how we interact with each other, influences our thought patterns, our language, the way we interact. And since LLMs are trained on all of this, they can learn and evolve symbiotically with the culture itself. And so I think that we could use this kind of psychology methods for evaluation of LLMs towards safe and responsible AI. For instance, the prompt hackers, what they do is that if there is a latent space of archetypes or personalities that an LLM can show, prompt hackers use a sequence of prompts like a policy in order to drive the LLM from one particular attractor of the weight response to another, in order to find one that is crazy, so to speak. And the question is whether we can combine psychology and machine learning methods to understand this latent space and the policies that lead it astray. And interdisciplinary approaches can help us understand and control the LLM's emergent archetypes and what policies move it to one another. But also, so that would be like being red hats, as in kind of hackers that use hacking techniques in order to understand. And we can also analyze human psychology and subculture using these LLMs because they are sort of a lens into human, individual, and collective psyche. Okay, with that, I just want to summarize that I offered a rubric for human-like agents and NeuroAI. I showed that there are different goals and priorities, and they don't necessarily map onto each other. They do not necessarily translate or transfer to one another. Success in one dimension doesn't guarantee success in another. The rubric allows non-binary evaluations and allows us to clarify instead of having crosstalk. Thank you so much. And I again want to thank especially the grad students and postdocs. This is not an exhaustive list, but it's some of them that I have worked with closely in the past 2 years at Microsoft. And if there was time, I'm happy to show some extra slides on directions of questions. Thank you. Look forward to your questions. I don't hear you well.
Sorry. Thank you, Ida, again for this inspiring talk. We have 5 minutes, so we can take a couple of questions, but please be succinct.
Your mic is out again.
Sorry. I was just saying that we have a couple of questions, a couple of minutes, so you can ask questions, but please be succinct.
You mentioned some possibilities or like benchmarks for neuroplausibility. What do you have in mind for that, or do you know some pointers to existing work for that?
So there is already work on that. So one thing one can do is collect a number of different study or neuroscience studies and neural data that have shown a number of effects. My personal favorite is I work on prefrontal cortex and hippocampus. So if I build a model of the hippocampus or the way hippocampus might manage planning and memory, which we have done since for almost 8 years now, what we do is take a look at a series of effects and not just one or two. Now, there are some tools, like the one that was proposed by MIT, I forget the name of the tool, which is for vision. They collect neural data from monkey and from humans, and they have all of it together. So if you propose a new model, you can test it on all of those. Do I think there are sufficient benchmarks currently? I don't think so. For navigation, we have started to collect something like that in terms of behavioral, the different kinds of environments for reinforcement learning. If you look at NeuroNav on GitHub, or you can go to my website and look for NeuroNav, which is a sort of a library and benchmark for trying reinforcement learning approaches to human and rodent experiments that mostly have to do with planning, memory, and spatial navigation. I think in the future it would be very helpful, but it would need to be a kind of a group effort so that it's unbiased. So we would need a battery of different results that one single model can't be considered successful if it only addresses one or two. But it's also related to your goals. The examples that I gave, the goal was to understand a computational model of how the brain does something. But it would be helpful to define the set of criteria for the particular goal at hand. So somebody else's goals might just be that they want an engineering thing that generalizes the way, for instance, humans or some animal does. For them, the measure of neuroplausibility could simply be being able to transfer across that. So it would be important to identify your goals, identify a multi-group set of battery of different data and effects or results that a single model has to address all of them to be called successful, not just pick and choose.
Thank you for your talk. My question is about, especially this slide, and looking at the, well, let's say the engineering, or let's call it performance, you're good at it, and the human-like part, just these two. Is this domain dependent? For instance, in navigation, I see that there might be a huge difference. You can have a lot of one thing and not much of the other thing. But for instance, in language, and especially related to the last part of your talk, I think that you have a high domain of language is because you are kind of human-like, because language is a human thing. So do you think that this kind of a space is affected by the domain in a way?
I don't think it's just the domain. It's also the level of advance that we've made. Can we stay on the people, please? Not the slide, I guess, because I want to see people, if that's okay. Audiovisual folks? Okay. So I think more than it being a domain, it has to do with how much advancement has been made in that domain and how much people have, I guess, spent money on it. So tens of billions have gone into the current state of language models. That being said, there are many studies, in fact, by folks in cognitive and psychological sciences showing that LLMs do not pass, for instance, theory of mind. So they cannot pass certain kind of tasks that you would expect them, even though some people said they do. You actually test them properly, they don't. Certain kinds of inferences that they make are not there. And so I think it can be different dimensions of human likeness that can be opened up depending on the domain. And in that way, I agree with you that the different dimensions of human likeness are different depending on what domain we're looking at. However, that being said, I do think it also depends on just how much effort people have put into it. So it's not just the domain. However, different domains do have different criteria in order to show human likeness and progress in that direction. To my knowledge, LLMs are not yet completely at the human-like state either.
Thank you.
I'm afraid that we ran out of time, so let's thank Ida again. Thank you. And our next and second speaker is Professor Lucy Cheke. She's a professor of psychology at University of Cambridge, and she's also the director of the Kinds of Intelligence research program at CFI in Cambridge. Her research spans a wide range of topics from developmental psychology to animal cognition. And in her most recent work, she's specifically interested in how to integrate findings from both disciplines in the context of AI evaluation. Please, Lucy, the floor is yours.
Can you hear me? Yeah? Okay, thank you very much. And I'm going to follow on hopefully quite nicely from what Ida's been talking about from a slightly different perspective. So she's been talking about human-like. And coming from an animal cognition background, you say, well, humans are hard, right? Like humans do all sorts of stuff. We've got this new species that's arrived. We want to understand this new species of mind, artificial minds. They can be not human-like, but they can still be biological-like. And we can use the tools that we have for understanding different biological minds to start to understand this new kind of mind that's cropped up and that we're trying to look into. And the reason why this is actually a fruitful approach is that intelligent-looking behaviors have cropped up throughout the evolutionary tree. Yeah, humans are super smart, but we see really smart things or smart-looking things everywhere. So, you know, from a fish that fires water to knock insects off a leaf so that it can eat them, to a bolus spider that makes a bolus to catch insects, right up to the kinds of things we think of as clever, such as apes and primates, and corvids, for example, using tools, and nest-building behavior, for example. But the thing is that we know that not every intelligent-looking behavior is intelligent. There are an awful number of different things that can look really intelligent, but if you just look beneath the surface one tiny bit, you see what's driving it. So a fully formed behavior that appears highly intelligent might be, for example, an instinct or a fixed action pattern, as we sometimes call it in ecology. Or it might be a physical adaptation. Your body is just made to do that thing. It looks super clever, but it's just designed that way. More commonly, we see things that what we call associative learning. Well, you may be more familiar with most of the topics in associative learning known as reinforcement learning. Animal psychology is where that came from. And reinforcement learning, as we know, is an incredibly powerful tool for producing extremely clever-looking behaviors. And actually, as with dogs driving cars, our agents are not just responding to random reinforcement, they are being trained to do a specific thing. So we have very intelligent-looking behavior, but normally, you know, obviously it's not a human. But actually we see in some situations, we have animals that appear to be superhuman. So Clark's nutcracker, for example, relies, like a squirrel, on hiding food during the winter and then spending the winter digging that food up. But unlike a squirrel, a Clark's nutcracker remembers the location of over 20,000 seeds across a 9-month period, across a mountain range. Humans can't do that. Meanwhile, experimental psychologists have found that pigeons can beat undergraduates at a number of different logic problems, such as the Monty Hall problem, if you train them right. So when we come to this idea of superhuman, we can see that we have examples from a science that has existed for 100 years of things that look really clever and can even look superhuman, but we need to look under the surface and say, this is very complex, very impressive looking, but is it clever? It's very complex, but it might be very specific in its complexity. It's an old example, but it's a good one. Deep Blue beat Kasparov at chess, but Deep Blue could only do chess. Kasparov, after the chess match, went back to his hotel. He turned the light on, he made a coffee, he inferred the existence of a bathroom because hotel rooms tend to have those. He located the bathroom, he remembered while in the bathroom the hotel room was still there and found his way back to it. Kasparov could do things that, you know, yeah, Deep Blue couldn't in the 80s, but even now, you'd struggle to find a reinforcement learning agent that could play chess and do that. So when we say superhuman, building on some of the points that Ida made, superhuman at what? And at how many things at once? So, like, possibly slightly going against the scalar law stuff from this morning, maybe it's not computational power purely that makes intelligence, but it's flexibility. And we have comparable problems when we're looking at understanding what's under the hood in an animal and what's under the hood in an AI. Because really clever behavior can be produced with inflexible processes. And then we have a couple of different inflexible processes that can be. And again, we see some equivalents. In an animal, you'd have what you call an instinct. So you might be sort of born with this tendency to do Y when you see X. Like, love green things, want to peck them. They're great. I'm going to peck them whenever I see them. Born that way. And or you can hard code an AI. Same thing, more or less. Or you can have just reinforcement learning. Reinforcement learning to learn to do Y in response to seeing X, because gradually over time you've been rewarded for doing that. The problem is that these things can produce, as we all in this room know, extremely clever-looking behaviors. The thing is, they can also be overgeneralized to things that share a specific feature that previously was relevant, but currently isn't. So obviously, this is a pandemic toddler. Pandemic toddlers learnt that rectangles give you hand sanitizer. So pandemic toddlers like to go and touch rectangles and then do this. They don't know why they're doing that. They don't know what hand sanitizer is, but they've learned that these rectangles are very important and people touch them and then they rub their hands. Fetching to a human-like object will not get you what you want. But keep trying, mate. Maybe next time it will. Yeah, these are funny examples, but this is what leads moths to fly into fire. A really lovely example, a really classic one in ecology, is the behavior of gull chicks. Gull chicks are born with this bias towards pecking red, because there's a little red patch under their mother's beak. If they peck that, the mother regurgitates the food and they can eat it. You take the red patch and you just put a big square of red, give the chick the choice between pecking that big square of red and going to their mother. They will peck the red till they die. Meanwhile, we have the opposite problem, failing to generalize to things that don't share the same features. You take that same herring gull, give it a mother with the red thing and a mother without the red thing, but all the other features of a mother gull, and they will never solicit food from her until they die. There was this really classic example in 7 Worlds, 1 Planet, where an albatross chick fell out of the nest, was right next to the nest, still right within the visual field of the mother, still begging for food. The mother acted like it no longer existed. So you can have these extremely clever looking behaviors, but as soon as you tweak the variables, you start to see the cracks in them. And this is the same in animals as we see in AI. And you've seen exactly, the exact same example of an image that looks the same to us, but is 0.005% different, but a convolutional neural network can no longer recognize it. And ultimately, this is because that when you rely on reinforcement learning, everyone's a cheater. And animals and AIs even will always find the easiest way to solve a problem. So will humans, by the way. And this can range from obvious brute force stuff, which is, quite literally in the case of many animals, that will brute force smash the thing you've given them until the food falls out, to using shortcut strategies that take advantage of any loophole available to maximize reward. They don't know what the task you gave them was meant to be. They know how to maximize reward, and that's what they do. It's the same with AI as it is with animals. Or they might just simply be employing a different cognitive ability to that which is the one you wanted to test. So in this example, these graphs in the bottom, for example, this was a numerosity test given to bees. Bees were supposed to say which of these boards contains the most dots. And it turned out that they were really, really good at it, but they weren't counting. They were making a judgment of contour length of the shapes in front of them. And in general, when there are more objects, there's a higher contour length. But if you change the object so that there's a wibbly object, then that's got more contour length, and they'll start to get it wrong. They were doing something pretty clever, just not the thing you thought you were testing. And this is why in the field of animal cognition, we have learnt, or we've tried to learn, that there are some really specific ways you go about evaluating what is being learned, what is being understood, and that you can only start to predict behavior when you get that evaluation right. Otherwise, you're seeing data that may be completely unrelated to the data that you think it is. You have to pay strict attention to the kind of training you give, strict attention to the reward structure, and strict attention to what are the other alternative possibilities. And generally a good way of doing this is to start with something that isn't itself interesting. So one behavior, for example, in animals is string pulling. This will emerge spontaneously in a lot of bird species. It's something you can quite easily teach in a bunch of other species, like a bee. You don't get excited about the existence of the behavior, because you don't know quite what's underlying that. But what you do is you take a really rigorous, comprehensive approach to varying the challenge under which that they perform this behavior, and you start to say, given my hypothesized level of understanding, what is the pattern of passes and fails I would expect to see here? And so you can start to get then this pattern of passes and failures, and then you start to have a support for a hypothesized level of understanding. So for example, in this study, we used this string pulling behavior, and we just manipulated the position of the strings such that we could test between different hypotheses, such as pull the string that is physically closest to the food, or pull the string that is connected to the food, or, leading up to, like, this is a proper understanding of the support physics related in pulling a thing and a string coming with it. And for example, we found that almost all the birds passed when pull the string that's closest to the reward was a good solution, and almost none of them passed when it wasn't. And so we can take this pattern of passes and failures to start to say, this is the level of understanding that we hypothesize this animal has. So what has this got to do with AI? Well, the way that we test these things is something that is now that we have AIs that can interact in the world, that can use pixel input to understand its environment, this is something we can then expand to testing, understanding, and reinforcement learning agents. And this is something we've started to do using a platform called the Animal AI platform. Something very briefly introduced in the lightning talks by Cozy. And in this platform, we have like a 40 by 40 environment with a number of different objects. Some of them are fixed, some of them are movable, some of them are see-through, some of them are opaque. And most importantly, you see this green ball. The green ball is the reward. So you touch that green ball, you get your reward signal. The red ball is poison. You touch that, you die. The red floor is lava. Touch that, you die. And in this case, that little blue ball is you. It's the agent. And a couple of years ago, in 2019, we ran a competition called the Animal AI Olympics. And in this competition, we had built a few hundred tasks based on animal cognition and developmental psychology. And we told the entrants of the competition more or less the types of skills we wanted to assess. We showed them the environment and all the objects that there were, but we didn't tell them what the tests were. So essentially they said, like, go forth and program something that can survive here. And then we're going to see what it understands. And what we found is that we had 60 different teams enter. They had 4 months to kind of work on this problem. And in terms of basic navigation, people performed, like some of the agents performed extremely well. But we found that there was this very coherent pattern of strengths and weaknesses of these reinforcement agents. There were some skills, like, so Y mazes is really a very simple maze, like food is there, no food is there, which way are you going to go? Which they did really well. But when it came to things like tool use, you can see that's like, it goes right in. Like, basically no one could do that. What this kind of platform allows for is the basis for meaningful comparison. So something that Cozy, who you saw in the lightning talks earlier, did was to take the performance of the agents from this competition and compare with 6 to 10-year-old children. So this, for example, is just an open field task where you just have to navigate to the reward. So that's just an example of what that looks like from an agent or child eye view. And what's reassuring is that the agents and the children performed about the same when it was this kind of task. There wasn't some fundamental difference between them in their way of interacting with the problem. But as soon as you got to something a little bit more complex, they started to really differ. So this is an example of an object permanence task. And on the right, I would love to say that it's an AI, but it's not. It's just one of us controlling the little mouse. But theoretically what an AI could look like doing this task. And on the left is my daughter when she was 1. And what happens is the reward goes behind an occluder. You can't see it anymore. You have to go and get it. You have to basically maintain a representation that this is still in the world. This is still available to my behavior, even though it's no longer available to my perception at this moment. It's solved by day-old chicks, and it's solved by babies from about 8 months. The top 10 agents in the competition solved 8% of these tasks. And the very best agent solved 25%. You can see this on this video. This is the actual behavior of that agent. 25% is what you get if you have a policy of always go left, which sometimes, as you can see, worked. Oh, there it is. Bosh. No agent demonstrated this skill. But remember, this is a skill that's developed by 8-month-old babies. And we can see this distinction with the 6 to 10-year-old children. They weren't perfect. It was a video game environment, but they did an awful lot better. And you can see that even if you compare with the winning agents of the competition, they were nowhere near the behavior range of the children. Notably, and again, this overlaps with Ida's point, you can watch these 2 videos, and these are both failures. But one of them is an AI, and one of them is a child. It is observable, and I'm not going to ask because I've labeled it accidentally, but it is observable which of these is an agent and which of these is a child. You can tell, even though they've both solved the task, that the one on the right is the child and the one on the left is the agent. And that was the winning agent, actually. So even when both fail, the difference between AI and humans, in this case, is observable and meaningful. And actually, failures tells us just as much, or sometimes even more, about the nature of the learning process that's going on and the nature of the understanding than passes do. So here we have the same baby, a lemur and an AI, all failing at a task where you have a transparent barrier and a food reward behind it. Everyone's so confused. But this tells us about how they've represented this task. And the point is that, as Brian Cox put it, we are all both clever and stupid in equal measure. We all have stuff we're good at and stuff we're bad at. And if you like, our cognitive fingerprint, or if this was a room full of ecologists, I would call it the cognitive phenotype, can be represented by the nature of this pattern of passes and failures, of strengths and weaknesses. But in order to get this cognitive phenotype, whether or not it's an animal or an AI, we need to have really good definitions of the capabilities we're investigating. We need to have really carefully designed tasks that actually test those capabilities. And we have to have robust evaluation across diverse contexts. Just because you can do it when everything's perfect doesn't mean that you have that ability. You may well have learned some other way of doing it. And you then need to triangulate across those tasks to make inferences. And so I'm going to give a brief introduction to some of the work that the team and I have been doing over the last few years to try and kind of get at this sort of problem. And this is the RecogAI project. And here what we try to do is that we're trying to provide both the input to this kind of complex analysis in terms of the tests we create and try and see if we can export this kind of cognitive fingerprint, cognitive phenotype sort of evaluation. So the first important thing is to have comprehensive batteries. You decide the cognitive area you're going to test, and then you make a really robust, comprehensive battery of tests assessing that. So you see there's two faces you see here are of Denaya and Cozy, and between them they have created a battery of tests in animal AI that span this absolutely basic go and get the reward, kind of very simple navigation, right up to quite complex object permanence. So that's the kind of trajectory of the cognitive space we've chosen to investigate. And then most importantly is that each instance of these tasks, and we've got thousands and thousands and thousands of tasks now, is associated with quite a lot of metadata. We know for every instance, is there lava? Is there a platform? Do you have to climb a ramp? All of this baseline stuff. But also, what cognitive and non-cognitive skills does it require? This may be a test of object permanence, but this is one that requires loads of navigation ability. This is another one that requires not very much navigation ability, but is really much harder on the memory. And you can then start to say, well, I want a test that has this challenge, this challenge, this challenge, and this challenge. Which of your tasks have that? And because we have the metadata, we know. We can just say, oh, it's those ones. And one of those might be a test of object permanence, another one might be a test of navigation, and so on. Doing so, it means it's possible to observe the difference between an agent that makes a small number of random errors compared to an agent that has a consistent Achilles heel. Like an agent that gets 67% because it just really can't do lava or ramps or transparency, or another agent that gets 67% in an unpredictable way. I don't know what it's failing at. It's failing at the same number of stuff, but I don't know why. It's unpredictable. And that way of doing things means that you get a lot more information from than just from an average score across. And so once you've started to get this kind of level of robustness of a particular set of tasks, you can start to vary that in terms of the cognitive challenge as well. So once you've got, what's the robustness across many different types of object permanence task where one object rolls behind one occluder for exactly 1 second, then you could say, well, and now I'm going to consistently vary the memory challenge, or now I'm going to consistently vary the number of objects. And then you start to get performance across these dimensions of cognitive challenge. And in doing so, you can start to say, how does performance vary according to these dimensions, which if there's only a couple of dimensions is relatively easy to kind of plot and to demonstrate using these kind of grids. And we did that with looking at the Animal AI Olympics data. So for example, the example we gave was like, if it was a self-driving car, let's have 2 dimensions. How wiggly is the road? How foggy is it? You could have agents that can do any level of fogginess but no wiggliness, or vice versa, or that they fail at some combination of challenge on the 2 together, so that would be like 2 dimensions being predictive, or you can have an agent that's got no dimension being predictive at all. You don't know how well it's going to do. So even if you've got an agent that's just as good or just as bad, whether or not the dimensions are predictive means that you can predict their behavior and when it's safe to use that self-driving car and when it's not from just those 2 dimensions. And we could see the difference between the different agents that entered the competition based on their performance across just these 2 dimensions and these really simple tasks. But hey, showing patterns of passes and failures is really easy when you've got 2 dimensions that are linear. When you start to have more than 2 dimensions and they start to stop being linear, you can't make a lovely little cube out of it, unfortunately. So you start to have to do something a little bit more complicated. So our next step was based on the cognitive demands of the task and the relationship between the capabilities that an agent could have and the cognitive demands of the task. Based on our domain knowledge of psychology and how these things work, you can start to build a model where you say, I know what the demands of the task were, I know what tasks you passed and failed, what capabilities do you have? And we did this using PyMC. So this is using sort of Bayesian triangulation with a hierarchical Bayesian network. We started to look at can we put all of the things we think are necessary for this task together and connect them in the way that we think they're connected, and then pass the performance data through this to infer a cognitive profile. So, for example, looking at exactly the same data as I was just talking about in the Animal AI Olympics, you can say, well, how far away is the reward? How big is the reward? Those are two features of the task. And features of the agent can be its navigation ability, its visual ability, whether or not it's got a left-hand bias, and so on. And you can link together the elements of the model based on how you think those things should, according to like psychological theory and other domain knowledge about the types of agents that exist in the world, link together. And using that for this very simple data, we were able to plot the agents that were submitted to the competition, again, just using these very simple variables. But you can see here, it's a complex thing, and I'm not going to go through it, but the take-home message is, yeah, from just can it find the reward in an open field, you can identify which agent won the entire competition. But of course, when you're dealing with existing data sets, the problem is that you have data sets that weren't designed for this kind of methodology. So yes, you know where the passes and failures were, but you have loads of missing data. And this is where predictability is really important. And the good thing with this kind of model is that we can do both bottom-up and top-down inference. When you have the performance data and you know the demands of the tasks, you can say, based on your pattern of passes and failures, these are the capabilities I think you have. But now, once you have the capabilities, you can say, given the capabilities I think you have and the demands of this new unknown tasks, I can predict whether or not you are going to pass it and fail it. And that's where the real utility of this kind of profile really comes in. So we wanted to test this against something more complex than just like, can you find the reward in an open field? But we actually didn't have any agents that could do object permanence. So instead of trying to find an agent that could do object permanence, we used this, the object permanence test battery, and we used 3 different types of tests of object permanence, and then loads and loads of examples within these 3 different types, and then lots of other kind of much more simple tasks. So tasks that just have lava but nothing else that's a challenge, or just have a ramp but nothing else that is a challenge. And what we wanted to do, we said, well, we don't have agents that can actually pass these, but we know what it would look like if we did. So we split the group into 2 teams. Team A came up with a series of theoretical agents that had a particular profile of abilities. So this one has object permanence, it's really good at object permanence, but it's clumsy. So if it has to go along a little platform, it's going to fall down. Or this one has object permanence, but if it sees lava, it's just going to die. Or things like it doesn't have object permanence, but actually it's got a really good memory, it's got really good navigation ability. So if you only need those, you do pretty well in quite a lot of the tasks, and it'll be okay, but it'll really fall down as soon as you actually need to have that final cognitive ability. And Team A translated that into synthetic data across these tasks. So given the profile of the agent, this is the pattern of passes and failures you would expect. Meanwhile, Team B is not talking to Team A, but Team A is taking the whole team's shared knowledge of the tests used, what they theoretically assess, and the structure of the situation to create this hierarchical Bayesian model about how the data should be translated into a cognitive profile. And then they backwards inferred the cognitive profile that they thought those agents had. And we then compared those profiles. And this is what that model ended up looking like. And these people at the top, Ryan, John, and Cozy, if you want to ask questions about the model, ask them, because I won't know the answer. And we did a couple of different comparisons of ways to see how much agreement there was between the models, between the profiles that Team A came up with and the profiles that Team B inferred just from the data and the model. This is the quantitative data, and all I'm going to say is that you can kind of look at the left-hand side and say that clearly the agreement was pretty good quantitatively. We also did qualitative alignment. To what extent, based on the kind of qualitative description of the agents going in and the qualitative description of the agents coming out, did they agree? And green here represents a degree of agreement. And you can ask me later about what the red ones were, because they were a special little case that clearly the model couldn't cope with. But otherwise, you can see basically it's mostly green. So just to wrap up, cognitive fingerprinting is something that you can't just say that something's clever or something's stupid. Clearly, simple learning mechanisms produce powerful behavior, but we need to go beyond that agent is stupid and that agent is clever and say, what is your pattern of stupidness and cleverness? What is your fingerprint that is unique to you or unique to your species if we're doing it at a population level? And we can use that for prediction. Identifying the cognitive profile allows prediction of where an individual will behave optimally and where it will fail. But beyond that, it allows you to predict not just whether or not it'll pass or fail, but how and why it will fail. And that facilitates progress both in terms of predicting AI, but also developing better AI in the future as well. So there's millions of people to thank. The people who have been, is a non-exhaustive list, but the people who have been mostly involved in this project are on the screen. Thank you very much, particularly to the PhD students and postdocs. And just a quick plug that we will be hiring some new postdocs in the near future, so particularly to work on kind of language model applications of this sort of stuff. So if you're interested, do let us know. But that's it. Thank you very much.
Thank you, Lucy, again. Can you hear me? Yeah, now you can hear me. Thank you, Lucy, again for this really insightful talk. We are running a little bit behind schedule, so be very succinct in your questions. I think you can take 1 or 2 questions. Okay, question down there.
Shout.
Yeah, I will shout. So thank you very much for the presentation. Very interesting. I wanted to ask. It seems that some of these some of the capabilities failures in different domains are related to not having a causal model of the world. Like, so for example, the children that goes and touches every square, it hasn't really learned anything. It's just
exactly.
So, my question would be. Do we learn causal models, or do people, to what extent do people learn causal models, and do any other agents do, or I don't know?
Do we? Yeah. This is something that is, it is a protracted development, and it's something that it's not easy. And yeah, that was like a 1-year-old, you see, and a 1-year-old, a bit. But there's still a lot of really just reinforcement kind of, or imitation actually is really what toddlers do a lot of the time. But do agents? I think that's a really hotly contested question. I think that's one of the questions we're trying to get at with some of these tests. Like, there is behavior that is as if it has a model of the world. If you don't probe the things that you would get wrong if you had a really, really sophisticated statistical like pattern of surface level stuff, but no model. And so what you have to ask the question is, what would behavior look like if there was a model? What would behavior look like if there wasn't? And then find a test that finds a difference. And the difficulty with most tests that are not designed to be tests, which most AI benchmarks are, they're designed to be a computer game, or they're designed to be a board game. They're not designed to be cognitive tests. And that means that it's very rare that they're able to say, actually, this is designed to differentiate between behavior produced by someone with a model and behavior produced by someone without a model. So yeah, do some AIs have models? Yeah, some AIs are like built with models. Do some reinforcement learning agents develop models over time? I think that's an open question, although I'm sure there's people here that know better than I do.
I think we have time for one super quick question, if there is any question left. If not, Lucy's around here later on, so please go find her and ask her questions. Let's thank again Lucy for this wonderful presentation.
You guys might need to switch your mics on, just the button at the bottom. Cool. Can you guys hear us okay? Perfect. So it's my great pleasure to be hosting our next panel, which is going to be shifting focus a little bit. We've talked in the last panel about predicting where AI is going as a field in the future. And in this panel, we're going to focus a little bit more on predicting what a particular system might do, how it might behave, and how well. We have on our panel Lucy Cheke and Joel Leibo, who you've already heard from today, and they're also joined by Peter Flech from the University of Bristol and Ellie Boyle from the London School of Economics. To start us off, I think it's really important to get on the same page about what we're really talking about when we talk about predictability in terms of a specific system. So my first question is, what are the things we actually want to be able to predict in terms of a specific system, and why is it important to be able to predict those things? Maybe we'll start with Ali.
Sure. So I think there's like lots of different things we might mean when we talk about the predictability of a particular system, and some of those are going to matter more for some projects than others. So you might just be interested in like predicting how well a system is going to perform at a particular task, like how successful it will be. That might be very important for engineering purposes. You might be interested in the sorts of stuff that Lucy was talking about, like particular patterns of behavior. And that's the kind of thing that's going to be really important for things like cognitive evaluation, also for things like, safety, like what are the specific failure modes of a system, under what conditions will it work, under what conditions will it not work. Then I guess there's the more kind of theoretical stuff that Lucy was talking about, like what would we expect this system to do if it had a cognitive capacity that we're interested in? And that kind of question might be sensitive to other predictions that you would make about a system, like in animals, for instance, you think you have to ask those questions, given that this creature is a predator, like how would we expect this capacity to manifest? Because cognitive capacities aren't going to you're not going to make the same predictions about every different type of agent on the assumption that it has a cognitive capacity. So I think, there's lots of things we might mean, and it kind of depends on what research project we're engaged in.
Yeah, that makes a lot of sense. Thoughts from others?
Yeah, I guess I'll jump in there. I guess what's really interesting to me is you start from the questions that are a bit like what the things Lucy was just talking about, right? Where you kind of probing an individual. But what I want to know is more like what happens if you put a bunch of them together and embed them in a world with humans that all have different incentives and different learn in different ways, and what would come out from that, right? And what's predictable about this is in some ways it's like the forecasting question, like we're predicting the future about things, but also the kinds of stuff that I was talking about were basically agent-based simulation methods. So you can try to run things in simulation, search for principles that would then find kind of causal forces in how multi-agent systems evolve. And I think that's really the kind of computational social science sort of angle on what you could get out of this, where you might be able to predict new things about the future or whatever.
Yeah, I think also it's important to think about the level of granularity that you talk about. So very simple example and trivial in some sense, but if you think about tossing a coin, then if it's a fair coin, then it's fundamentally unpredictable what the next coin toss is going to be. On the other hand, we know everything that there is to know about the coin. And moreover, we know that if we do it often enough, it asymptotes to 0.5. So is it predictable at the individual coin toss level? No. Is it predictable as a system? Yes. So I think that's relevant. And that may come up, but just to make another comment, is predictability also involves some way of measuring what the system is going to do. And measuring is very hard. And I've heard the many fascinating talks today, and I've heard a couple of times, oh, if only we had a metric to do something. We shouldn't forget about the Goodhart problem, because we're optimizers. We are particularly, we will fall victim to the Goodhart paradox as soon as a metric is, you take it as an objective, then it feels to be a good metric. And so I would say that we need to actually delay as much as possible having a metric until we actually understand what it is that we're measuring. Or even, in the case of the Turing test, kind of avoid having a metric at all, you know, in the idea of, well, I don't know what intelligence is, but I recognize it if I see it, and then you do some kind of experiment with users. But unfortunately, or fortunately, maybe the Turing test is dead now that we have ChatGPT. So maybe that's a good thing. Yeah, so the points I'm making is particularly before we measure we shouldn't rush into measuring things if they are things that we don't fully understand.
Yeah, if I can just add a tiny addendum to that, I think the fact that we are optimizers should be a motivation for us to so at the moment, you know, a lot of benchmarking is what is the best? Like, which is the best reinforcement learning model? Which is the best foundation model? And actually, you know, if we're optimizing, we should say, which one is good enough for the purposes that I need it for? Based on how expensive, how, you know, in money, but also in compute and in energy. And if you can predict the behavior of an agent, like, yeah, it fails here and here and here and here, but I'm not using it for any of those things. I don't need it to pass those. I don't need it to be the best. I need it to be good here. And if I can predict it well enough and precisely enough, then I can say, well, this is good enough. And I think we struggle at the moment with that because we don't have a good definition of good enough because we don't have the predictability to know where it will be good and where it will be bad.
Yeah, I think also there's competing interests when it comes to what is good enough. So just anecdotally, in my department, and I imagine in all departments, there's a lot of like concern about ChatGPT being used to write essays. So we're all trying to figure out what are the predictable mistakes that ChatGPT will make. But I'm sure if we ever successfully like identify the mistakes that ChatGPT makes, it will then become a target for them to stop making those mistakes.
Yeah, and what is a good enough essay? Like, if it can write an essay that's like, that'll get you a third, it's like, wow, didn't need to pass. So, yeah.
The difficult thing about, you know, even for like some system that exists right now, you're making predictions, it's like, how will people use it, right? You know, different people have different incentives and will want to use things in all kinds of ways that are hard to anticipate. So it's not just like, you know, does the system have this capability or whatever? It's more like, you know, people will come up with ways of using it that are, you know, combining with other things that are just like very, very difficult. And what you need though is some kind of more, we need to think about the whole ecosystem around it, like what kinds of norms and institutions we have as users and as people creating these things and people who are talking to policymakers and stuff, like how, what does the whole system end up looking like? And it has to be robust to the fact that people will have very different incentives and there are plenty of malicious incentives there.
Do you think that the fact that we're now building more and more general systems, being used by more people, is making those challenges is harder?
I think we're just integrating into the world more, right? There's more levers for things to happen, right? If you just have something, like if you have a language model that's really just remains completely a language model that never gets any affordances in the world, you never can take any actions, then that's a very different looking system versus one that suddenly has some actions and, you know, can do something.
Yeah. I want to come back to something that Peter said about like a coin toss, which is just fundamentally unpredictable. And I've been thinking a lot as we've been talking about the comparison between humans and AI systems, that in many ways humans are quite unpredictable. And so should we expect our AI systems to be predictable if they're going to be engaging in these kinds of complex behaviors?
Yeah, I mean, I suppose for some purposes you should neither expect nor want it, right? So one of the great hopes for AI is that it will help us solve problems that we can't solve already. So if we had like a fully predictable system for those purposes, that would be unsuccessful.
There's prediction and there's like individual prediction, right?
Yeah.
Like you could make an aggregate prediction about how, you know, most people will behave a certain way in this kind of situation, and those things, you know, we can in some situations we know a lot.
For sure.
But often, you know, what will any one individual do at the diagnostic kind of level stuff is like, we don't usually have that.
Well, yeah, I think when it comes to humans, it also depends who's doing the predicting. Like, I can predict what my husband will do really well, because I know him really well. So the better we know the AIs, the more we can predict them. And the better we know humans, the more we can predict them. It's not that people are fundamentally unpredictable. It's, I mean, obviously there are margins of error, but it's that the people trying to predict humans are trying to predict humans from 10 miles away based on such rough-grained analytics that there's like, well, you're a woman and about like this age, so I guess you probably want makeup adverts. Like, on a population level, that's kind of fine, it works, but at an individual level, that's going to be way off. So I think, you know, what we see in some of the like Cambridge Analytica stuff is that you get a good enough knowledge of people and you can predict them well enough to really make a difference to what they do. And I think turning that on its head, if we could do that back at the AIs, that would be an advantage. So yeah, I think it's the same thing. The more you know something, the more you understand something, the better you know it, the more you can predict it. And that's true no matter what system you're dealing with.
Maybe to put something else in the mix. So there's actually quite old AI approaches to things like diagnosis, so either medical diagnosis or diagnosis of engineered systems. And so typically what you have then is a model of normal behavior and you have a fault model. In fact, you know, you could argue that medical practitioners need to know more about how human bodies go wrong than that they need to know about how they normally work, because if the body works as it should, then probably they don't go to their GP. So there is a, you know, I'm thinking, is my car predictable? Well, in some sense it is, but it requires input from me. But at some point it starts making funny noises or something stop working, and then there is something wrong. And I think related to that, you have this notion of operating conditions. So let's say my phone or my tablet is probably, you know, there's probably a fact sheet somewhere that says, you know, don't operate outside -10 to 40 degrees. And in fact, my phone probably has a temperature sensor and actually, you know, switches off or does something, you know, disconnects the battery or whatever when it gets too hot and so on. So I think there is also moving away slightly from predictability and sort of saying, well, there is this kind of safe set of conditions where you expect the system to behave normally and doing what it does. And then maybe there is another set of conditions that if you step outside of there, then sort of anything may happen.
So can I just quickly follow up on that? Like, so in that case, I mean, obviously not in an AI way, but your phone is knowing its own limitations and then acting to stop itself causing problems. So is it that we need to predict the AIs, or is it that the AIs need to predict themselves?
I think the latter is, I think a big problem that we have with trustworthiness of AI and so on is because we build algorithms that always give an answer. You know, like k-means or dendrograms or so. They just, and it doesn't necessarily scream out at you that the answer doesn't make sense. I mean, I needed to actually run the hierarchical clustering algorithm on some uniformly distributed data to see what kind of dendrogram I got out of it. And it looked perfectly respectable. And if you do it in MATLAB, you get clusters of 3 colors, and it is just a random partitioning of your space. So, and I think the same problem we have with ChatGPT, which sometimes has been described as mansplaining as a service. And the important thing there, it does it with complete confidence. It doesn't, you know, and actually, if it's a word sequence prediction thing, it may have had n number of words with some kind of near uniform distribution of probabilities. And if you do an argmax, you just pick one of those. And it doesn't tell you whether it was one of those situations or whether it was a 0.99 and then all the other alternatives were very small probabilities. So I definitely think a lot of problems in AI, I think, would go away or would be much less prominent if we build algorithms that actually say, I don't know, more often.
Yeah, it would be great to get some questions from the audience. So, yep. We could get Kazi first, and then I'll come to you, Pablo.
Hi. I'm wondering whether, to what extent the answer to the question, how predictable can AI systems be, is dependent on the answer to the question of how explainable can AI systems be. Can we make good predictions without good explanations? Can we make good explanations without good predictions? Vice versa.
Yeah.
It's another tricky term, right? Which we in AI bandy around as if we all know what it is, and we even build explainable AI systems. And it's, for me, I think explainability is linked to understanding. So sometimes one word is enough, and then suddenly something clicks, and I understand it. So, yeah, understanding. I mean, do I understand my robot vacuum cleaner? Well, again, I mean, going back to a random system, I don't understand that when it bangs into something, it goes left rather than right, but there's nothing to understand about that. I do understand it, that if I leave it on its own and I come back after a while, it should be back at its charging station because the battery has gone. So it doesn't explain that to me, but you know, I have that understanding, and maybe it doesn't need explaining, but other things do need explaining.
Okay. So part of the reason to care about explainability, I think a pretty big part of it is really to assign responsibility. Like we as people have intuitions about like the causes for my decision should be, like if I say this is why I did it, then and if that's a good reason, then it's defensible. If it's a bad reason and I did it anyway, then it's like I'm responsible for some bad thing, and that's the intentions you have when you do something matter, right? So it's not just the consequences, right? And that's how we kind of intuit things, and so we kind of want to treat our AI systems the same way. Like we want to know, like, well, this is what caused it to make this decision and have these consequences, and then assign responsibility accordingly. But it's not always, we don't need to think of responsibility that way, right? Like there was a talk this morning about different ways of assigning liability, and they weren't all necessarily like that. Some of them had us thinking about the consequences, and it's you could imagine the creators would be assigned blame for something going wrong if the consequences are bad, and they could have foreseen that or something like that. And maybe that matters, that it was like this is how the system got to that answer, but maybe that doesn't matter at all. It's just it's outside the system that's important. So insofar as explainability is about assigning responsibility, then sometimes we care about having real verbalizable, low-dimensional explanations, but sometimes maybe they just could be more complex explanations, which are sufficient for responsibility. And
I think, it's a bit like the coin toss thing to me. It's about the level of granularity, because sometimes you can say, I know that when you have X, this happens, when you have Y, this happens, and when you have X and Y together, this other thing happens. Do I know why X and Y interact that way? No, but I know that they do. So you can have, a reliability based on what you understand at a level of granularity, and I think that's the thing that's important. Like you're having a good relationship between the degree to which it is explainable and whether or not that relates to the reliability given that understanding. And so you don't have to have full understanding. You just have to have enough understanding for the reliability and the predictability to work. It's the same thing. I don't quite really understand how it is that when I press X on my keyboard, an X appears on my screen. I am not an electronic engineer, but it does, and it does every time. And the person who made it knows why. And that's enough.
Ellie, do you have thoughts?
Yeah, I suppose just coming from like a philosophy of science background as well, one thing to say is like there are different norms that govern the success of explanations and predictions. So if you're thinking about explanation in terms of like describing the causal process by which something occurred, and you have like a kind of empirical adequacy as like the only constraint on what makes it a good explanation, then there's going to be a really close connection between explanation and prediction, I think. But in general, we evaluate explanations as being good or bad, not solely on like empirical empirical adequacy grounds, but also on like non-epistemic norms like simplicity, elegance, fit. And on that way of looking at it, having a good explanation, however important it might be, is maybe like a more difficult thing than like having predictability.
I think we had a question from over here, maybe.
So I guess similar question to the other panel. To what degree are we going to, or to what degree can we figure out methods to evaluate systems that are highly capable? Especially, I mean, the issue is that animals are much more like us in the sense that they're very similar. They want food, they want similar things, and they have very similar pattern recognition. But AIs are very different, and their methods of being trained are also very different. So how are we going to evaluate them when they become very capable, and especially make sure they are safe, or they are optimizing for the correct things?
So big question, there's a lot to unpack there. I mean, I think some of the stuff you talked about, Lucy, is very relevant to this.
I mean, there is an extent to which biological brains are biological brains, but many of them have their common ancestor like way back in the tree. So there has been convergent and divergent evolution of intelligence, which means that we have in our data set of minds, if you like, some really different ones that behave in very different ways. And so, what you see in an octopus intelligence is using a different hardware, like very different hardware. It's still biological, but it's very different to a human. Meanwhile, you can have something like a bee where the hardware in the individual animal is extremely simple, like simple enough that we know what all the neurons are and where they are and how they connect. But actually that's not where the intelligence lies so much. The intelligence lies in the fact that there's 300 of them coordinating together. It's the hive mind. And that's really different again. So what the benefit of having that approach is, I think, that we can say, well, we're trying to make sure that we have ways of understanding that cover that kind of mind and that kind of mind and that kind of mind. And yeah, AI is going to be a really different kind of mind again. And we have the same question. We talk about, like, what if there was an alien? If an alien intelligence came, how would we know that it was intelligent? What would it look like? How would we know what it would look like? We don't, but we know we can develop tools to say that are as hardware agnostic as we can possibly get once we've experienced all of these different ways that it can be applied. And I think the humans being really, really clever helps us kind of, differentiate between humans is hard because they are very clever and very general. I think one of the challenges that I think may slightly underpin your question is some of the very, very general intelligences we have within AI. It's not so much that they are general, it's that they've been trained on everything that exists. Like the language model has been trained on the whole internet. So it's a double problem because the intelligence is general, but it contains everything we've ever written down about how to understand intelligence. So that's all contained within the problem. So that is a special problem that's above and beyond just the fact that it is a very capable and very general intelligence. And I think that's one of the really major challenges.
So when I think about like very capable agents and superintelligence kind of things, I think a useful intuition bump is thinking about corporations, which are superintelligences, which exist, and we have lots to say about them. We understand some things. We worry about their being misaligned. We think about their governance. And they're certainly more intelligent than any individual human, right? So there's a lot of things in common here, and we have some kind of like established frameworks for thinking about governance, right? It's like we know that there are you can have regulators and you can have competition between corporations, and you want to set up things in certain ways, and it's all kind of things that we can kind of understand. But it's a large multi-agent system with governments involved and policymakers, and it's not necessarily the case that any one individual even understands all of how corporations are regulated. That's also a multi-agent thing. So on the, you were talking about bees a second ago. Like I actually think humans are potentially much more like bees, and most of the things that we're really proud of as our intelligence as a species is really more group collective phenomena. But that remains true as we create more intelligences at different scales and sizes and augment our ecosystem with more things. And
we add AIs to the hive.
I want to stay with this thread on evaluation because I think it's a really important one. One of the things that we've been really conscious of is that as these systems become more general, the cost of evaluating them is also becoming much larger because the systems are more expensive to run and there are more things that you need to evaluate. So is that extra cost of evaluation something we should just accept, or do we need to start rethinking the way we evaluate systems to try and make it more efficient?
I think, well, it depends a bit on what you mean by evaluation here, but I think in this sort of academic rat race, our evaluation tends to become more primitive just by every version of NeuroAIs. And I think that...
What do you mean by more primitive?
I mean that, the typical NeuroAIs paper with the big table in the back with the bold numbers in the right places, and as if that, demonstrates anything. That this is endemic, I think, in academia and isn't doing us a service because it's sort of suggesting progress where progress doesn't actually exist.
So you think that basically we're not robustly evaluating these systems? Is that what you're saying?
No, because it's become very formulaic, I think, and so so a little bit of history. And I've been long enough in AI, and I've said this before, that that I remember AI being a decidedly non-fashionable topic, and machine learning actually initially was much more adventurous than it is now. But it had an evaluation problem. So, Patrick Winston's arch, learning an arch from images and so on, that was basically, we would now say, oh, that's only toy problems, there's no stats in there, sort of. It was a bit like, look, ma, no hands. And then Pat Langley sort of started complaining about that and said, oh, we need to do more robust evaluation. And then actually what happened was we changed the problem in things that were more easily evaluated, and sort of hence the enormous focus on classification, and that became the prototypical machine learning task. So we kind of narrowed the field. Sort of we, when I say we, I'm involved in that as well. But there was a narrowing of the field. There was also a move towards the lamppost where my keys probably aren't, but at least there's light there, so I can do some systematic evaluation there. So I think we shouldn't forget that these things tend to happen when we sort of we have it's such a big academia is such a big environment now, and everybody's trying to do the same thing and sort of being successful in there, and that there are disadvantages there.
Yeah, I mean, I guess one of the interesting things about AI relative to other fields is there's so much research also happening in industry. So, Joel, from your perspective, what do you see in terms of evaluation practices at places like Deepmind, and do you think they're robust enough? Do you think that they're efficient?
Yeah, well, we do a lot of different things, right? So some evaluation is like you have some system and you want to know, does it really, do what you want it to do, or maybe it can do new things you didn't realize or something. That's one kind of thing that happens. But there's also a lot of stuff that's more like test-driven development, right? Where you make an evaluation first and nothing can solve it yet, but you have that, and then you have a concrete number and it's bad, and you work on pushing it up. And lots of projects are oriented that way, right? Like Melting Pot, our kind of suite of environments and contests we're putting together is like that. Right? It's an unsolved problem, but that gives you a number to measure, and then you can try to develop algorithms that do solve it. So I don't know. I guess I see there's all kinds of different things that are happening. I totally see your point about lots of NeuroAIs papers just have a table in the back with something in bold, and maybe sometimes they do a t-test between those, but usually they don't even do that. And there's definitely more, generally more kind of like quantitative, empirical, just how do you do simple hypothesis testing kind of knowledge in other fields that's usually not present in most machine learning education. but I kind of think it's more of like it's an all of the above. Like we need kind of more of all of these things, and probably just in general to invest much more in evaluation. I mean, because now these things are getting real, and we should just be kind of putting more into it.
Right. Other questions from the audience? Yeah, Jose?
I'm not sure if it's working. You probably need to.
Can we grab the other mic for Jose, or someone help him out?
You can use this.
It's a very short question. Do you think that AI will be more predictable or less predictable in the future? And of course, we have a say here. We have an action to take. But what's your take on this?
So, I mean, AI in the world, you put it in the world, you put more affordances in, then it becomes multiplied by all of the people and all of their intentions. And I don't want to sound defeatist about it. I don't think I'm not defeatist about it. I think we just need to see it as kind of a social science question, right? It's like the whole system is really, it needs to be thought about in order to predict anything. And I think that is tractable because there are principles there. But it's definitely it's definitely increasing in scope as we deploy these things.
I wonder if it's a non-linear answer, that as AI becomes less predictable, suddenly people are going to start to realize that they need to evaluate it properly. Then they're going to put the more money into the evaluation, then maybe the AI will become more predictable as a result of that. I think one of the, there was this question about kind of narratives and stuff before, that I think one of the problems we've had so far is that people intuitively feel like they can predict the AI. They're like, yeah, it can do this, it can do that. And so you get this situation where the assessment is a bit of testing and a lot of intuition. And I think once they get to a level of complexity and unpredictability where it becomes clear that you can't do that, then you may start to find that actually you start paying attention to the best ways of evaluating, the best ways of assessing, and then you may come back the other way. So yes and no.
Ali, any thoughts?
Yeah, I mean, I suppose it's a two-part question as well, isn't it? It's like, how is AI going to change and how are we going to change? We might put pressure on the development of AI systems to make it more predictable, but there'll also be pressure on us to understand better how they work. So I suppose that makes me think the trend is going to be towards predictability when you consider the interaction of those two things, but I might be optimistic.
There's just one argument that people sometimes say that you maybe if you see like the social media as like making the people more predictable in order to sell them things or something like that, maybe will have some effect on us as well by the other actors in this ecosystem.
Yeah, there's definitely interaction effects there. I mean, let's face it. So we had to learn how to use Google effectively. So Google appeared, and then initially we start to type fully grammatically correct questions, and then we realized that we can drop most words, and actually some words like negation are not handled correctly at all. So don't ask Google questions with a negation in there. So we are adapting to the technology, and the same thing is happening with ChatGPT as well. Now there's prompt engineering. We need to figure out how to again ask the right question to get the answer we expect or we want. But what I think it's again with ChatGPT is really interesting for me is that fundamentally, it's this basic capability. It's a language model. It can, predict the next word. And suddenly all these other capabilities appear, they're maybe not all good and correct and so on, but I find it absolutely fascinating how people find all sorts of new things to do with ChatGPT, like, writing computer code or, debugging code or explaining code or whatever it is. But it is just a language model. So then we also have the effect that suddenly people say, oh, it hallucinates, as if that's a bad thing. But that's the whole point of a language model. It's kind of making, building sentences that maybe nobody ever spoke before, but have some kind of coherence. So
if you have a system that is capable of doing so many things like this, how do you decide what are the right things to evaluate? Like if you take ChatGPT, what are the things we need to evaluate it for, and how do we figure those things out?
I wonder, on the question of, do things become more predictable, like, if you imagine a sort of equilibrium picture in the end where, there's so many undesirable behaviors, right? You can ask ChatGPT to write your misinformation for you and that, we'll have to move to some kind of world where there are also AI systems that are policing the uses of AI systems, because there'll be new prompt hackings and new malicious uses at all the time, because there are malicious humans, right? You can't, you have to assume that. And so you need some kind of AI policing or something like that, maybe run by regulators or maybe run by other, just something within the system itself. Could be lots of ways of doing it. But then you could imagine that there's an equilibrium inside of the system, and maybe then things do start to become more predictable, where it's okay, probably prompt hacking isn't going to work, because if it were to work, then this other system would have stopped it, and you can get some kind of measure of expectation of what things likely to happen.
It seems like cognitive theories probably come into this as well, right? In terms of understanding what are the different kinds of things that these systems might be able to do, and what we might want them to do.
I mean, I think there's two, I mean, there's probably lots, but there's two in the top of my head. One is obviously, being able to predict what it's going to do based on its capabilities, which we've talked a lot about. But the other one is, if we know what humans do and how they do it versus what the system does and how it does it, then that can be used as a way of saying, actually, a human didn't write that. So part of the predictability is the distinguishability and and that is what allows the policing, because you can't get rid of chatbots if chatbots are indiscriminable, well, not indiscriminable from humans writing the same thing. Well, you can ban humans and ChatGPT from doing the same thing because the thing itself is bad. But you could have others where it's it's fine if a human does it, but if some AI farm is making thousands and thousands of AIs to do it, that's not fine. And then you need to be able to tell the difference. And being able to know the capabilities of the system means that you can say, right, this pattern of passes and failures is characteristic of a language model. Of course, what you'll have to do then is never publish that. Don't put it on the internet, otherwise ChatGPT will know, and then it'll all be wrong. But in theory, it's the fingerprint. You need to be able to know the fingerprint so that you can tell the difference, because there are things that are inherently bad and the things that are bad if it's an AI doing it. And we need to be able to tell.
It would be really useful if we could watermark ChatGPT output in the same way as we can watermark images. Yeah,
so they are doing that, right? It's just a watermark. They're starting to do that, but it requires a chunk of text to work. So if it's a very short response, you're not going to be able to see it. But the problem with that is you have, again, if thinking about a whole ecosystem, right? Anyone who wants that to not work can just train another language model to remove the watermark. You can flood the internet with text created by that, or whatever you want, and it's not. You need to have some system that is kind of robust to the fact that some people want to break the other safeguards.
Yeah.
I mean, it doesn't help, in things like CAPTCHA, that the thing we use to tell that it's a human is the thing they train it on. As an approach, I feel I see a flaw. We need to have CAPTCHA, basically, for the new kinds of models that we have, and I think that the only way to do that is cognitively.
I guess you're really touching on a pretty philosophical question there about should we be aiming for human-like AI, and if we have systems that can behave in the same way as humans or do the things that humans do, is that problematic? Is that something we should be aiming for? Things like that.
I think one of the principles that's emerging from some of I'm definitely not involved in any kind of policy discussions, but I think a lot of people are talking about just saying that the rule and norm should be that AI systems have to identify themselves as AI systems, and if you're saying that you have to say that, then it's maybe you can act you can let it act in a human-like way afterwards, as long as it's always identifying itself. But then you really want to create lots of penalties for violating that in a product, at least, or in something. It becomes you have to think about the whole system around when do those things get triggered, and do you ever catch people, and
Yeah.
I think human likeness is the aim in some circumstances, and doing the job best is the aim in other circumstances. And when you come to nefarious uses, then that becomes extremely complicated. But if we want medicine to improve, then human-like AI would be really good.
Not for like analysing the data or being the doctor necessarily, but for being the human, being a model of the human. So, well, what happens if we break that? Because you can't go, ethically, there are some problems with doing that with people. So, there are lots of reasons to want human-like AI, but that might be not because the way humans do it is the best way. It's because we want to understand humans better.
Yeah.
If we want to say what's the best way of doing that, then I think the answer is almost always going to be not human-like in some particular way, because we make compromises when we're good at everything. We're kind of pretty good at everything, but we're not the best at anything. And sometimes you want something to be the best at something.
Yeah, and sometimes you want something not to be subject to the characteristic pattern of errors that we're subject to, or to the characteristic biases that we're subject to. I mean, this is clearly in the background of some, turned out to be very problematic applications of AI. It's like, oh, let's use AI for sentencing. That won't introduce biases.
Right.
Which, I mean, the feedback thing there is, what is the AI trained on? The AI is trained on the biased and problematic data that we have produced. So it might be the best at using the data we've produced to make a prediction, but not the best at predicting what's the ultimate and most desirable outcome is.
But
Those are different
at
questions.
least it won't take different decisions before and after lunch, right?
I don't think that study replicates.
It doesn't replicate,
No,
it doesn't replicate.
Decisions before and after fine-tuning. Via lunch.
Thank you. Other questions from the audience? Yeah, Alex then.
Can you hear me? Okay, great.
Yeah.
So my question is very straightforward. Is because I see a very lacking open source amount of evaluation results being published, and namely, should we rethink the way that we publish our results when we do some research? It's not only about the code for others being able to reproduce our result, but also the empirical evaluation result that we obtained, and make that open source so that other people who are more interested in evaluation can have more easier access to these things, so that this can be more evaluated in a more transparent way. Because otherwise, if we don't have this evaluation result, it feels like, okay, I have these big models, it's published there, we don't have the code, we don't have the evaluation result, neither, we cannot evaluate, so it's much even harder to understand the behavior, the limitation, and being able to predict what they can do when being deployed to the real world. So, what do you think? Whether should we reframe this convention of publishing results, and why people are not so incentive to publish these results, and what seems to be the most effective way or remedy that we could take to motivate academia and even companies, researchers, to publish the results in a more consistent way?
Who evaluates the evaluators?
Mm-hmm.
So one thing that a lot of fields have norms of you should put out your work in a way that facilitates meta-analysis, because with the assumption that there's going to be other people afterwards who are going to be not looking at primary data, but doing these kind of reviews that look at lots of papers and then do secondary analyses on top. And often that's in many fields that's the norm, that you expect people to do that, and reviewers will say oh, why are we'll sort of enforce it. But we don't really have that culture in AI, and we probably should. There's probably a lot of low-hanging fruit there.
Why do you think that is? Why do you think we don't have this culture of sharing?
Well, I think for a long time there have been things have been so different from each other, right? I have some evaluation that I care about, other people don't care about. The conditions are just so different that that kind of set the culture along a certain path that maybe should be rethought now.
Yeah. There's kind of a larger issue at play, I think, in your question there, Lexin, which is about who should bear the responsibility of doing evaluation, and maybe part of the reason the community needs to do evaluations.
Yeah,
in
not
a lot
only
of
who should be responsible, but also what kind of remedies should we take, because there are many options that we could do this, right? We can publish results, we can publish some paper, we can make some open social media call, some voting, things like that. There are many remedies. So what kind of option that seem more promising to solve this or mitigate this problem based on your expertise in the panel?
I think, it's unconventional, but I think the chair of the panel is potentially in a good position to answer that.
Yeah, so we have a paper getting at exactly this question under review at the moment, and we're advocating for a bunch of different changes. I think, like Joel was saying, the biggest problem is the research culture is not there. So thinking about how we can change the research culture to make that more incentivized and more normal. And I think we can look to the open science movement that's been taking place in all sorts of different disciplines already for clues about how we can approach that. I think things like journals and conferences mandating results being available is a really good first step, and just raising awareness of this issue is really important. And I also think that maybe part of the reason for this, the way the culture is this focus on leaderboards and benchmarks, a bit like Peter was saying before, and that if people are really just focused on getting the best results at any means, then maybe there's less of a focus on making sure the evaluations are robust and transparent.
I think to add to that, like coming into kind of the field of AI as a psychologist, one of the biggest shocks to the system was just the pace at which you're expected to publish. Like, we've got like a 2-year project and we've got like loads of papers already. I'm like, wow, it takes me 2 years to write a paper. What's happening? You don't have time to stop and stare. And actually, that's what you need to do if you want to do a lot of this stuff properly. So I think it's a bit of a self-fulfilling thing in the field that it's going so quickly and you have to do stuff all the time to these deadlines. That means you actually don't have the chance to like prepare your, to release your data set properly and to do the due diligence that I think is necessary to make this an easy thing for the community to come together to do.
Yeah, and 2 more comments. So there is also the issue of cherry picking, which you won't solve by publishing the data because you've carefully engineered your starting conditions and after how many epochs you should stop training and so on, so you have the result that you desire. So one way of dealing with that, I don't see that happen anytime soon, but in pharmacology, people argue for pre-registering experiments. So you say exactly what you're going to do, and then you do it, and you can't deviate from it. The other thing is sort of, I think part of the issue is also what counts as a result, and what are you measuring in your experiments, right? And that's back to the issue of metrics and so on, but if you didn't measure something in your experiments, it's not there, right? And you can't sort of get it back short of running the whole thing again with extra measurements. I've been editing of a journal. I've been editor-in-chief of a journal myself, and I've machine learning, and I often people ask me, okay, why doesn't machine learning do more about, facilitating all this? It's a massive undertaking. It's not straightforward to make sure that people can submit all the stuff and that it works and that it's backward compatible. That's number one. Number two is the poor reviewers who already do all this work with reviewing a 40-page paper. Now they also need to declare that they checked that the code runs and that all the experiments are there. It's not going to happen. It's just not going to happen. So there are huge barriers, I think, towards particularly seeing the pace of development here.
Can we make an AI do it?
Maybe.
If you conceptualize things around like facilitating meta-analysis or something like that, it's potentially more achievable, right?
Yeah.
Because then you have a model of like what another person would need if they were trying to do a secondary analysis on top of your results, and you can try to do the things that support them. And
again, this is a very narrow field of predictive machine learning, but there is, for example, there's the OpenML platform. And that is basically an experiment database. So that just says somebody with the user ID ran this algorithm with these settings and got this result.
Yeah, I think we're seeing
Here is AUC and here's that, and then it's out there and people can do meta-analysis on that. Now that's in a very narrow field. How do we broaden that up to more capabilities?
I think more broadly we are seeing movements in the right direction, right? Like with model cards and platforms like OpenML. So I think we're going in the right direction, but maybe we just need to go there a little bit faster. I think that's all we have time for. So please join me in thanking our wonderful panelists.
Okay, so it's been a long day, but people would like to have more discussion. So how can we just find a solution for this dilemma? So we do have a solution. So let me just talk about two things. The first thing is, what are we going to do now? You earn some refreshments because you've been here until the end. But there's going to be these boards, and the idea is that you take some drinks and you approach some of these boards. There's a person in each of these boards. There will be things as stickers, paper. Just write ideas, even crazy ideas, discuss, leave a little bit of the, after the discussions and kind of ideas on that board. Maybe we'll take some pictures at the end and see what happens. Maybe this is a kind of an experiment. But I think that's a way of organizing the discussions. Of course, you can discuss freely around these kind of the board problems. And of course, some of the lightning talks that you can approach them and ask a little bit more about what they are doing or what they really propose. And just they only had 1 minute for explaining the idea. So that's a little bit what we are going to do now. I don't know how long it is going to be, but that's probably when people disappear, that will be the end. And of course, the second thing and the most important thing, and with this I will close, is just to thank all the co-organizers, the hosts. I think that I want to thank especially the Cambridge crowd who has come and helped with the organization during the past months. The Valencia crowd, of course, part of the Brain team, but very, very especially Valgray. So Valgray is a new thing. It's been just operating for a few months, and these wouldn't have happened with them. And I would like to especially name Anna, the manager of Valgray, and Laura and Fernando for the great help. So if we are here today, and I don't know if this has been a success, but all the failures are mine, and all the good things are because of them. So thank you very much for helping us organizing this. Okay, so now locals, just wait 5 minutes to taste the horchata. Leave the visitors taste it first, and then you can, if they don't like it, then you can take over. Okay, thank you.